So it is 9:35. I think we can start. So very warm good morning to all the participants of IBMS School 2020. And today we have with us Dr. Rahul Singhal, the first speaker of morning session. He has done PhD from IUAC, registered in JNU actually, and he did his MSc from IIT Roorkee, and the postdoctoral he spent some time in Fullerenes State University. So he will be taking the first lecture for you people, students, and please pay attention. And wishing you a very good interactive session with the speaker. So all to you, Rahul Singhal. Please present your slides.
Yeah, thank you, madam. Thank you. I hope my slides are visible.
Yes, they are visible. So you would like to go to the full screen mode?
Yes. Yeah. Good morning, all. So today I'll be talking mainly about the application of swift heavy ions in different kinds of materials. Myself, Rahul Singhal, I'm working as a head and assistant professor at Department of Physics, MNIT Jaipur. And this is basically a lecture in a school. This is not like I'm presenting only my results, it's a talk and every other things. So whenever we are talking in school, it means that it should be more interactive session. So so that whatever I'm telling you, at least half of that you should get it, or it should be helpful for you in your future research studies. Okay, so whenever you have any question, please write down, and at the last of my lecture you can ask me through chat window or whatever the organizer will suggest. And I hope that at least something you would be able to get from my this lecture. I'm not saying it's a talk, it's a lecture, because I'm looking to deliver something to you. And before starting my talk, I would like to express my gratitude to Professor A.C. Pandey sir, Director, IUAC New Delhi, for the organization of such wonderful international school. And after that, there is an international conference also. I am also thankful to the organizing team, Dr. Ambuj Tripathi ji, Dr. Foran Singh sir, Indira madam, Pawan sir, Saf sir, Dr. Ashokan sir. I have completed my research PhD from IUAC only, and these people have been my teachers, my guru, my mentors. And with the support of these people, I could complete my PhD, and then I could get some positions. So it's always good to pay the regards to the to our seniors or the teachers. So now I'll start my lecture. So this is the plan of my presentation come lecture. So I'll start with ion matter interaction, but yesterday I think Professor Sanjeev Srivastava from IIT Kharagpur, he has already talked about ion matter interaction in detail. He has already told you how this when ion beam is passing through the material, how the defects are creating in terms of high energy or in terms of low energy. So I will not discuss in detail these things. I will tell you a few points on that. Swift heavy ions and Pelletron accelerator also, because you are almost all of you are IUAC user, you must be knowing about the Pelletron accelerator, how it is giving you such a high energy, which is a state-of-art machine, and lots of physics is there behind this machine. Lots of manpower, lots of people are working. It's not so simple to get a beam of a million electron volt, okay, MeV. It requires lots of efforts, lots of manpower, lots of money, lots of energy. Everything is there. and we as a user simply going there and taking the beam for our different kinds of materials for the irradiation. But behind that story is really different. It's not so easy to run such a high-end equipment. Then I have been asked by the organizers to speak or to say some results about of swift heavy ions in different kinds of materials, means how we can use these beams for the betterment or for tuning the properties of these materials. Okay, so I'll be talking mainly about 3 or 4 different kinds of materials where my group has used ion beams and we were able to enhance the properties. Okay, and then finally I will conclude, and I will also tell some facilities which are available at my institute, which is NIT Jaipur, and you are all welcome to use those facilities as well. So this is all about basics of ion energy, ion loss in matter. Indra madam, my voice is clear?
Yes, we can hear it properly. Maybe some Ambuj Mishra, is it okay now? It's coming fine for you, Rahul. You can proceed, please.
Yeah, thank you, madam. Why I'm asking, because from last few days our internet connection of our institute is not working properly.
No, it's very clear. It's clear.
Okay, madam. Okay, so suppose for 1 or 2 minutes you are not getting my voice, so please interrupt me on my mobile so that I can switch to different connection.
Sure.
Okay. Yeah. The basic of ion matter interaction, I told you that you have already heard Professor Sanjeev Srivastava yesterday and also Professor Toulemont from France. If you have whenever we are talking about the energetic ions, so mainly in India we are talking about, like for IUAC users, we are talking about the low energy and the high energy. High energy means when we are talking about the million electron volt energy, and low energy whenever I'm talking roughly few tens of keV. Okay. So here basically my aim is to tell you about the MeV energy and irradiation. So in MeV energy irradiation, you can see the cursor of my mouse. Like if you plot the curve between the stopping powers, I'm taking both the electronic energy loss and the nuclear energy loss versus the energy. So you can see you are getting a peak of electronic energy loss at a energy of at almost 10 to the power 5 to 10 to the power 6 keV. It means almost about 100 MeV. Okay. So generally, whenever we are planning some experiment with the high energy ion beams, our aim is to get the maximum electronic energy loss. So we are planning to take the energy in this region where we are getting the peak of this curve, almost 100 MeV. Depending on it may be different in some other experiments, but generally we are looking for that we should get the highest electronic energy loss in our material. Okay, so this curve is well known. You can easily plot using SRIM software. Using SRIM software, which is available freely online. You can download it at your PC and you can draw this curve. Okay. So this is I have plotted mainly for some gold ions, silver ions in SiO2 here. This okay. Now these regions are defined like region 1, region 2, and region 3. Okay, I'm not going into the detail of that, but my aim is to that whenever you are taking a beam of MeV energy, then when this one single ion having energy of million electron volt, when it will pass through your material. So it will create a cylindrical zone like here, like this. Whenever this ion is passing through your material, it will create a cylindrical zone, and the diameter of the cylindrical zone may be of few nanometer only. And then while passing through the material, it will impart this energy to the atoms of the materials in some way, which we can define through thermal spike model. And then some modifications in the material will be produced within this nano cylindrical zones of diameter a few nanometer. Okay, about the cylindrical zone we are talking, it's like an ion track, okay, or nano channels. Strictly speaking, it's not a cylindrical, it should be conical, because the energy is continuously the ion is continuously releasing and losing its energy, so energy is decreasing. But because we are working in the irradiation, like for our thin film is of hundreds of nanometer, then we can assume that it's a completely cylindrical zone. Okay, so the creation of this ion track, what is the mechanism, what is the thermal spike model, how the energy is transferred to the electronic system, and then from electronic system to the lattice system through electron phonon coupling, how the temperature is generated, how the quenching is occurring. I think Professor Toulemont yesterday in his lectures, they have covered all these things. Professor Tulemont is one of the best person in India who can speak or who can, give you the simulation about these ion tracks, about the generation of this ion track. Okay. So my aim is to tell, like here, if you see, I am comparing the effects produced by low energy as well as high energy gold ions in carbon. Okay. Let's say in first case, I am showing you that 100 MeV gold ion are passing through the carbon, and you just see this view, which is depth versus y-axis. So this ion is passing through the carbon film, let's say 100 MeV gold ion, and you can see all the damage or all the modifications are produced in this very narrow cylindrical region. Whereas if you take the same system, but if you change the energy from high energy to low energy, let's say here we are having 1.5 MeV gold. Okay. So here the modifications, if you see, these are basically the simulated result by the TRIM software. So here you can see the modifications are produced in much larger region compared to when we are having the very high energy. Okay. So in case this is the basic difference between the low energy and the high energy, that in high energy, if the energy is above a threshold value, then one track will be created, ion track, and all the modifications mainly will be produced within that cylindrical ion track. Okay. But whereas in low energy, due to the collision cascades, the modifications will be produced in very, very big region. Okay. This you can see the transverse view also. This is like a cross-sectional view of ion track. So this is a small cylindrical zone, but here this zone is on much larger region. Okay. So in case of MeV energy, all the modifications are produced which they are mainly due to the electronic energy loss. Okay, we can neglect the nuclear energy loss, whereas in the low energy region, SN plays an important role. Okay, so here in this talk, because I have been asked to talk mainly about the swift heavy ion, so I will only be talking about this cylindrical zone ion track. Okay, I will not be discussing about this in low energy regions or collision cascades. So about the Pelletron accelerator, if you are using the Pelletron beam, you must have some idea how the beam is, how you are able to accelerate the ions up to the energy of MeV, such a high energy. I'm not going into the details of it. Just I'll show you this curve where the mainly you have some ion source at the top of the tower where you are getting energy of maybe 10 kV or less than that. After that, the main component is the high terminal voltage, and the other two main components are the injector magnet and the analyzer magnet. Injector magnet is basically bending the beam at 90°, as well as it is also like when you are having the ions from the ion source, there may be some impurity ions also. So it will also eliminate those impurity ions, and this you will get the negative ions from this ion source. These negative ions will travel through this tube of the accelerator, and with this injector magnet, it will be bent at 90°. Now these are the negative ions, and here you have a positive terminal. It's a positive potential. 14 like we are saying, it's a 14 million volt accelerator. So now due to the attraction between the negative ion and the positive terminal, the ions will be accelerated. Here they are having the single negative charge. Once they will be accelerated up to the million electron volt energy, after that they will pass through, this is a stripper foil. It may be like carbon foil or I think nitrogen gas. And once they will pass through the stripper foil, they will lose some electrons, or some electrons will be stripped off from the ions, and your negative ions will become the positive ions. Okay, but here you may get all the charge state, not exactly at the one. You may get other like +4, +5, +6 also. And now these because your ions have become positive, and already you have a positive high terminal DAC here. So again it will be a repulsion between the positive ions and the positive terminal DAC. So again your ions will be accelerated. So basically here we are having the double acceleration. Now we are having an analyzer magnet, which will again bend the beam at 90°, and it will also eliminate other charge state. We will fix the magnetic field, because these are the electromagnets. You can change the current, and accordingly you can change the magnetic field. So we will fix the magnetic field so that one particular charge state will pass through exactly at the 90° angle, and other charge states will not pass through at 90°. So it will eliminate other charge states also. And from the then it will go to the switching magnet. and after switching magnet, it will go to desired beam line, whether you want to perform experiment in material science or nuclear physics line or atomic physics line. So accordingly, you can switch. Okay. So these are some idea about how such a high energy is generated. So mainly, if you see, energy gain from the Pelletron accelerator can be divided into three components. A small energy from the ion source, that which I am saying E naught. Then after that, we are having energy due to the attraction force between the negative ions and the positive DAC, and it is so-called 1 into V, because now these are the singly charged ions. After that, there will be again a repulsion between the positive ions and the high positive DAC. So again, but now charge state will be different. So suppose charge state is Q, then again there is acceleration of Q into V, or in terms of energy. So then the total energy will be E naught plus 1 into V plus Q into V. So total energy will be E injector plus 1 plus Q into V. E injector is very, very small compared to this high energy. Sometimes you may neglect this E injector. So total energy is given by 1 plus Q into V. So if you want to change the energy, so you have option, you can change the potential of the deck, and you have the option in terms of the Q also. But generally we are choosing Q in a manner that we should get the highest current, because time is very, very important when you are performing the experiment with the high energy ion beams. And in that case, we are having the optimum Q so that we will get the maximum current. Okay. So this is all how the energy is generated because with the Pelletron accelerator. Now, using this Pelletron accelerator, you can really do the miracle in material science, basically. And nowadays, not only material science, you can use this beam in many other fields also. Like yesterday, I heard Professor Yeshi Pandey sir, Director IUAC New Delhi. He was talking about the NEP, this new national education policy. And in that, now the government of India is giving you freedom to choose your subject as per your wish, as per your interest. Like somebody can take mathematics with music also, which was not possible in India, but if you go to USA or in European, it was possible. Okay. So now you people will also get opportunity to get the subject as per your wish or as per your interest, and not from single university. Suppose you want to take courses from some other university, that also you can choose, and that will also, the credit which you will earn there by passing that course in other university, that will also be added in your final CGP or in your final marks. Okay. So you people will get lots of freedom, and due to that, this NEP is also very popular. But people are there are lots of teams who are working on that, lots of committees. The Shiksha Mantralaya, Ministry of Education, has already constituted. Director IUC is also a part of that. So soon the implementation and the how this new education policy or national education policy will be implemented, soon it will be done, and then you people like PhD students or masters students, you will get lots of benefit. Okay. Now let's come back to the swift heavy ion in different kinds of materials. So I'll start with one most, very important materials which basically metallurgy peoples are using, and these are called basically shape memory alloys, and the higher version is the ferromagnetic shape memory alloys. So I have chosen the different materials with respect to SHE for this lecture. Like one, the metallurgy people are using, second, the material science people are using, third, the chemistry people are using, like that. Okay. So swift heavy ions you can use in any kind of material. It's up to you how you can taking the advantage of this machine. Okay, I'm sure you one or other way everybody can use this machine for their research, and not only the use, you can enhance the properties of your materials, means you can use this machine in a very positive manners. Okay. So now let's come back to shape memory alloys. Now, shape memory alloys are the materials which can remember their shape. Okay. If you deform their shape by applying some perturbation, it may be a temperature, it may be a pressure, and if you remove that perturbation, then these materials will regain their shape. Okay. And if I'm talking shape memory alloys, then I'm using that perturbation, mainly temperature or stress or pressure, but it can also be done using external magnetic field. That comes into the category of ferromagnetic shape memory alloys. Okay. So if you have heard study any course in metallurgy, then this Bartonestic transformation is a very, very popular term in for the metallurgist. This Martinistic transformation is basically a first order phase transformation. So what is this? Like in metallurgy, most of the material you see, we have two phases. Like one is the Martensite phase, second one is the austenite phase. Martensite phase is the relatively soft phase, and because it's a soft, it can easily be deformed and it exists at lower temperature. Whereas austenite phase is a highly symmetric phase, but and a stronger phase also, and it exists at higher temperature. Okay. So what is happening now? Let's say this is our material. This is the macroscopic view, and at the bottom it is the microscopic view. So now here T is greater than Tm. Tm is the Martinistic transformation temperature. If this temperature, if the room temperature is greater than this transformation temperature, then obviously material will be in austenite phase. It's a highly cubic symmetrical phase. All the atoms are sitting at their atomic sites. So highly symmetric phase. Okay. Now what you do, you reduce the temperature and you come below the Tm, Martinistic temperature. Then you see macroscopically there is no change, but microscopically you see within the material two invariants are generated, okay, due to the shear of or slipping of planes or shear of planes. If you have attended some course about the defects in solids, like zero dimensional defects, one line defects, surface defects, volume defects, that then you must have heard about the shear. Okay, so then due to the shear or slipping of planes, two invariants will be generated. And now at this phase, if you apply some stress or if you apply some pressure, then the material will be easily modified and you will get deformed martensite. Now, if you remove this stress or if you increase the temperature, then again this material will come back to its original shape, like here. So this is so-called shape memory effect. Initially, you have a highly symmetric austenite phase. You cool it at below the Martinistic transformation temperature. Then you will get twin martensite form. Now you apply some load, stress or pressure, then the shape will be changed. Now again you remove the load and heat the material, then again it will come back to the original shape. So this can be done by pressure also, by temperature also. Okay. So now in Martinistic, like when you are going below the Tm, then twin martensite form is generated. Okay. So this was when I'm saying this is the main characteristic of shape memory effect, when we are saying like we are doing by the change in temperature or by change in pressure. But here there is one other important property which is called pseudoelasticity. So unlike the shape memory effect, the pseudoelasticity occurs without change in temperature. Like you have here on the x-axis you have a temperature, on the y-axis you have a load. Okay. MS, MF are the martensite start temperature, martensite finish temperature, and AS, AF are the austenite start temperature and austenite finish temperature. So initially our material is in this stage where we are in the austenite phase. If you apply some load, then we will go here, like we are going in the martensite phase. But as soon as you remove the load, suddenly at the same temperature, it will come back to their original shape. So it's like a pseudo-elasticity. Okay. The most like if you see these materials we are using in a spacecraft and even the in our daily life also, the like frames of reading glasses are made of SMA. हम लोग पहले यूज करते थे कि आपका बाई चांस ग्लास निकल गया फ्रेम्स का, फ्रेम को डिफॉर्म कर दीजिए, मोड़ दीजिए और अगेन टेबल पर रख दीजिए, कुछ सेकंड्स बाद वो अपनी शेप रिगेन कर लेगा. So those materials are also made of shape memory alloys. So like very important shape memory alloy initially was NITI. Okay, and then ferromagnetic shape memory alloys are also in picture. Now I told you that it can not only be defined by temperature or pressure, but also by external magnetic field. You apply some external magnetic field, then shape of the material will be changed. You remove it, then again material will come to its original shape. If you simply type on like in YouTube, you can see many videos where people are showing that you are bringing a magnet close to these materials, like it's a wire, and then it will change its shape like a snake is going and something like that. As soon as you remove the magnetic field, the wire will come its to original shape. Okay, it's like earlier some magician was showing some magic, but it's not a magic, it's a science purely. It's basically ferromagnetic shape memory alloy materials. So in ferromagnetic shape memory alloy, this is the situation where you have the austenite phase, then you have the twin martensite phase, and then this is the twin boundaries. But now in this situation, like here the situation of the magnetic moments when you have not applied any magnetic field. Okay, so you have a macroscopically there is no change in the shape. But as soon as you apply some magnetic field, okay, so when a sample is exposed to an external magnetic field in the martensite phase, the magnetic field tends to realign the magnetic moments. This external magnetic field I'm talking, which you are applying, that will try to realign the magnetic moments along the direction of the field, and simultaneously the variants or these twin variants in favorable, those who are in favorable orientation, they will grow with respect to the another one. Okay, so all the magnetic variants, they will be now in same direction, and due to that their shape will also be changed. Okay, so by applying some magnetic field also, the shape can be changed. Now this is all about these materials which basically metallurgy people are using. But now how ion beams are useful in these materials? The first report is, I mean, very early, like in 1998. The first report was given by Barbu in NITI. NITI is the most studied material. Okay, and this was reported by Barbu et al. That you can create some ion tracks using swift heavy ions or high energy ions in these materials. Though it's a alloy, shape memory alloy, and alloy are very hard materials. Like metals, you rarely have any effect of swift heavy ions, okay, due to the conduction electrons. But in this material, you can create the ion tracks, and it was shown by transmission electron microscope images. So what he did, he basically irradiated the NITI shape memory alloy with two different kinds of ions. One is 760 MeV uranium ions, and second is 840 MeV lead ions at a fluence of 5 into 10 to the power 10 ions per centimeter square. Though energy is very high, but fluence is a bit low. Okay, it's difficult for us to get such energy in India, but obviously in European countries you may get it. So now you see, this is the image when the beam of the TM is parallel to the ion beam. So you are simply seeing some spots. Okay, but if you change the direction of the electron beam in TM at 20 degree with respect to ion beam, then you can see the cylindrical structures. It means basically this is the cross-sectional view of the ion track, and now this you are seeing the exactly the ion tracks. Okay, like for other ions also, this first figure is for 760 MeV uranium, another one is for 840 MeV lead ions. Okay, so it is possible actually to create the ion tracks in these materials, provided you have the energy above a threshold value. And that threshold was also given by this great physicist Barbu et al. He has basically given a table. He has performed or repeat these experiment with different kinds of energies, and then he has formulated a table, and he has calculated, okay, this will be the threshold value of SC for this material, particularly NITI, and if you are having energy higher than that threshold, then you can easily create ion tracks in that. Okay, so he also observed that if you are doing irradiation in martensite phase, then with the ion beams you can change their phase also from martensite to austenite. Okay, so this is the XRD spectrum. Initially, when they have not irradiated, you are seeing have the martensite phase where you are having many XRD peaks. But if you irradiate at a 1.8 into 10 to the power 12 lead ions, then you can say that its phases also change. Okay, but if you still go at some higher fluence, then amorphization will also occur. Okay, so using ion beam, it's really easy to change the phase of these materials, because for the metallurgy people, if you think in terms of a metallurgy scientist, then to change the phase is very important for them. Okay, so using some external perturbation like high energy ions, we can change the phase of these materials. So we performed similar experiments, not on NITI, but we did on ferromagnetic shape memory alloy. So we chose NIMNSN. Before that, nobody used that beam on ferromagnetic shape memory alloys. So what we did, we approached the IUAC persons, and we requested 200 MeV gold ion beams, because we wanted to have maximum electron energy loss, so that we can go even above the threshold value for the ion track generation. So we were lucky to get 200 MeV gold. It's not so easy to get 200 MeV gold beam. And then what we did, we planned our experiment in a manner that we have one set of samples where the phase is martensite, and another set of samples where the phase is austenite. So using keeping the same ion beam parameters, same energy, same fluence, we irradiated those materials, and then we analyzed the results. Okay, so this is the Accelerator spectrum. You can see this is a spectrum where the phase, initially the phase is martensite. Okay, now if we are increasing the fluence, suppose we are going from pristine to 6E12, 6 into 10 to the power 12 ions per centimeter square, then you can see the phase is changed from martensite to austenite. Okay, how we are saying this austenite phase, that is a separate story. I'm not going into the detail because it has some superlative planes also. There's a, like using a structure factor, you can easily calculate these planes and everything. So here, at a fluence of 6E12, we were able to change the phase of ferromagnetic sheet nebulae, but still if we go some higher fluence, then again amorphization will occur. Okay, so this all about the phase, but if you see the magnetic properties, because these are the ferromagnetic materials, so for the pristine sample, here the most interesting thing is that you will get one hysteresis. It's not an ordinary hysteresis like you are doing ZFC and FC measurements. Here we are taking a cycle like FC and FH, field cooled and field heating. Okay, so in this cycle you will get a small hysteresis here, and with the help of this hysteresis you can get this temperature ASAF, austenite start, austenite finish, martensite start and martensite finish temperature. So in the pristine sample, which is in martensite phase, this hysteresis is not very clear. If you zoom this curve, you can see some signature of the hysteresis. But if you repeat the measurement for the sample, which are at 6C12 ions fluence, then you can see clear hysteresis here. Okay, and you can easily define now AS, AF, MS, MF. Okay. Now, and after that, the hysteresis has also disappeared because now your material is transformed to the amorphous. Okay, so now this magnetic properties are also enhancing. Not only we are changing the phase of the material, but its magnetic properties are also enhancing. Okay, now it was when the material was initially in martensite phase. Now we irradiated when the we did the same, we performed the same experiment, but initially when the sample was in austenite phase. So when if the sample is in austenite phase, then you can see there is no phase change. Okay, although the amorphization is we can see at 313 or maybe at a bit higher fluence. Okay, but in martensite phase we were able to change the phase, but not in the austenite phase. So here also in austenite phase you are getting a hysteresis. It is again getting more prominent at 6C12, and after that it is disappearing. So the reason is that like why we are getting the change in the phase and why we are getting the morphization, you can easily explain using this core and halo region of this ion track. This is a cylindrical view of ion track. This is the core region where you are having the maximum temperature, and the temperature, if you see the radial profile with respect to the distance, the temperature is decreasing very fast. Okay, so in the core region basically you are getting the amorphization. But if you are at low fluence, then you will not get all the your sample area will not be covered with the core of the ion tracks. Okay, so halo region will be the more. So in halo region basically, because temperature is decreasing, you are getting basically the change of the phase, and in core region it's a completely amorphization. But if you are increasing the fluence and if you are going above the overlapping fluence means when the ion tracks will start overlap to each other, then all the area will be covered by the core of the track and you will get a complete amorphization. So this was the one material which metallurgy people are using, and using with, and with swift heavy ions we can also change the phase. Now another important material is the fullerene, which chemistry people are also using. Even the in solar cell we are using. Initially people studied a lot about the fullerene C60, which is highly symmetrical material. It's like almost a spherical ball. But another interesting material is fullerene C70, which was not studied in detail with respect to the ion beams. So we tried to perform some experiment with ion beams on fullerene C70, and our aim was to see if we change the electronic energy loss, how the structure is getting modified, or what will be how the ion track diameter is changing. So we performed a series of experiments using taking different kinds of beams and energy. Like one case we took 90 MeV nickel ion. In second case we took 90 MeV silicon ion. in another case, we took 55 MeV silicon ions, and in another case, we took a bit higher energy, 120 MeV gold ion beam. Okay, and we kept the same fluence in each experiment, and then using some characterization techniques, we tried to find out what will be the ion track diameter in case of fullerene using different electron energy losses. Okay, so all these experiments were performed at inter-university accelerator centers, and the fullerene is easy to deposit using thermal evaporation. Thermal evaporation is very well-known technique. It's not a new technique. Easily by thermal evaporation, you can deposit the thin film of fullerene, and then you can irradiate at IUAC. So our aim was to see how by changing the electron energy loss, your ion track diameter is changing. So basically, it's a fullerene is a carbon material, and if you are dealing with the carbon materials like graphene or CNT or fullerenes or diamond or graphite, the most important characterization is Raman. Using Raman spectroscopy, you can get to know about the structure, how it is changing with the beam, and other parameters. Okay, you can do some calculations also using Raman modes in order to find out the ion track diameter. Because in swift heavy ions, I told you that everything depends how your materials are getting modified. It is mainly the ion track. Ion track is like, suppose you are in dark room, you want to see at one corner, you have a torch, you just switch on the torch and you can see what is there. Okay, similarly, if you want to see what is there inside in your material in nanometer region, then ion beam is like a torch. Okay, you just apply ion beam, it will create a cylindrical zone, and it will give you what is the inside, not directly but indirectly manner by doing some spectroscopy. You do some spectroscopy, study the changes before and after radiation, then you will come to know what is there inside the material. Okay, so ion beam is nothing like, it's a torch which can give you information in nanometer region which other technique cannot give you, although it is always associated with some kind of damage also in the material, but it's up to you how you can use those damage also in a positive manner. People are saying no, ion beam is always causing damage, it's not good for the material scientists, but it's not true. Nowadays, if you see, I can tell you hundreds of studies where people are using ion beams in some positive manner for some good applications also. Okay, like nowadays people are using ion beams in organic solar cells also in order to enhance its efficiency. Time is limited, so I cannot give all the examples, but ion beams can really do the miracle in different kinds of material which no other technique can do. Okay, so in case of fullerene, if you see the main Raman active modes of fullerene C70, it is coming around 1565 centimeter inwards, and this is a spectra where it, with the increasing fluence, with the increase, let's say from 1E12 to 3E13, you can see how the amorphization is occurring. If it's amorphization, means fullerene structure is getting destroyed, so it will not give you vibrational peaks. So this intensity of the peak is decreasing with the increasing fluence. Okay, so if you are able to do some curve fitting using Origin or some other software, and if you are able to find out the area and how this area is changing with respect to ion beam, then using some equations, you can easily find out the cross-sectional damage area and what is the radius of the ion track. So because here and it's a 90 MeV nickel ion, so ion track is highly only 2.3 nanometer, or I can say the this radius is 2.3 nanometer, diameter will be around 4.6 nanometer. These are other characterizations which we performed in order to see how the surface is getting changed with the increasing fluence. So this is basically SEM images, and these are the AFM images. So we have calculated the band gap. Although it's hardly there is a change up to 312, because band gap is we have calculated using top plot, and top plot is not so sensitive that it can give you in the second place, but that's why I'm saying that there is hardly any change. And after that there was no band S, so we could not find out the band gap. But if you see the roughness is increasing with increasing fluence. Same experiment was repeated for 90 MeV silicon ion beams using same fluence starting from 1E12 to 3E13. 3E13. Yeah, here we have gone up to 6E13 also, because we could not see the complete amorphization at 3E13, because here electron energy loss is small. So because hardly it's 2.26 into 10 to the power 12, so much higher fluence is needed in order to see the amorphization. Even amorphization has not occurred up to 6E13. One has to go even even higher fluence in order to see the amorphization here. And here, using the same Raman spectroscopy, we have calculated how the ion track is formed. So if you see the ion track radius, it is hardly 1 nanometer, means diameter is hardly 2.02 nanometer. It was when we are continuously decreasing the energy. Earlier, electron energy loss. Earlier, it was 90 MeV nickel. Here, it is 90 MeV silicon. Now, these are the surface spectroscopy. I'm not going into the detail of surface one. Now, again, I'm going 55 MeV silicon. Okay, here electron energy loss is 2.7 into 10 to the power 12. And now you can see the ion track diameter is radius of the ion track is 1.14 nanometer. Here also, because electron energy loss is very small, you have not yet seen the complete amorphization at a fluence of 3 into 10 to the power 39 per centimeter square. So now we decided to take a bit higher electron energy loss. So we chose 120 MeV gold ion beams. And at 120 MeV gold ion beams, your electron energy loss is 1.4 into 10 to the power 3. It's not minus 3, it should be 3. Okay. So this is the electron energy loss. And here you can easily see like complete amorphization is occurring at almost at 1e13, because electron energy loss is so high that your ion track diameter will be a bit larger in size, and this overlapping of fluence will come at a bit lower fluence. Okay, so here the radius is around 3 nanometer, or diameter is around 6 nanometer. So after that, what we did, we plotted a curve between the this diameter and the electron energy loss. And using that, you can find out, like you can get some idea that okay, in your material, like you are using this ion beam, because fullerene is used in solar cells, basically organic solar cells. And if you want to use ion beams in order to enhance its efficiency, or in order to create some PN junction in the solar cell, then using that curve, you can get some idea that okay, what will be the ion track diameter for one particular type of electron energy loss. Okay, so this our aim was to develop this relationship. Although this is not a very, I mean, this experiment have already been done by many people for in C60, but nobody actually did in C70. So we tried to do in C70 also these things. And I have shown you only one aspect of this. In each of these studies, we have done some different spectroscopy also. Like in one case, we have shown the IR spectrums also. In another case, we have shown these liquid drop measurements also. So those I have not touched here. I have shown you only one aspect of those studies, but in every study you have some new interesting aspects also. So this is like how you can create that ion track in fullerenes, pure fullerenes, and then how you can find out their diameter of this ion track. After that, what we did, we tried with some nanocomposites also. So we incorporated gold nanoparticles in fullerene, and then we tried to tune their optical properties, basically the plasmonic resonance, with the help of swift heavy ions. So this is the third material that in this series I have already covered about the shape memory alloys, ferromagnetic shape memory alloys, then pure fullerenes with ion beams, and this is the third one where I'm showing you the results of ion beams in nanocomposite, where we have the gold nanoparticles in fullerene. So I'm talking about the optical properties. This plasmonic resonance is very well known thing. It's not a new thing. If you have some metallic nanoparticles, so it will always be surrounded by some electronic cloud. And if you apply some electromagnetic field, so due to the vibration of this electric field, the electronic cloud will also vibrate, but with some different frequency. If you keep on changing the frequency of this electric field, then at one particular frequency there will be a match, there will be resonance, means the energy and the frequency of the vibration of this electric field will be equal to the frequency of the vibration of this electronic cloud, and then resonance will occur. Whenever you have a resonance, means energy will be transferred from one system to other. So here this electromagnetic field will give its energy to the nanoparticle, and you will get a sharp plasmonic resonance here. Okay, this peak is basically surface plasmon resonance peak. Okay, in literature, very well defined theories are available in order to find out theoretically how I mean this peak is generated, or what are the parameters over which this SPR wavelength or frequency depends. Okay, so one interesting theory is Me theory. It was given by a great Italian scientist Guzzolini in 1904, and he has done a calculation of more than 100 pages in 1904. Okay, by basically solving the Maxwell equations. So what he did, he applied all four Maxwell's equations using spherical polar coordinates over a spherical nanoparticles. And by doing a calculation of 100 pages, this paper is still available online. If you type on Google Guzzolini Me theory paper, you can see it. And you know, he did in 1904, where no software was available like Mathematica, MATLAB, or Python language was not available that time, so that you can use some mathematical tool in order to solve the complicated differential equations. Okay, because all Maxwell equations, four Maxwell equations, are nothing but the differential equation or integral equation. But he did himself, and after doing all the calculations of more than 100 pages, he was able to derive this formula for the extension cross section. Okay, and using this formula, you can say here this is a simplified formula, although he has taken lots of assumptions or lots of simplifications, but at least he was able to tell that this extension cross section basically depends on four factors. First one is the V naught, which is basically the volume of the nanoparticle. So it consists of both shape and size of the nanoparticle. And then here we have epsilon omega, which is real part is epsilon 1, imaginary part is epsilon 2. So basically this is the dielectric constant of metal, which is a complex quantity, and epsilon m is the dielectric constant of the embedding matrix. Okay, so here from this equation you can get some idea that the extension cross section, it depends on mainly four factors. In case of nanoparticle, one is the size of nanoparticles, shape of nanoparticles, then what will be the dielectric constant of refractive index of the metal, and what will be the dielectric constant or refractive index of the matrix where these nanoparticles are embedding. So in order to get the maximum cross section, this denominator should be minimum, and as per the mathematical condition, this denominator will be minimum when this curve between whatever we have inside this curly braces, it should be 0. So if epsilon 1 omega plus twice epsilon m is 0, it means epsilon 1 omega is equal to minus twice epsilon m, means the real part of the dielectric constant of the metal should be equal to the minus of the twice of the dielectric constant of the matrix. This is a very well known Me theory equation, or the equation for the surface plasmon resonance. And if you are able to write down an equation for the real part of the dielectric constant of metal in terms of frequency, and similarly for the dielectric constant of the embedding matrix, then you can find out what will be the omega, SPR omega, means SPR frequency. So there are two other, if you want to write down the dielectric constant of the metal, then you have to take two terms, root free electron theory terms and interband transition term. Interband transition term is very, very important in case of silver or silver nanoparticles. So by doing some simplification, or by avoiding this second term, if you take only the first term, then you can write down this epsilon 1 omega due to the root free electron. It depends on the plasmon frequency, and it depends on the omega in this manner. Okay, plasma frequency is a constant for one particular type of metal, which is given by this equation. So if you do the bulk calculation, put this value in here, epsilon omega, and then you put the value of epsilon omega here in this resonance condition equation, then you will get the resonance frequency is like here, omega is equal to plasma frequency divided by under root 1 plus twice of epsilon m. Okay, this is a very, very simplified equation, but again I am telling, we have the concerned person have used lots of assumptions here, lots of simplifications here. Okay, but it tells you roughly that okay, this omega depends on epsilon m. Okay, epsilon m is the dielectric constant of the embedding matrix. So if somehow you are able to change the dielectric constant of the embedding matrix, then you can change the resonance frequency. And similar thing we did with the help of ion beam. So with the help of ion beam, we were able to change the dielectric constant of the fullerene after deposition or post deposition, and then we were able to see the change in the plasma frequency. So what we did, we deposited like gold fullerene nanocomposite or copper fullerene nanocomposites using thermal evaporation technique, because gold and fullerene both can be easily deposited by the thermal evaporation in the same chamber. So here this result shows the when we tried different metal concentration in gold, let's say from approximately from 5% to 33%, and then we see how the SPR peak is generated and how it is changing with the increase of metal concentration, as well as how these particles are getting bigger inside with the increase in the metal concentration. This is when we do not have any ion beam. This is like a synthesis study. We try to synthesize this fullerene gold nanocomposite with different metal concentration. Okay, and here we got one more interesting phenomena, which is called basically surface enhanced Raman spectroscopy for one particular optimized metal concentration only. So if you say this fullerene C70, it is not as symmetrical as C60. In fullerene C60, we have almost 10 Raman active vibrational modes, but here in fullerene C70, because it's a ellipsoidal molecule, symmetry is broken, we have almost 53 Raman active modes here. Okay, and few of these modes are of having very low intensity, so that you are not able to see them through the experimental techniques. Okay, although theoretically using some group theory models, people have given some information about the wave number values of those low intensity modes also, but experimentally it is not so easy to see all those modes. Okay, so by incorporating nanoparticles, basically you are doing surface enhanced Raman spectroscopy, and you can see for one particular metal concentration, which is 11% of the gold, you are able to see the maximum enhance in the low intensity peaks also. So by this, we were able to tell those peaks also which were not available in pure fullerene C70. And why this is an enhancement? Because here you see the gold nanoparticle size is roughly 5 to 6 nanometer. And if you see the diameter of this C70 molecule, it's hardly 7 angstrom. Okay, it means one big gold nanoparticle is surrounded by many small C70 molecules. Okay, and once you have some SPR property in gold nanoparticle, so then this gold nanoparticle will act as a strong source of energy, because it will acquire energy from the electromagnetic field, and then it will transfer its energy to the surrounding C70 molecules. So by this energy, this C70 molecules will vibrate more rigorously compared to the situation when there was no gold particle in the vicinity. So this gold nanoparticles are acting as a strong source of energy, and they are basically enhancing the vibration of C70, and due to that you are able to see the enhancement in the modes. But now question comes that why only at one particular concentration of the gold we are getting the maximum enhancement? It means there should be one optimized size of the gold nanoparticle at which you will get the maximum enhancement, and much more studies are needed in order to investigate why you are getting maximum enhancement at one particular size of the particle. Okay, so we are still working on that. So now what I did, I use ion beams in this nanocomposite, basically gold fullerene. I chose one particular metal concentration, and I irradiated with 120 MeV silver ions beams in gold C60, and I was able to tune the SPR wavelength in visible region from 721 nanometer to 602 nanometer. So it was basically the tuning of optical properties of this nanocomposite of almost 120 nanometer in visible region using ion beams. Okay, so initially in pristine, this SPR is 721 nanometer. But if you are increasing the influence, then it is going towards the lower side, and it is coming around 602 nanometer. Okay. So basically what you have in your system, you have gold nanoparticles and you have the fullerene matrix. When you are bombarding these nanoparticles and matrix with high energy ion, let's say 120 MeV silver beam, then your nanoparticle will grow in size and your fullerene will gradually transform to the amorphous carbon. Okay, so if you do the Me theory calculation, then if you are increasing the size of the nanoparticles, like here from the TM, it is clear that initially the size is 5.7 nanometer, but if you are increasing with the fluence, it is going up to 8.6 nanometer. Indra madam, can I take 5 more minutes?
Yeah, please go ahead.
Okay, thank you. So here, if you are increasing the size, I mean, with the influence, we are increasing the size from 5.7 nanometer to 8.6 nanometer. And now if you do the back calculation using Me theory or some other theory, then it tells you that increase in size of the nanoparticles, gold nanoparticles from 5.7 to 8.6 nanometer will give you some redshift. Redshift means it should go to the higher wavelength, but not of very, I mean, it will not be a very large redshift. You will get hardly 15 to 20 nanometer redshift. But if you are changing the refractive index of the fullerene, like when you are bombarding with the ion beams, it is getting transformed from, gradually transformation is there from fullerene to amorphous carbon. Like from Raman spectroscopy, it is clear. Initially in the black spectrum, you can see the modes of fullerenes. But after that, you are getting these D and G bands, which are basically the characteristic of amorphous carbon. Okay, so D is basically the disorder peak, G is for the graphitic peak, because you will be having some nano order graphitic clusters also. So you are getting D and G bands. And if you see the refractive index of fullerene C70, it is around 2.1. And if you see the refractive index of carbon, although it's varying from 1.3 to 1.6, but obviously it is lower than the fullerene refractive index. And if you have such a large change in the refractive index from 2.1 to 1.5 or 1.6, then obviously there will be a large blue shift in the SPR wavelength. And this is the reason why we were able to see 120 nanometer blue shift in the SPR wavelength with the high energy ion beams. So here this example shows that, this study shows that you can use ion beams in order to tune the optical properties as well as structural properties also, because with the ion beams we are able to increase the size of the nanoparticles also post deposition. Okay, so this is the example how you can use ion beams in positive manners also. One study I perform now when we have gold nanoparticles in pure carbon, not in the fullerene. Because from previous studies, we got some idea that, okay, this large blue shift or large change in the SPR wavelength is mainly due to the change in the matrix, change in the refractive index from fullerene to carbon. So in order to further confirm this, now we deposited nanoparticles in carbon only, and then we tried to see gold nanoparticles. And although we have done these studies on silver also, but I am not showing here because now our aim is to use these nanoparticles, the nanocomposites in solar cells, where gold will be more interesting, or basically copper. So I have done with copper also. So here, if you do same experiment with gold nanoparticles in pure carbon, then you can see you are not able to see those large blue shift in SPR wavelength which you got in case of gold nanoparticle in fullerene. Okay, so here you are able to see hardly 16 nanometer blue shift and then 28 nanometer red shift. Okay, with increasing fluence. So this blue shift is basically the change in the amorphous carbon structure, because amorphous carbon structure is also very versatile. You will there are lots of depending on the sp2 to sp3 fraction, you can have different forms of amorphous carbon also. And this red shift is basically due to the enhancement of the particles. So these studies will further it further confirms that we are getting the large tuning of optical properties due to the change of the matrix. So after that, we tried with copper also, copper nanoparticle, because gold is costly. Although gold is a best one because it doesn't get oxidized. Okay, copper and silver may get oxidized also easily. But if you want to use this nanocomposite in organic solar cells, and in order to reduce the cost of the cell, you should use the materials which are not so costly. Actually, this is the reason why this organic solar cells is not so popular, because the materials like polymers, conducting polymers, which you are using like PCBM, fullerene derivative, these materials are so costly. Like if you want to buy 1 milligram, it is costing around 1.5 lakh. So nobody is using those materials, and even you cannot see the organic solar cells in your commercial life, okay, daily life. So we tried with the copper also, because our nanoparticles are embedded within the matrix within C60, so there is less chance of oxidation. So we deposited copper nanoparticle. This is my last study. Within 3-4 slides, I will conclude my lecture. So these are the copper nanoparticles which we embedded in fullerene C60 matrix, and then we use same beam, 120 MeV silver ion beam, using IUAC Pelletron accelerator, and then we expected the same change in the SPR wavelength. Like here also we are getting high beam, or matrix is fullerene, it will be transformed to carbon, and we should get the same high tuning of the SPR wavelength. But on the contrary, here if you see, we could not see the large shift. We got only a red shift from, this is the UV visible absorption spectra. we could see only a very small redshift of hardly 11 nanometer from 622 to 633 nanometer. Although here, if you see the matrix, here it's a pure fullerene, pristine. You can see all the modes, Raman active modes of fullerene. And finally, you are getting at highest fullerence, which is 3 into 10 to the power 13, you are getting the D and G bands of the carbon. So here also, in case of when you have the copper nanoparticles in fullerene matrix, here also with the ion irradiation, you are getting a change in the matrix from fullerene to carbon. But surprisingly, you are not getting a large redshift or blue shift here. Okay. Other parameters, if you see the band gap, it is again decreasing. If you see the conductivity or resistivity is increasing, means conductivity is again decreasing. The other things are same, but surprisingly, we are not able to see maximum shift here in case of copper. Okay. And we tried to do some surface studies also here, and XRD also tells this XRD was done using some synchrotron accelerator. So this XRD also shows that your copper nanoparticles are here also getting bigger in size. TM also says that you are getting a bigger size nanoparticle. Initially it was 4.1, now at highest fluence you have 8.8 nanometer. Okay. And we performed XPS also in order to see what is the oxidation condition, what is the whether we are getting more oxygen with irradiation. So, but it shows that with irradiation, if you see the core level spectrum, that with irradiation, copper oxide peak is reducing. Earlier, like you have these peaks, enhanced peak, but it is reducing in intensity, or area is reducing. It means with ion irradiation, copper, if you have some copper oxide on surface, then that also it is getting reduced into the copper. Okay. But still, you see that surprising thing is that you are only getting a very small redshift. So some more studies are needed to understand why you are getting a very small redshift or very small change in SPR wavelength with the high in case of copper. Okay, so we are working on this, and we have to perform few more experiments here. So now this is all about how you can use ion beams in different kinds of materials. We have some experimental facilities at MNIT Jaipur. All of you are requested, or all of you are encouraged to use those facilities. I have some facilities in my lab also, which you can use without any charges. Like I have this thermal cooperation in my lab, which you can use to deposit nanocomposite thin films. We have 2 electrodes here, so you can deposit 2 materials same time. Recently, one RF sputtering has also been added into this lab. So now you can deposit thin films by RF sputtering also. We have this high tabular furnace also. It can go up to 1400 degrees Celsius. You can do in presence of any gas also, or we have the pump also. Rotary pump can also be attached, so that you can do in presence of vacuum also. We have low temperature IV measurement setup also using Keithley source 2410 model. So you can do low temperature IV measurements also. And we have developed a centralized facility also at MNIT Jaipur, which is having all high-end analytical equipments like HRTM, FESCM, AFM, XPS, XRD, atomic absorption, glow discharge, and all other like XRD, fluorescence, UV visible, thermal CVD, RF spectring, electron beam, EBSD, DTA, TGA, FTIR, universal testing machine. We have LN2 plant also. We have nanoparticle and zeta potential analyzer also. We have some software tools also, like Materials Studio subscription is there. So all these facility also one can use, but these are chargeable facilities because lots of money is needed in order to buy their maintenance. I mean, for their maintenance and to buy their consumables. So centralized facility is a bit chargeable, but all the facilities which are available in my lab, that one can use without any charge under collaboration. So all those who want to use those facilities, they are encouraged to use these also. So with this, I finish my talk. Thank you. Thanks everyone.
Okay, thanks a lot, Rahul, for such an enlightening talk. Actually, you have covered the aspects of how swift heavy ion reacts with the material and what could be the possible outcome in different field, SPR and all.
Yes,
and you have touched upon the important aspects of our accelerator and how the beam is important to utilize in research. So your lecture is now open to the students if they have any questions. Few of them are written in the chat box. So Bhim Khan, if you can hear me, can you read out your question?
Yes, ma'am. Hello.
Yeah, we can hear you. Please
Hello.
proceed. Yeah, we can hear you. Please
जी
proceed.
हाँ जी actually ma'am I want to ask that why there is an increase in the morpher nature after the irradiation at accelerator. So can you sir explain me?
Yeah. Beam, like initially, I hope you are talking about the nanocomposites where we have fullerenes. So
Okay sir.
fullerenes are getting amorphized with ion irradiation because fullerene molecule, if you see, this is a very small and sensitive molecule, and the bond energy between the two carbon atoms in fullerene C60 or C70 is very small. When you are bombarding these fullerene molecules with such a high energy, let's say 120 maybe gold ion beam, so it will create one ion track, and within that ion track, the temperature rise will be of around 10,000 of Kelvin. At such a high temperature, every bonds between the two carbon molecules, carbon atoms, will be broken, and within that cylindrical zone everything will be in amorphous carbon. Okay, and that the diameter of that cylindrical zone is almost 5 to 6 nanometer for 120 MeV silver beam. But if you keep on increasing the fluence, then these cylindrical zones will also be increasing over your surface, over the entire volume of your film. And at a fluence where you will get a start, the overlapping of these tracks will start, at that fluence you will get the complete amorphization of your film. Okay.
Okay sir. हाँ जी तो सर
So,
ये मतलब जनरलाइज नहीं है.
नहीं बीम जनरलाइज नहीं है, डिपेंड्स on material also, material to material how the amorphization is happening, and this varies. Like in case of alloys, and if you say in case of alloys, it's difficult to get amorphization at the low fluence or at even at moderate fluence. So that depends on the properties of the materials also. What is its thermal conductivity? What is its melting point? What is the bond energy between the atoms or between the molecules of your material? So it's not a generalized thing.
Okay sir. Thank you
okay.
sir.
Okay. Now switching over to the next question. So it is from Prachalit NC. So,
Yeah, his question is what will be the change in spectroscopic factors when a fluorescent salts are irradiated in amorphous forms? Yeah,
yes.
Prashant, your question is not very clear. Could you please repeat what you want to ask?
Hello, sir.
Yes, Prachit.
Sir. The fluorescence salts are studied in the solution form, right, sir?
Mm-hmm.
For example, dyes and all.
Mm-hmm.
So my question is, when the salts are irradiated with in the amorphous form, can we expect a fluorescent properties?
First of all, it's difficult to irradiate any material in solution form.
Okay.
So if you can get out some extraction or powder of that, then you can stick that on the carbon tape or some using some other mechanism. You can put in a chamber, and then you can irradiate it. And after irradiation, it is for sure that fluorescent property will be changed, because fluorescent properties or luminescence properties, they all depends on the defect centers available in your material. So with
Okay.
the irradiation, obviously defect centers will be changed, and obviously you will get a change in the fluorescent. But the problem is that all these light dyes,
Okay.
if they are in solution form, so it's difficult to irradiate in solution form. So we have to
Okay.
get some powder from extraction of that or some
Okay.
other mechanism. After that, obviously there will be very interesting studies with ion irradiation in these dyes, because like I have used some organic materials like solar cell materials, so conducting polymers, and we have
Sir.
studied like P3ST and others. We have seen the significant change in the luminescent property.
Okay, sir.
Yeah.
And about excited and ground state characteristics, regard those properties, can we expect the changes in those two, sir?
Excited
Uh,
state and ground state properties
yes.
with respect to
Up,
what?
up, after irradiation.
After radiation, which property you are talking?
About an oscillating frequency and strength and its
Ye-
absorption cross
Yes,
section.
yes. Exactly. Because with the radiation, if you see oscillation frequency of the nanoparticles, the size is getting bigger. Okay, and it
Okay.
depends on the size of, your wavelength of incident light also. So obviously, your this excitation or from ground state to higher state, it will be changed. Definitely, there will be a change in that.
Okay. Okay. Thank you, sir. Thank you.
Yeah.
Okay, so if there are no more questions, so I would like to thank Dr. Rahul for accepting our invitation and delivering such a wonderful lecture for which is of use to the students. So thank you so much, Rahul.
Yeah, thank you, madam. Thanks a lot, madam. Yeah.
So now we can move to the next speaker, Professor Tapobrat Ghosh. Sorry, Som, Tapobrat Som. So Professor Som, welcome to IBMS school. So he has done his PhD from IIT Kanpur, and later he joined our institute IUAC as a postdoctoral fellow. So he has a long association with IUAC, and he is presently working as a professor in Institute of Physics Bhubaneswar. And today we will be hearing from him the basics of nanopatterning with ion beams. So Professor Som,
Yeah,
good
thank you.
morning.
Yeah, good morning, Indra, and thanks to Dr. Asakun and the entire organizing team to give me this opportunity to share my thoughts with all of you, and particularly young scholars. These lectures I have planned in such a way that mostly it will be based on several examples, and you will get to see that how ion patterning, self-organized nanopattern formation actually depends on several parameters, and we will try to address several fundamental questions. For instance, we will try to see if there is a common mechanism or not, if there is some behind pattern formation, if there is a universal process or not, and so on and so forth. And then after covering these things, I will try to share with you several possible applications such as pattern surfaces. Okay, and with these few words, once again, I wish you a very good morning, and let me start my presentation. Just 1 minute. Give me a few seconds.
You're looking totally dark.
Can you see it?
No.
Yes, sir, it's
Yeah,
coming up. It's
now.
coming up. Yes, sir, it's coming up. So,
okay, so this is the talk title. Okay, and nanopatterning and applications. There will be 2 lectures formally, but I don't know where the boundary will come, and but I'll try to tell you about the patterning story of pattern formation first. Yeah. Okay, so before that, a very brief introduction on our institute. Mostly the ion beam facilities and kind of related facilities, actually, you can say, which are useful or meaningful rather for such nanopattern formation and to study their further functionalization. And when we talk about functionalization of certain surfaces, we do need to take care of growth of thin films on them under various conditions, and nano-dimensional and particles, nanodimensional thin films with nanoparticulate grains, and so on. And we are very well known for our old 3 MB Pelletron accelerator facility. Then we have subsequently developed a 40 kV negative ion beam facility. Well, I mean, it reaches these days, the capacity is 40 kV, it reaches up to 28 kV. So this is actually a very old SNCC source which came out of the Pelletron when we replaced it by a multi-cathode SNCC source with many targets which could be loaded together. Then we have started developing a 30 kV electron cyclotron resonance ion source, best low to medium ion ion beam facility. It's up the way, although we are able to gate ion beams, all gaseous ion sources and some solid materials which we right now have with us. This ion source can deliver up to 22 to 23 kV ion energies at the moment, and is extensively used by two of my PhD students. And then we have a focused ion beam facility, and then we have a couple of very low energy ion sources, starting from energy starting from 50 electron volt to 2 kilo electron volt. Okay, this is the kind of ion source that will be focused here. So far our results are concerned, but it's not limited to that only. We have used extensively the IUAC facility in terms of both the LEIBF. I was one of the fortunate persons to see through the establishment. I was the first formal user of the old LEIBF facility. And of course, now in that room, probably this negative ion beam facility is there. So we have used that as well in recent times. And then we do need to characterize these samples. So when you talk about nanopatterning, and particularly ion-induced nanopatterning forming at the surfaces of various materials, we need to characterize them well. Big and more so when we talk about or think about using those pattern surfaces for potential applications. It's very important. So for very high resolution TEM facilities is always a win-win situation for us. In absence of that, means always if it is not accessible, then scanning electron microscopy also gives us good results. But for us, the bread and butter kind of machine is the atomic force microscope, and where we should be equipped with several modes. Okay, and we have an SRIM research facility, and also a multi-mode system with my colleague Professor Verma. And but the SRIM research is FM is a very frontline FM, probably the best in the world at this moment, and it offers a very high resolution with a large scan area with a single scan head. It goes up to 100 micron by 100 micron, and we are also equipped with variable field magnetic module. What it means is during the magnetic force microscopy study, we can vary the magnetic field across the sample. Okay, and we can vary it up to 2 kilovorsted with an accuracy of plus minus 1 worsted. So this is a very powerful system, and we are equipped with several facilities like Kelvin for force microscopy facility, then conductive atomic force microscopy mode, then we have dual pulse tunneling microscopy mode, and PFM, that is piezo force microscopy, and then we can also apply pulses to do neuromorphic computing studies on resistive switching materials. I suppose my PhD student, Mr. Bhubaneswar, will be presenting a poster in a couple of days' time through a short presentation, and in the forthcoming conference after the school gets over. And basic thing is, this is not limited to these kind of studies. It depends on what kind of systems we are interested in. It depends on the same thing I'll probably support in a different context or substantiate in a different context, whatever Dr. Al Singhal was talking about. Nothing is unique. In this beautiful world of material science, nothing is unique. However, sometimes we do feel happy if we can unify certain things, like human beings always looking for a unified and all these things for explaining very fundamental physics and particle physics and all these things. So unified theoretical framework is always a desirable thing, but in most of the cases, since it is not a naturally expected thing, we must look towards other characterization facilities also when we talk about nanoscale pattern formation. Say, for instance, depending on what kind of properties it offers, the pattern surfaces offer, we can take help, or we may need to take help of X-ray photoelectron spectroscopy for compositional analysis. We may need to take help of extra diffraction facility. We may need Rutherford backscattering spectrometry facility, and so on and so forth. Okay, and then magnetic studies, and then plasmonic studies. It offers actually a gamut of potential, and that's how I will try to take you through a journey of whatever we have achieved over the last 10 years or so, through which is practically the outcome of 2 of my PhD students and the 3 postdocs. Okay, and then when we come to talk about the functionalization of these pattern surfaces, we do need very high quality thin film deposition facilities, and we do have UHB e-beam evaporation facilities and pulse DC and RF spot deposition set up with a glancing angle deposition the module with that, then pulse laser deposition and molecular beam epitaxy as well. Okay, so these are very quickly the photographs of a few of these setups, the ion beam based setups that I was talking about. This is our very new setup where we have this patterning ion source here. Then this is the distribution chamber, and this is the MB chamber. So when we talk about growing magnetic thin films and even patterning of silicons or for instance other semiconducting materials, then we get to have a thin native oxide layer formation as soon as we take out of the patterning setup. Okay. This is our old setup. This we established in 2009. Here, only patterning can be done, and at the end of the day, we have to take it out of the chamber for deposition of thin films and other characterization technique. So we never ever can address the exact fate of the surface right after the pattern formation. Particularly, we talk about silicon. Silicon, we know for obvious reasons, silicon is the most prized system. Silicon is the most prized system in terms of growing other system and for instance, making them functionalized and so on and so forth. And when we talk about silicon, it's very prone to the formation of native oxide. And so to get rid of that, we have designed this system where we don't need to take out, and we are in the process of adding a lead OJ system right on this flange. You can see this flange here, okay, which is protruding from this small flange, okay. So lead OJ will come from the top and sit here. So right after pattern formation in this small chamber, perpendicular, this is the backside of the ion source, this square gray surface. And ion source goes like this, okay, and like here is the ion source. Is a cylindrical small differential system. The pumping system is attached with it, and so we make the patterning here. Then we just take it out of this chamber, put it under lead OJ. We evaluate first the near surface crystallinity of the pattern surface as well as this composition and analysis, and then we transfer it to the distribution chamber, and through the distribution chamber we can take it to the growth chamber for ultra thin growth of ultra thin films, and particularly plasmonic systems in terms of more of magnetoplasmonic systems or bimetallic layers. Apart from gold, I mean, other things have a tendency in terms of nanoparticles grown on these pattern surfaces to get oxidized. But to get rid of those problems, and we have plans, and we are in the process of adding for which dedicated port is already designed, and we have to just fit into it the spectroscopically setup. So with these few words, we all know that what kind of ion radiation induced processes go into a material. We are all aware of, and this expands from this spans from very low energy ions like 100 eV to 10 keV or even hundreds of keV energy. And today we get to see here, through this view graph, I'm showing you that you can have sputtering, we can have smoothing, ion-induced smoothing. And sputtering, when it is operative, it means ion beam bombardment is operative, then smoothing and sputtering induced roughening can take place. And smoothing occurs because of ion induced diffusion, and then overall there could be surface instability, and this surface instability is all about we're going to talk today. Okay, this is what gives rise to corrugated nature of surfaces. And then underneath, there are many other processes which go on. I'm not getting into those things. So this is the pattern formation regime. Okay, ion-induced surface instability. And there could be ballistic processes due to shear two-body elastic collisions, collisional processes, and thermally activated processes as well. Okay, so next, let me tell you that what we all do in my laboratory here at Bhubaneswar. And this is a part of our entire span of research. This is only the projection on what we do with self-organized nanoscale pattern surfaces. We do try to address anti-reflecting materials either directly through the pattern surfaces or by making them nanoscale functionalized materials. Anisotropic plasmonic property has been addressed. Cold cathode electron emission, the field emission is kind of a very specific property that we are putting a lot of thirst in these days. And then nanoscale magnetism through thin film nanoscale magnetism or resistive switching, or we can make use of the surface, the pattern surfaces to study their hydrophobicity. Okay. And so on and so forth. This is unlimited. More applications are coming up. The reason is, one aspect is to study the pattern formation. Enough has already been done over the last several decades. And by now, to some extent, a good understanding has been there. It has developed over a few decades. And you can see low energy ions. When I say low energy ions, is all these images that you see here, they're all atomic force microscopy images obtained from several ion pattern surfaces where the ion energy is limited to within a couple of keV, starting from hundreds of electron volt to up to few keV, or maybe limited to 1 keV, etc. And you see very different kind of patterns which come up, and starting from silicon to germanium to indium antimonide to gallium antimonide, indium phosphide, zinc oxide, silicon dioxide, gallium arsenide, and so on and so forth. So various things, and it's not limited to this. We have results from TiO2 as well. I've not jotted down here. But the important thing is, you keep varying the ion beam parameters. There are the experimental conditions. You keep changing your samples. You keep changing even for the same sample, different ion species you allow to bombard upon. Even for the same class of samples, same substrate material, if you change the crystalline direction, crystalline orientation, the temperature, the azimuthal rotation, several parameters, the incident angle, you get to see such variations, or so rather such variety of patterns to evolve. Okay, and this is what ion beam does. It helps reorganizing the surfaces, and that's why these are self-organized patterned surfaces. Advantages galore. Single step processing route for large area patterns. Let me tell you, when we talk about these kind of ion sources, very high current ion sources, these can all go up to hundreds of microampere current, and with a flux of 10 to the power 15, of the order of 10 to the power 15, close to that, 15 ions per square centimeter per second. And you get to go along with large amount of fluids. We can go, it may take in some special cases several hours, but that's okay when we address a very novel problem. And when these are not so high running cost ion sources, or rather ion sources with not having so much of high cost factor involved to run in day-to-day basis, I mean, nothing goes wrong. We are still in a win-win situation. And this is faster, and let me tell you, large area patterns, when you talk about, is a complete wafer scale process at a single go. We have generated patterns on a complete gallium arsenide wafer, complete inch gallium antimonide wafer, and so on and so forth. So the kind of results we see here, gallium antimonide, starting from room temperature to high temperature, starting from without rotation of the without azimuthal substrate rotation, starting from room temperature to high temperature. I mean, starting from rather liquid nitrogen temperature to high temperature. Our setup is equipped with a single go. We have not to go anywhere. We have not to change anything. We have generated large amount of different patterns, fascinating patterns, and these are extremely ordered ripple pattern. Okay, and so is for an indium phosphide, so is for gallium arsenide, and you can imagine that how powerful the technique is, this processing route is, and also shows the terrific power of our most lovable ion beam physics in materials. Okay. And that's what I mean, that complete wafer scale uniform pattern formation, because these are broad beam ion sources. And I say faster and cheaper because when we talk about commercial wafer fabrication or doping or any other ion implantation related processing, it takes actually quite a bit of machine time, quite a bit of infrastructural facilities are involved. And you can only keep adding to it, to this list. However, here it is very fast, as I told you, very fast because of extremely high current over a broad area. And automatically it's a small setup, so it's going to be very cheap. And then tunable pattern parameters, as I have already shown in the last slides. Many learned speakers through, learned researchers through the globe had contributed in this book. You can learn really starting from fundamental to the applications. The book is named as Nanofabrication by ion beam sputtering, application to applications. And once again, as I told you, pattern formation or nano pattern formation by using energetic ion beams under different parameter, the experimental conditions are dependent on several factors. So this is anything but simple to understand such ion-induced patterning on material surfaces. Okay, and another important thing is the presence of impurity. In the early days, means our late 90s, early this millennium, okay, there used to be many fascinating papers reporting wonderful pattern formation on several materials, which subsequently turned out to be metal impurity induced. And people at that time didn't care about, because they were more bothered about, there was a mad rush rather to create more of nano patterns on the surfaces of several materials, rather than minding about, counting about the quality of those material studies. Not much. Mostly AFM or ACM images, beautiful continuum theory-based simulation studies, and then you could publish in top papers, I mean top journals. Okay, so impurity is one thing that has to be looked into, and for that, what we suggest, we recommend through our own learning process that we have realized is, you must always try to cover your sample platen, that means the sample holder, by a similar material on which you are planning to create surface patterns. For instance, if I'm talking about working on nano pattern formation on the silicon surface, we must take care that it has to be, the sample platen should be covered with the silicon wafer completely, because there has been reports from top laboratories as good as Harvard University that even silicon sputtered on the actual sample from surrounding can give rise to very different pattern formation. So homogeneous or heterogeneous doesn't matter. One should be absolutely sure of that there is no source of any impurity, no matter homo or hetero, on the surface of the pattern material. Okay. Now, there's a first observation of periodic nanoscale ripple formation on glass. This goes to 1962, nearly 60 years ago, a French group led by Navez, and several kinds of pattern formation were there. And it was established by great Peter Sigmund, that where he has put forward many thick reviews and books and on sputtering. So it is basically, in layman's language, one can understand, as I told you also through that first schematic, that the local sputter yield will be depending on the curvature of the surface. And the main point is the surface is never a plane one. So there is a tendency towards less sputtering near a top and more sputtering near a valley. Okay, so here and here there will be difference. Okay, and so finally, remember the sputter yield, local sputter yield, will be dependent on the locally deposited energy density as well. And we'll see that energy deposition is more. Okay, that means sputtering yield is more, and so gives rise to more and more instability. Let us go forward. This is the revisiting kind of situation, because after Navez and his co-workers discovered that pattern formation is a reality, okay, many people, of course, wanted to hide. In the sense, they never highlighted, the field did not go forward because people got scared that in the process of particularly seams analysis and so, when pattern formation takes place, so that's the kind of thing they never wanted to have, because it was materials analysis. And so pattern formation they wanted to avoid, but then it's a seminal work from Stefan Fachko and his supervisor during his PhD thesis work from University of Aachen, Germany, where they had shown that beautiful gallium antimonide dots were forming on gallium antimonide single crystalline surface with the help of argon ions, and they varied ion energy, fluence, and whatnot. And this is a TEM picture. Okay, so these dots were crystalline dots, and base and height were roughly around 30 nanometer. Okay, wonderful work. And following the PhysRep papers where they tried to explain, and several other systems, and goes beyond saying that Stefan Fachko is one of the world leaders in this field. So, what could be the motivation? I mean, that's what I was telling you. This is now already known to you through these few graphs. And yes, beautiful patterns form. What are our motivations to trace? What we addressed over these last decade or so in the process of understanding pattern formation process, and or say the nanoscale functionalization of pattern surfaces. The questions are, is it possible to create patterns on every material? Then we are seeing here till now the cases of low energy ion induced pattern formation. Now, medium energy ion induced pattern formation, does it take place? Does it follow the similar mechanism which we try to apply for low energy ion induced nano pattern formation on the surfaces? Okay, do they show common features? Then which physical processes actually contribute? Then question is, microstructural influence in pattern evolution, is it there or not? Because we know that generally, even for low energy ions, once it crosses a fluence of 10 to the 15 ions per square centimeter or so, you can expect, when most of the materials are for the non-metallic cases, you can expect a good amorphization. And so as I was telling you, the major concern would be, and our minds would like to see whether so much of so different and fascinating patterns formed under different experimental conditions, will they be possible to be understood under a unified framework? Other way around, if we can do that, can we predict pattern formation without doing experiments beforehand? Why I say that? The question is, you will see through my presentation, that as we keep on moving ahead, that you have to actually cover the whole angular window to understand the mechanism responsible for pattern formation. And then if we keep doing this, you can imagine to know whether the pattern formation will be taking place on TiO2 or not, on SiO2 or not, on the aluminum oxide or not, etc., copper oxide or not. How do you know that? One and only way, if it can be doing experiment, sometimes it could be very rigorous. Okay, and a lot of resources will be needed, manpower will be needed for a successful. That means for a successful application-oriented work, it will be easier that if we can address the underlying mechanism under the unified framework, then probably if we do those kind of calculations or simulation studies, then before doing the experiments, we can rather identify the pattern formation window in terms of angular window. That means the incident angle of the ion beam on surfaces. Okay, let's see how it goes. Now, as I told you, surface curvature dependent sputtering, the famous Bradley-Harper theory was developed on that in 1988. Prerequisite was the amorphous target. So energy reaching to a point P, remember here, energy reaching to a point P due to an incident at point P prime. Okay, that means here to here, downslope. It is greater at valleys compared to hills. Okay, so valleys are eroded faster compared to hills. And that is what is the source of the growth of surface perturbation. So it's a competition between sputter erosion and surface diffusion that results to ripple formation. That's the general understanding based on surface curvature dependent sputtering, which follows from Bradley and Harper theory. Now, the success of this theory is a lot. Ripple formation mechanism can be understood very nicely. Hundreds of papers have been published where, even though it was not related to this theory, people had attributed to this famous Bradley-Harper theory, but results can be very nicely explained in light of Bradley-Harper theory. But how, etc., most of the people didn't bother to address. Now, this theory actually teaches us that ripple orientation does switch at a high incident angle of the ions on target. And problem is, it predicts ripple formation at any value of incidence angle. But then practically, that's impossible to address because 90 degree will also be included in that. And experimental observations actually also did not speak in favor of this prediction. So this was a drawback. Now, it talks about pattern formation in the linear regime. So this is the continuum, this is the equation based on continuum theory. And here's the sputtering induced surface roughening terms, this the surface erosion coefficient, and Sx and Sy along x and y directions. And this is the surface diffusion. And if Sx is less than Sy, less than 0, that means whenever Sx and Sy would be negative, in between critical angle, that means the pattern evolution critical angle is involved for any pattern evolution. So that critical angle for pattern evolution has to be less than 90 degree and greater than theta. Okay, and so ripple rotation will take place for the condition that Sy has to be greater than Sx, unlike Sx greater than Sy. Okay, and Sy has to be negative though. Okay, and for again theta should be greater than theta critical and should be less than pi by 2. So very obvious that a very high ion incidence angle, this is supposed to happen, pattern of rotation of pattern wave vector. And so sputtering induced instability that can be found out from this equation as per Bradley and Harper theory. And gamma xy is a complex function of dimensions of energy distribution ellipsoid, basically projected range, straddling, and etc. Okay, a crucial point is simulating the energy ellipsoid is possible by SRIM or SDTrimSP code. SDTrimSP stream, I'm pretty sure Professor Hofsaess will be talking a lot. Little bit that we have learned is through Professor Hofsaess only. We had collaborated with him also. It is a very complex code, but it is pretty accurate. And Professor Hofsaess, I'm pretty sure, will be explaining to you at great detail. So I don't think that it makes any sense for me to touch upon that thing, but this is a very useful code. Now, then came the concept of ion-induced mass redistribution. Although, when I say that it came for understanding pattern formation. Okay, and Carter and Bizniakov theory popped up to explain certain pattern formation aspects observed on silicon surface, where they utilize tens of keV energy for incident ions and in form of argon on silicon. And here, one important thing comes is the average displacement of recoils. Okay, and these are the equations. But problem is, a crucial problem is, delta is not very easy to be calculated exactly using SRIM, although some near about value may be possible. I'm pretty sure Professor Hofsaess will touch upon all these things in detail, so I'll move on. For this theory also, Carter-Bizniakov theory, it predicts ripple formation from a critical angle theta c. That's correct. Unlike Bradley-Harper theory, as we had seen here, it predicts pattern formation at any value. That's why it was a drawback for this thing. And in contrast, Carter-Bizniakov theory says that predicts actually ripple formation from a critical angle. That's because they had observed this, that pattern formation on silicon surface for tens of keV energy started evolving beyond 45 degree ion incidence angle. However, again, it has a drawback as well. It predicts ripple formation up to theta is equal to 90 degree. And you see that is because two theta terms appear here. Theta is the ion incidence angle. So when you talk about even 45 degree critical angle, if it starts from here, so straight away, it will be in principle, it should be expected to see pattern formation in a 90 degree, which is again very difficult. How can we see pattern formation because 90 degree ion को कैसे चलाएंगे? So that's a major problem. Now, I will now start talking about quite a bit on low energy ion irradiation, but I'll be switching back and forth in between tens of keV ion energy related results also in terms of pattern formation. So if we start with, say, for instance, a schematic diagram of this, and like this with 500 dB argon ions bombarding on silicon, so instability will take place. It can be seen as a competitive processes due to sputter-induced instability and mass redistribution. So in this smoothing will be possible to be observed and is observed below, mostly for silicon below 45 degree. And instability predicted and reported also above 45 degree. But many people predicted, I mean, experimentally had shown dot formation, ripple formation at very low angles as well, low ion incidence angle, which are far below 45 degrees. So those were all intermediate. On today's date, as a senior colleague, I can suggest you that don't take those results very seriously in terms of thinking to reproduce them. You may not be able to reproduce them. Okay, but more or less, many people have reported that in between 46 degree, 47 degree up to 51, 52 degree, mostly for 500 electron volt argon ions. Okay, if we think in terms of the critical angle for pattern formation, so this could be the typical values. Okay, and so just 1 minute. Now, So beyond this critical angle, we indeed get to see ripple pattern evolution, and then surface instability plus surface relaxation occurring due to ion-induced diffusion or viscous flow in the ion-induced amorphized layer that happens in between room temperature up to 200 degrees centigrade or so. Now, amorphization of the crystal surface, however, takes or expectedly take place, as I told you, mostly in and around little above 10 to the power 15 ions per square centimeter. Now, this is the situation for silicon that we observed. Up to 51 degree, nothing evolved. Sample remained as smooth as the pristine sample. Okay, I have not shown here these smooth surfaces. And beyond 51 degree, ripple patterns started evolving. I have not shown either that as well, because very nice ripple patterns, very well known. And then, as you see, that for 65 degree, 67 degree, you see kind of broken ripples evolve. And these broken ripples actually give rise slowly for even higher incidence angle to formation of this nanoscale facets, and they grow even bigger with increasing this thing, and then slowly pattern nano needle-like, they become actually very thinner in dimension, needle-like structures they get into, and then slowly we get to see the ripple orientation switching at even higher angle, and then the ion surface becomes as smooth as like pristine. And you can see the surface roughness evolution. Okay, so starting from 65 degree, as I told you, I have specifically avoided to show here all these data starting from 0 degree ion incidence angle. We have up to 88 degree, 89 degree, as much as we could with our manipulator. But for all practical purpose, beyond 85, 86 degrees, it's not very desirable to have. It's not very expected to have very reliable results. Now we see that so surface roughness falls close to the pristine surface at very high incidence angle, because this surface again becomes smooth. And this gets very nicely represented by the corresponding sputtering yield as well, which depends on against the angle of incidence. Okay, so near around these angles, we get to see that sputtering yield is also quite high. So is the surface roughness getting evolved? Okay, high surface roughness, and then subsequently this fall. So this is the true manifestation. So ripple rotation takes place through a series of different types of pattern formation. That's the take-home message. I will come back to this kind of formation of these faceted structures, and will show you that how fascinating usages can be thought of, which we have studied through our experimentations, and how this transition from these ripple patterns to these facets actually take place, and all these will come slowly. Now, this is known as a parametric phase diagram, or I have presented here two such parametric phase diagrams. Mostly this shows argon in silicon at room temperature. These parametric phase diagrams are nothing but a plot between energy versus angle of incidence. Okay, and that means if we keep varying ion energies, and for a given ion energy we keep changing the incidence angle on silicon surface, we get to see such patterns. So these are stable surfaces, means smooth surface. Excuse me. So for us, as I told you, silicon starts showing pattern evolution from 51 degree, and remember these data are obtained after doing probably hundreds of experimentation on samples different times. Okay, this was a thesis work of my first PhD student, Tanmay Basu, and this is the parallel mode ripple. Okay, that means the ripples will be perpendicular to the direction on the ion beam projection onto the surface. And then again at higher incidence angle, it becomes stable surface. That means smooth surface. However, this is in the linear regime of pattern formation. Okay, here you see that's the reason. I mean, I have shown all the way up to 7 degree, 78 degree odd that parallel mode ripple formation. Correct. And linear regime, that is typically, it forms under low ion influences. Very different kind of manifestation of ion-induced surface evolution we do realize when we go to high influences. Okay. Again, you see up to 51 degree, everything remains same, but then we get to see all those unusual pattern formation like these, etc. Okay. All these things, they evolve. They evolve at higher influences. And then we see we have called it unusual patterns. At that time in 2012, when we reported this, we called it unusual patterns. That was the title of our paper also in applied surface science, that's unusual pattern formation. Because such faceted nanostructures, nano-needle-like structures, they were not talked about. We did indeed very careful experiments right from day one, taking the experience of other researchers in terms of creating complete impurity-free surfaces. Okay. And then we did see these perpendicular multiple pattern evolution, and then followed by stable surface. And these patterns, these unusual patterns, could be very useful for important applications, although ripple patterns are also very useful. And we can tune the ripple amplitude, we can tune the wavelength, etc., which are actually very good for applications because tunability will come in picture. And for understanding the pattern formation mechanism, that is fundamental physics wise, I mean, this is linear regime is pretty useful. Now, I tell you the same ion incidence angle of 60 degree. Here I have not shown, but 60 degree comes in terms of quality degree. You can think of sputtering yield is almost comparable with 60 and 65 degree, not much difference. So is the roughness. Okay. So patterns are more or less similar in case of 60 degree as well. And we chose 500 degree argon ion, same 60 degree incident angle, and 5 into 10 to the power 17 ions per square centimeter, with which we work to generate these kind of patterns, that's written here. However, we gave a rotation, as a neutral rotation to the surface with respect to the incident beam. So we first fixed at 60 degree incident angle, first fixed that, and then the substrate continuously rotated at 3 RPM and equivalent to 8.7 10 to the power minus 3 radian, that is 8.7 millirad per second. And then we get to see beautiful silicon dots. Okay. The motivation was if we could reduce the dot to light emitting regime in quantum confined regime, but in spite of a lot of attempts, lot of efforts, whatever you can say, we couldn't go down below 19 nanometers per cell. Maybe some other things tried at the time because of time restriction for thermal physics work, we could not do so. And this work actually came up in collaboration with Professor Mark Pardee from Boulder. And this is also the parametric phase diagram with no rotation and with subsequent rotation. Okay? So many interesting things can evolve. That's what I am trying to share with you and trying to take you through this tour guide kind of situation. Now, recent development in terms of studies in low energy regime, you see for 1 kV argon induced pattern formation, this Professor Michael Aziz from Harvard, they had first talked about the combination of, they told that there is no role of sputter erosion at all. It's all about mass redistribution. So Cutter-Wisniewski theory through the help of Cutter function kind of formalism, they tried to explain this in, that was PhD work of Sharbel Madi, and it was published in PRL. And indeed, later on in the next year, they realized that it was not devoid of impurity, silicon impurity, and they published a subsequent paper in 2012 Applied Surface Science, correcting their situation. But still, this gave a first opportunity to calculate these sputter coefficient and all, and try to see through simulation studies that where these patterns formation could be realistic. And for them it was 47 degree which was the critical angle. As I told you, several people have seen at several angles. Some people observed at 45 degrees, some people at 53 degree, and we did see it for 51 degree. Ion sources are different, setups are different, exact experimental conditions are different. Partial pressure that we use during the experimentations are exactly not same, cannot be the same, and so on and so forth. Subsequently, Mike published another work for the PhD student of his student Jay Parkinson, and he had shown pattern formation in germanium. Remember, with similar energy of argon ions doesn't lead to any pattern formation for germanium. However, using 250 and 500 dB krypton, Jay Parkinson had shown that yes, he could generate patterns. And however, results were not explained in terms of any theoretical framework. They just had built up this parametric phase diagram, and this paper was published in JVST in 2013, JVST-A. Subsequently, the group from Leipzig, IUM, the famous Dr. Frank Frost group, they had then by the time corrected their impurity related problems. They were actually the most affected people in terms of generating impurity induced patterns without realizing much. And although they had initiated wonderful works, subsequently people learned a lot, but at a much later stage it was realized that those were impurity induced. Later on they corrected those things and they worked on categorical impurity induced patterning as well, compared with several results and so on. And Teichmann, he actually showed that using xenon ions, they could see that pattern formation was a reality in this angular window with several ion energies for germanium. So experimentally, ripples were evolving at 70 degree incident angle. Now, Professor Hofsaess and his co-workers did show that through SDTrimSP simulation of the thing, that 10 kb xenon on carbon, amorphous carbon, and 200 dB to 10 kb rather, that both erosion and redistribution would be required to explain observed angular window pattern of synergy between erosive and redistributive effects in low energy regimes for nanoscale pattern formation. So this is another example of pattern formation on SiO2, single crystal, as well as thermally grown amorphous SiO2. We wanted to check on both, but for expected reason that these high kind of fluents, anyway, the single crystalline silicon dioxide substrate also underwent amorphization very fast. All the way similar patterns evolved. And this work was done at very initial stage of my next other student, Dr. Mohit Kumar, who actually worked on different other aspects. But we worked on this SiO2 problem extensively in collaboration with Professor Hofsaess, and we did conclude that here also the synergetic effect between sputter erosion and mass redistribution regime had to be invoked to explain this. Again, the parametric phase diagram shows that beyond 39 degree or so pattern formation takes place or should take place. We did see. And then it was proactive up to 73 degree or so, 72 degree or so, if I remember correctly, or rather 70 degree. So in between 40 to 70 degree unstable surface were there. Different patterns were formed depending on the linear regime or non-linear regime, practically getting dictated by low fluence or high fluence regimes. Okay, and RMS roughness also was high within the unstable range. Okay, obvious. That's how we see unstable surfaces or instability to give rise to pattern formation. Now, this was the SDTrimSP simulation, and even the important thing is that you see here what we have shown is the ion energy dependence in terms of versus angular window. That means the variation in angle of incidence of argon ions. And here we did see that critical angle for pattern formation actually remained unaltered. That was 39 degree, more or less, for different ion energies for the same ion fluence. Here it is 500 dB, here it is 1000 dB. Okay. So simulated critical angle was 39° and ripple rotation would appear at 66°, and that's why precisely within a couple of degrees we always see it. Then question is, I asked a question. Do we see nearly similar kind of or any similarity can one expect in terms of pattern formation for low and intermediate energies? Intermediate energies means tens of keV of ions to hundreds of keV. So in doing so, we did see that yes, the ripple patterns do evolve on silicon, germanium, SiO2 as well, using 100 keV or 30 keV, 60 keV, etc. kind of argon or krypton or xenon kind of ion species. And energy dependent wavelength was also obvious, and ripple patterns were specific angular window could be observed, although they were all different for different materials expected. By now we have seen. But the important message here is that's what we asked a question to ourselves. Do similar features evolve for low, means sub keV to tens of keV ion energy regime? And the answer is yes. Nearly similar features for sub keV to tens of keV energy do evolve. And you see here broken ripples are seen. These are very high fluences. And then it could be textured surfaces. My other PhD student, this is on germanium, but my other PhD student who actually worked on intermediate energy, Dr. Sandeep Garg, who is a faculty member at Patna University, he addressed this thing in his thesis in detail. And how useful the textured silicon surfaces could be or textured germanium surfaces could be, I will show you through some examples in a later part if time permits. So wavelength coarsening, that means enhancement in the ripple wavelength, transition to the ripple to sawtooth like structures, etc. at high fluences, all are seen for low energy ions. And so do we see for intermediate energy ions, that means tens of keV to hundreds of keV energy. Now, what was the need for us to try and stand in the nanopattern formation at tens of keV energy regime for silicon? There were some reports that I told Carter-Vizniakov started predicting, reporting. Then Professor Tapas Chini from Institute of Nuclear Physics, including his PhD student, Dr. Devi Prasad Datta, who was our postdoc at some point. We have done a lot of work with him as well in collaboration during his stay here, and we are still working together. Now, silicon at intermediate energies was a different kind of revelation. Okay, but there were little discrepancies here and there, so varied results. So a general understanding was necessary. Okay, a lot of work came. And so we tried to see, and these are statistical analysis that we performed through our obtained atomic force microscopy images, and you see very high fluences. These become textured surfaces on silicon surface at 60 degree incidence angle. This is a 3D AFM image, and here you see how asymmetric this becomes. So this is the clear signature of slowly getting transformed beyond 3 into 10 to the power 18 ions per square centimeter towards the nonlinear regime of pattern formation. Okay, and in the linear regime, this is like this, and then in the nonlinear regime, the roughness increases very drastically, and then it becomes almost saturated. But in the linear regime, you know, the ripple amplitude varied exponentially, okay, which is quite expected. That's not a big deal. And slope distribution from symmetric to asymmetric one that we see here, a separate paper was published in one of the IOP journals, surface topography and all. And then the linear regime could be well explained, already told to you. And then what we did is we constructed the parametric phase diagram with data obtained from Sandeep's experiments. All these experiments were carried out at using the old LEIBF, this ECR source-based facility. And then we took help of the literature data that Carter-Vizniakov, then the Rasendrov group, then Dr. Chini's group, and of course, Devi Datta's PhD thesis work, and also we could form this parametric phase diagram in terms of E theta variation. And this was a good summary which helped us to understand the underlying mechanisms for different patterns formed. But one thing was for sure true, that in this case, below 45 degrees for all meaningful results without impurity being involved, everybody in from different laboratories actually saw nothing below 45. Okay. Yes, please.
Sir, can we break for some time?
If you think so, but I would like to have the break only after 5 or 10 minutes because otherwise I'll be losing the thread. Let me take up to 5-10. I'll try to minimize as soon as possible. So maybe give me at least 5 minutes. Okay.
Okay, sir, sure.
So then what we need to know is why such kind of changes happen and how the patterns evolve. What is the role of even the incident ions? We think that in terms of such inert gas ions, everything is safe and sound. But then very interesting thing is when we undertake TEM studies, cross-sectional TEM studies, we get to see that a lot of argon bubble decoration in the near surface region. And particularly from the valley region towards the peak region, this is decorated more. And more we move towards the valley, the bubbles almost get disappeared. But you see, everything is amorphous, no problem. Contrast is that when we do micro-Raman studies, UV-Raman studies, we do UV-Raman studies in collaboration with National University of Singapore, and you don't get to know what is all happening about, because everything would show you that amorphous. But when you do TEM studies, we get to see this. This is very important information because the local atomic density will definitely be changing, and that means material density is going to change. And when you think of simulating and all, and without which it is difficult to predict the patterns or understand the underlying mechanism, etc., this is a very useful feedback. So higher thickness of amorphous layer in the front slope, that is also there. So it's not very uniform kind of amorphosity that is getting evolving within the near surface region, okay, till the projected range and all. And projected range also is quite nicely matching with 60-degree kind of incidence angle, etc. There is no issue. And as I told, SRIM does not take into account the erosion of target due to sputtering so accurately, not at all. Those are our illusions. TRIDYN, the dynamically can take care of many things, estimation of target erosion. However, let us not forget, it doesn't either give the vacancy or recoil distribution. So that's why, find out mu, we have to turn around only our focus towards SDTrimSP kind of simulation. We can take a break in the from here but I think 15 minutes will be little this thing because we started late and I have to finish by 12:45. Okay. Or
maybe you can have
by 1 o'clock. So I would request all of you to kindly manage this break by little up to limited to 5 minutes. And otherwise, problem is I lose the flow as well. Is it okay with all of us? Is 5 minutes break okay with all of us?
Yeah. Okay. So
yeah, thanks. Yeah, okay. Because mostly because I am, as I told, I have not kept much of a boundary to for the first lecture or second lecture. So minimal is the break. It will be easier. Although I myself also need a break to have some water. So we join in 5 minutes time from now, tentatively. Okay, please.
Hello.
Yes,
Som sir?
he has gone on break, so he is not sitting there.
Okay, so dear participants, I would like to tell you that we are monitoring your attendance. So kindly available online and try to interact with the speaker, because we have organized this so that it can benefit you if you want to pursue the research with ion beams. And it's a very good chance that you can actually gain some of the knowledge by the speakers who have worked in this field for many years. So try to interact. Whatever could be the uh, query or question coming in your mind regarding the talks, or it may be a silly question, but sometimes asking it makes a lot of difference, because that will trigger your brain, that will trigger your mind. So we expect that you have some active participation in the school, and try to be present in all the sessions, because the participation certificates will be delivered to you by seeing your attendance. Okay. So Ambusa, did he announce the break, or what do we have to do?
He said but just for 5 minutes. So I think he said he just wants 5 minutes break. So I think he will be back in couple of minutes.
I'm already back.
So this was just 5 minutes break. So
Somsa, we should we break, or you want to continue?
no,
As
Actually,
I told you, for
sir,
5 minutes and pardon.
okay, okay, sir.
Indra,
Yeah.
he had already gone. He is just coming back. So his 5 minutes break is over.
Acha,
So
your
for
break
me,
is over.
but still there is officially there is still 2-3 more minutes, so there is no problem. Still 2-3 minutes we can relax and then get started.
Actually, sir, the participants should take some water or something. So let us break for 5 minutes, and then we will be back by maybe say 55, 11:55, 56. Is it okay, Somsen?
No, for me, no problem. I mean, it all depends. If time is not enough, I will not be able to share enough things with the students. Otherwise, there is no problem. Because I have 1 o'clock, I have another meeting actually. Okay, so no problem. If they can take a break, no problem.
So participants, please take a 5 minutes break, quick break, and soothe yourself. Take some tea, water, and then we will again meet here at 11:56, 57. Okay. By the time Somsel will be ready with his presentation.
Dr. Ambus Tripathi, are you still there?
Yes, yes.
Sir, please start.
Yeah.
No, I just
Proceed,
thought,
sir.
can you see it, Ambuj? My presentation is visible?
Yeah, yeah, yeah. It is coming fine.
So it's not
Only
in the
thing is,
first
it is
screen.
not full screen just now. Earlier
That's
it was.
why, because I made
Yeah.
little bit smaller actually.
Yeah, yeah. Otherwise, it was coming fine.
Okay, okay.
And then, well made slides as usual. So.
Thank you, thank you. और बाकी the official break है, so we can chit chat a bit on unofficial things.
I think we can start now because as you said, if you have to leave by 1 o'clock, then I think you can start now. It is 55 anyway, 11:55.
Okay, so Indra, if you think it's okay, I can start along with the permission received from Bambuji. Okay.
Sure, sir. Please keep some time for the questions in the end.
Yeah, sure. And you see, as I was telling you about silicon, I mean, let me point out at this moment that I have not talked about yet about the possible mechanism of pattern formation with tens of keV ions for silicon. But then let me first try to take you through the results of germanium, etc., using the similar kind of ion energy. The reason I'm keeping it on a hold, putting it on a hold is, so for the mechanism is concerned, our goal again will be to test here whether we can think of exploring the pattern formation mechanism in this higher energy regime a little bit in a similar fashion, means where similar kind of mechanisms can explain all the patterns we see on different materials like silicon, germanium, etc. Now, germanium, it was the work of Dr. Datta. Again, we did it solely by utilizing IUAC facilities, and we get to see here through these parametric phase diagram constructed that with argon ions, pattern formation was not prominent below 60-degree incident angle. Everything was smooth and smooth. And little bit of pattern evolution was also seen for 75-degree. You see, this is the 60-degree argon, nothing, almost nothing comes. Okay, very faint signature of, through the FFT, very faint signature of pattern formation. Almost now zero, close to that. Beyond that, little bit, very poor. But with 100 kV krypton ions, we get to see very nice pattern formation. And pattern rotation also was possible to be seen, okay, using 100 kV krypton ions. You can see from this view graph of AFM image. So ripple rotation for krypton in case of germanium took place beyond theta is 80-degree, and for the angular window of 60 to 70-degree, we did see pattern formation for argon ions on germanium. Again, TEM studies, cross-sectional TEM studies were carried out, and for 516 ions per square centimeter at theta is 60-degree, we got to see this bubble formation again underneath the surface. But here, interesting thing is, unlike silicon, where we saw just around the peaks of these hillocks, we get to see these argon bubbles almost just underneath, very clear. But unlike that, in case of germanium, you see that there was around 8 nanometer, okay, amorphous germanium layer below which almost uniformly distributed argon bubbles were observed. So very interesting actually. Sorry, these are krypton bubbles. Okay, and then this is the depth of amorphous this thing. Of course, that is expectedly varying from valley to crest, the hillocks and all. But most interestingly, krypton bubbles were seen to be distributed over a depth of nearly 14 nanometer. and became very prominent through these stem head of PDX measurements during TEM. And of course, everything was amorphous, and crystalline peak of Raman studies was, as expected, around 300 nanometer in this. But interestingly, bubble formation does take place here also. Now, in this case, we try to see whether only Bayes theory could explain, that means only sputter erosion could explain the results, whether only Carter-Bizniakov theory, that means atomic redistribution, could explain, or both need to be taken care of. And interestingly, as I told, Bradley-Harper theory cannot explain the pattern formation, absence of patterns below 45 degree or 60 degree or whatever critical angle, because it predicts pattern formation to take place at every angle. Carter-Bizniakov doesn't predict, account for these smooth surface again occurring at very high incidence angle. So with all our rigorous simulation studies based on SDTrimSP code, we could show that a synergetic effect of erosion and mass redistribution can very nicely explain the pattern formation on germanium surface using these tens of keV ion energies. And this is a snapshot of how mu value is deduced from SDTrimSP. And this is the case of SiO2, again the work of Dr. Datta, and using 100 keV argon ions. So pattern formation here also was taking place from close to 38 degree or so, and the same formalism was operative. Although like the low energy SiO2 case, here also the theoretical formalism predict numerical simulation actually predicts using 45 degree, which is greater than the experimental one by 5 degrees or so. We don't understand yet completely, but this is that. I mean, it is true for SiO2 also. One possibility could be that as the compound material, preferential sputtering also takes place, and how it changes the material density locally, etc. Unless and until one determines dynamically, it's very difficult, and so one has to accept as close as possible we could reach. And then in the same framework, we could understand everything. So for pattern formation on silicon is concerned. So this is the beauty of this kind of numerical simulation. Now I will very quickly share with you one or two slides of what happens for pattern formation on germanium at elevated temperature. Again, I will come back to low energy this thing. This is an example. There is no high temperature data for pattern formation on any material surface using tens of keV ion energy, at least not to our knowledge. So I restrict it to 1 keV argon and impartation on germanium, which ions were normally incident, and you see so fascinating pattern, checkerboard pattern. Then this was the work of Stefan Fachko. This they explained everything in light of reverse epitaxy, and because of early soluble barrier formation, so this could happen, and at little bit different temperature, 250, this sample surface was completely smooth, and see to 60 degree checkerboard pattern started evolving, and 320 degrees centigrade the substrate temperature, this only became coarsened, and then you see crater-like objects, inverse pyramid. Okay, so very fascinating things. And 500 degrees centigrade again, the germanium surface becomes remains smooth. So all these details are given in this feasibility paper, and then subsequently they published in the paper in nanoscale also, where they did pattern formation at elevated temperatures on a couple of other substrates. These are our results. We are yet to publish. These all take place using our low energy ion beam setup at Bhubaneswar, and a bit of in collaboration with Dr. S.R. Bhattacharya at SINP, Kolkata, before their ion source completely got died up. And we are in the process of completing this work. And there are many interesting results, beautiful and well-like, grating-like structures evolved on gallium arsenide, gallium antimonide, indium phosphide, etc. already told, so I'm not getting into such detail further. And then you see, question is, can we generate such beautiful and highly ordered patterns in case of tens of keV ion energy? The question is, after a lot of trial and error, we realized that such low energy argon ions, etc., or krypton ions, we was not giving much new things in case of germanium. Okay. However, there was a paper of Professor Debabrata Ghosh in collaboration with Professor Bradley, where that was the thesis work of my past postdoc, Dr. Safiul Malik. They had shown that if you use a two-component system, then for a mono-elemental semiconductor target also you could generate so wonderfully ordered patterns, nanowell-like patterns, grating-like patterns. So it was necessary to have two components, and the second component in this case was gold. And what Dr. Bradley predicted through his simulation studies in this paper, okay, was you need to change the near surface composition. That was a mandate, okay, but they did not study any compositional analysis or anything. They just predicted that such a two-component system would likely be creating changes, making changes, significant changes in the near surface region, in terms of altering the composition. And after that, incidentally, Dr. Malik had joined my group, and we had taken up this study, and we did do a lot of materials characterization in terms of composition analysis through RBS, then XRD, and a couple of other studies as well, including cross-sectional TEM. And you see, as we increase for 26 kV in the gold ions, as we increase ion fluence, okay, so these were done with negative gold ions, okay, and using the SINP facility, and at theta is equal to 60 degree with increasing fluence, the ordering starts becoming better, okay, and in at 3 into 18 counts per square centimeter fluence, ordering becomes even mathematics. When you do extreme studies, we get to see that all these flowery nanostructures at the crests of these patterns, these beautiful patterns, okay, and they are rich with gold, and we overall an amorphous layer is seen, okay, underneath is the crystalline germanium substrate, and this is the groove in between two patterns, okay, these nanowell-like structures, these are the grooves. And here, the ridges, we get to see that they are rich with gold nanoparticles, germanium nanoparticles, as well as the mixed phase of gold germanium. So AU 0.6, G 0.4 alloy phase nanoparticles were also observed, and they were randomly distributed. And this was further confirmed through this elemental mapping through stem Haddock measurements in collaboration with Dr. Satpathy at SINP Kolkata. And the results were published here. So the hypothesis, the prediction of Dr. Bradley and Professor Goswami, Debabrata Ghosh's group was validated by us further. Okay, and we did do some RBS measurements as well to see the presence of all these things. And you see, you get a further indication when you carry out work function measurements and CFM measurements on these pattern surfaces. So at the ridges, okay, you get to see that the work function was higher. Okay, work function were higher, and that the groups, they were less. And this is the height profile as you draw such a line profile on the graphic image, and as well as work function image map. Okay, and so it was becoming at higher fluences, it was becoming more and more higher work function. That was quite obvious because gold content was increasing. Now onwards, I'll show you a few very quick examples of how these pattern substrates could be utilized for a good cause. This was a work done during the PhD thesis work of Dr. Mukesh Ranjan in collaboration with the Russian supervisor, Dr. Stefan Franco. They had shown that you generate silicon surface pattern using 500 eV argon ions and deposit silver at different in growth angles, okay, on rippled silicon substrate as well as a flat silicon substrate, and then also anneal it at 300 degrees centigrade. You clearly see a plasmonic shift, okay. And this is an anisotropic plasmonic shift because of the anisotropic surface morphology. So anisotropic surface morphology in terms of the ripple patterns can give rise to several change in surface property of different physical, super physical properties are concerned. One example here is the surface plasmonic property. Now, here there was no change when it was deposited on flat silicon, okay. So expectedly there was no change. And subsequently, we have done in collaboration with Mukesh. This was the part of PhD thesis work of my past student, Dr. Mahesh Saini, where we had also grown gold on such patterned silicon substrates by varying the growth angles, and we saw the good plasmonic shift have the most intense effect we could obtain at 70 degrees. That was a critical growth angle for gold. The details are available here. Since these is self-organized surface patterns, and over and above, again, self-assembled gold nanoparticles are getting organized. So the distance between these gold nanoparticles, as well as basically the interparticle gap, as well as diameter and the ripple wavelength, etc., everything decide that how this plasmonic property can be achieved. Okay. So this was a preliminary study. More works are underway, and we are trying to see if this could be useful for further studies in terms of drug delivery, etc. Because Mukesh is an expert on this in this direction. So now Mahesh is a postdoc with Mukesh, so we are thinking of having some collaborative studies together to understand more. Now, this is another old work where we had made use of silicon ripples created by 500 eV argon ions. We had deposited transparent conducting oxide thin film, aluminium 2% aluminium zinc oxide samples, both on pristine silicon and rippled silicon simultaneously. And everything was conformal in both cases, but beyond 15 nanometer, things were no more conformal in case of rippled silicon substrate. And expectedly here there was no change, everything isotropic. And we could show that because of this change in, for very low thickness deposited on this pattern silicon substrate, as low as 10 nanometer, there was a shift in the photoluminescence peak. Okay. The blue shift was observed, and so the results were published in JAP. So this was Tanmoy's thesis work. Apparently, from the grain size analysis of the height image, we were not very sure how small could be this thing. But then we were following this paper. We did take help of the phase images, FM phase images, and to have a better resolved grain sizes. So this could help us to see and correlate these results in terms of variation in thickness. And likewise, we had also deposited zinc tin oxide, the tint of zinc oxide also on these things, rippled silicon as well as faceted silicon. But then how do we get this faceted silicon? How does the transition takes place? That is very important. And so what happens is beyond a certain ion incidence angles, shadowing effect comes in picture. Okay. So if the ratio of the amplitude and the wavelength of the ripple they exceeds a certain threshold value, then the trough of this sinusoid will not be eroded further. but instead erosion will take place at the crests. And this in turn will give rise to a sawtooth-like waveform. This was a rather well-known fact for metal sputtering, and dates back to 1976 or so, but early works of Hofsaess from Dresden University. And this was very useful for our data to be explained in terms of shadowing and all. So very detailed work we did, and we saw that facets do get coarsened as we increase the influence. And this could, as prepared facets, we could show very efficiently that the tunable photoluminescence were yielding, and fluence dependence actually gave us the opportunity to tune the facet sizes at rather dimensions. And XPS analysis revealed the presence of SiO2, Si2O3, SiO3, and of native oxide as well as SiO bonds beside elemental silicon. And these are all well studied, and more details will be available. I'm just sharing that what kind of possibilities such pattern surfaces offer, right, from various tunable physical properties if we want to achieve. And another thing is the good light trapping. I mean, such faceted nanostructures, bigger of the facets, you see a tremendous reduction in light absorb optical reflectance. Okay, so basically the graded refractive index was attributed to observe such tunable anti-reflection property. As I told you, I mean, zinc tin oxide samples were also grown on both rippled silicon and faceted silicon to observe nearly similar kind of anti-reflection effects. I'm not going into detail. And aluminum doped thickness dependent aluminum doped zinc oxide, when deposited on these facets, show good junction properties, and fill factors actually were pretty good for 60 nanometer thick samples. These are all thesis work of Dr. Basu. And then the most fascinating work came out in terms of tracing the cold cathode electron emission properties, basically field emission property, and we could successfully show that size and aspect ratio of the silicon nanofacets when these increase with increasing ion fluence. So then the field emission property actually deteriorates. We see that actually the turn-on field is higher for higher ion exposure time. So this was equivalent to nearly 20,000 seconds, close to 3 into 10 to the power 18 ions per square centimeter, using 500 eV argon ions. And as we keep on reducing the ion fluence, that means for very short exposure time, okay, 6 times less, so we get to see much lower turn-on field, okay, less than 0.7 volt per micron. And this was at that time the lowest known turn-on field that could be achieved from any kind of silicon nanostructures, because silicon nanostructures, the conventionally the general notion is silicon nanostructures are no good for field emission studies, because field emission as it takes place, I mean, it's a common notion that field emission takes place from the tip like sharp objects, and for silicon that will be covered completely by native oxide. And so how can one observe? And that's why silicon based nanostructures were shown to have high this thing. And it's a fact of life that yes, they do get oxidized. But then what we saw is this oxidation is curvature dependent. So smaller were the facet, smaller facets created at lower ion exposure time. You see that these are all crystalline facets. Only near the peaks of these, the apex points of these facets, there was a little bit of native oxide. Lest everything was devoid of any oxide formation. On the other hand, the bigger facets, that this lowest frame corresponds to that. That means prepared at higher ion fluences, they have far more extended degree of native oxide formation. And this is curvature dependent. And this explains that why we get to see a uniform nearly 2 nanometer odd native oxide formed on a bulk silicon single crystal. So this could help us to understand the entire results. And so turn-on field was increasing with increasing size of silicon nanofacets. That was a take-home learning for us. and curvature dependent formation of native oxide, and the crystallographic orientation dependence, because these facets were all ensembles of different crystallographic orientation. Okay, so we could not reduce further, but then it gave an open question to us. So can even smaller facets lead to better turn on field? Okay, or even can it be, and second question was, can it be even lowered by decorating the smaller silicon nanofacets with metallic nanoparticles? Because metallic nanoparticles are well established to demonstrate the to bring down the turn on fields for many materials. So in the quest to answer these open questions, Moyes took it up in his studies after Tanmay finished, and we reduced the incidence angle, because we had the knowledge base from Dr. Basu's thesis work that 70 to 72, 73 degree odd angular window actually gives rise to this prominent shadowing effect during pattern formation, and ripples slowly get converted to or undergo a transformation to faceted structures. So Moyes took up both. So we reduced further the facet preparation angle, so that gave rise to even smaller facets compared to the ones observed here. And further, we went ahead to grow gold nanoparticles at several growth angles. And you take a note that these samples were simultaneously deposited on the ripple substrates also, which we had made use of for plasmonic property studies in collaboration with Dr. Ranjan. So 65, 70, 80, 85 degree, these four growth angles were utilized. And very nice self-assembled gold nanoparticles. Higher was the growth angle of gold. Further shadowing during the growth process prompted the gold nanoparticles to decorate near the apexes only of those facets. And lower was the growth angle for gold nanoparticles. The facets were getting more and more covered by gold nanoparticles. And we did RBS studies and all in collaboration with the NUS group. And we observed that coverage was more for 65 degree growth angle. Okay. And we subsequently annealed these samples also. So the upper frame is as prepared gold nanoparticles on as prepared silicon nanofacets. And here, as prepared silicon nanofacets as well as these samples were annealed simultaneously in vacuum for 300 degrees centigrade for 1 hour. And this is the result. A little bit of portioning of nanoparticles do take place that we saw. These are the TEM studies in collaboration with Dr. Satpathy from SINP. And again, we see that the facets were single crystalline in nature, of course. And you see up to this gold, there is no native oxide. The gold was sitting precisely on the single crystalline silicon nanofacets and the valley areas. However, it was completely not devoid of native oxide formation, as we have told. I mean, the degree has to reduce with the smaller curvature. Okay, and that's what we saw here. That gold nanoparticles were sitting in direct contact with the facets, and it was further confirmed with the STEM head-up EDX measurements. And we did extensive measurements of cold cathode electron emission. I mean, this paper will come in published form very soon. It's in proof stage, which was accepted in Journal Materials Chemistry C. So we did a lot of XPS studies in collaboration with Sanjeev. And before annealing and after annealing, overall, the work function shows this kind of variation with gold growth angle. And most importantly, for 70 degree growth angle, we see the optimal kind of an optimization of growth angle kind of situation, and we see that the highest field enhancement factor as well as the lowest turn on field could be achieved. So our mission was successful in terms of addressing these two open questions. Yes, smaller facets yield better result when we compared with as prepared facets in terms of their turn-on fields compared to the previous work. I mean, rather these SCSMI and applied surface science works. As a whole, the as prepared facets have showed reduced turn-on fields, and over and above, when we grew these self-organized gold nanoparticles on these facets, they reduced further. Okay, so we did some field emission finite element method based simulation. This was free. This is freely available Argos 2D code from the net, and this support our field strength. You can see that as after annealing, little bit of Ostwald ripening was taking place for gold nanoparticles, and they were all overall increasing in dimension, and so field strength was also enhancing, okay, for the similar dimension of the facets. And this is one example seen in collaboration with Dr. Fachko, that again now I am coming back to the examples of highly ordered gallium antimonide surfaces. Okay, and they had grown this MOSI multilayer to make these grating-like structures, which would be useful for X-ray mirrors. I mean, used as X-ray mirrors, and so did they do for chromium cobalt carbon multilayers and so on and so forth. You can see absolutely fascinating patterns, and gets simply transferred to the layers or to the over layers of these in the form of multilayers. Okay, some in situ studies are being done by Dilip at UGC DACSR also. They have a very nice setup which Professor Gupta set up during his regime in UGC DACSR Indore, where they can do direct in situ measurements, smoke measurements, while growing magnetic thin films on such pattern surfaces. Not these ordered, but they had done a lot of studies on pattern silicon surfaces in situ. So I didn't show it, but because they are kind of routine other measurements. This is a study where we are actually using our ECR ion source at Bhubaneswar. We have generated these 5 cubic krypton ion induced surface patterns on silicon, ripple patterns, and then deposited TiO2 thin film and did CFM measurements and all. We could see that resistive switching property, anisotropic resistive switching property to see on the ripple draws and the crests. So very interesting things, a part of thesis work of Mr. Sina. And so anisotropic surface morphology of silicon can, and in turn, which gets extended to TiO2, that was known by PLD at our place, shows up in the form of anisotropic resistive switching property. Okay, but interestingly, for TiO2 grown on pristine silicon surface, there was no anisotropic RS behavior. In fact, there was no resistive switching behavior which was changed and like that. Now, surface morphology also evolves using 60 kV gold ions on these PLD grown TiO2 films. Here, the flat silicon surfaces were taken after growth of 220 nanometer of TiO2 film by RF sputtering, and were taken to IUAC to get bombarded with 60 kV gold ions. Ibrani was kind enough to help us at the time. And here we had shown that ripple wavelength increases steadily with increasing ion fluence. And we did a lot of local probe measurements, including RBS, etc. And this was done in collaboration with Sunil. And then we did some XPS measurements also. So this shows very nice variation in work function. Again, because the ripple ridges are rich in gold. Okay, as we can see here, with increasing gold fluence, gold concentration of gold is increasing, and patterns are also getting pretty mature, coarsened, and Ti concentration near the surface is reducing, and so gold was getting decorated near the surface, and that's why the work function was increasing quite nicely and steadily. Okay. And we did do some anisotropic local surface current measurements through CFM1, and resistive switching also I have avoided showing here. This is a whole lot of work we did for our thesis. So beautiful anisotropic resistive switching property, and in turn anisotropic neuromorphic computing effect was also very nicely demonstrated by us. These are all in the communication stage. Now, very quickly, I would like to show in the remaining time that how these beautiful nanowire-like germanium patterns can be used in terms of application. Okay, so this is the pristine germanium's surface, which was subjected to 26 kV gold ions, and which give rise to such wonderfully or fascinating kind of nanowire-like patterns. Okay, and then we subsequently deposited cobalt thin film on these pattern substrates, and two different growth angle was utilized. One is north-zero, that is normally incident flux of cobalt, and another one is oblique angle growth, and goes beyond saying, I mean, very visibly we can see different microstructure to get evolved, and growth angle gave rise to some inclined kind of surface in between the grooves. It's very clear here, and so the very nice tunable anisotropic magnetic property. Okay, so magnetic hardening was observed for higher fluences, and these fluences are the fluences with which we created these patterns. Okay, I'm sorry, this is not resubmitted. This is very old view graph I collected. This was published in 2018 Nanotechnology, and the same paper. And you get to see that the higher the fluence to create such patterned germanium surfaces, they get more ordering and more ordered, and in turn gives rise to more magnetic hardening in the columns. Okay, and almost they get saturated beyond a certain amount. Okay, beyond 1 inch. But it's very interesting. And what we did is we took help of magnetic force measurement facility under variable field module. We applied a magnetic external magnetic field, as I talked about right in the beginning, using our AFM setup, and you get to see that along one direction. Okay, so when we place the sample parallel to the patterns, I mean magnetic field is applied parallel to the pattern, then beyond 1000 degrees centigrade we get to see that almost these magnetic domains are getting disappeared. But in one direction, when you apply perpendicular to this thing, it's difficult to see the spin reorientation is not yet complete here. So this is the beauty of such patterns, to visualize directly the evolution of anisotropic physical properties in terms of plasmonics, in terms of optical magnetic properties, etc. Such wonderful works have come up from the Rosendahl group also, in collaboration with Dr. Fachko and their director, Dr. Eugen Fassbender. And because Eugen has a very strong group, and they had done a huge amount of studies on MGO and other things, and they do a lot of MBE studies to grow these films and do in situ characterizations, and they do synchrotron radiation studies and all. So more important thing is that characterization has also to be frontline. So growth is one thing, creating pattern is one thing, and then further characterization I would repeatedly stress upon. The right kind of characterization tool and the right kind of condition has to be adopted to get the maximum benefit of such a system. You see wonderful growth of cobalt at different growth angles. So here 0 degree, 30 degree, 70 degree, etc. We had varied up to 80 degree, and so we kept on doing the magnetic measurements, and this is our latest work of Dr. Malik. And you see the magnetic anisotropy is very clear. So in one direction, you apply the magnetic field along the pattern direction and perpendicular to the pattern direction, you clearly see there is a change. Okay. Once again, details are given and very nice explanations as much as possible we have tried to put forward. Now a couple of properties of these tuned pattern surfaces in terms of intermediate energy cases, like tens of kV argon-induced pattern silicon surface. They when we talk about patterning at very high fluences, then textured surfaces start evolving, and you get to see That means those are nonlinear regimes. If we recall, we had shown at some point that beyond 318, it starts becoming nonlinear. And then along the pattern direction and across the pattern direction, we get to see there is, variation in the contact angles. Okay, and this is the roughness, subsequent roughness values. So a little bit of changes are there, and we attributed all these results to the local variation in the atomic density, etc., due to the incorporation of argon bubbles. Okay, and also the local slopes created due to patterning. And this is the work of Dr. Datta when we create such textured germanium surfaces. Okay, using 100 kV krypton ions, we can see very nicely that optical reflectance goes down drastically over a real broad band, starting from 300 to 3000. And you can see this red plot, that is theta is equal to 60 degrees, 3 into 10 to the power 18 ions per square centimeter fluence. We can generate such beautifully textured surfaces, which yields so much reduced, all the way better than black germanium kind of optical reflectance. So this is our latest work, and I would like to now conclude. Simple conclusions. Low and medium energy ions, starting from sub keV to tens of keV ions, irradiation can be used to modify and pattern surfaces at nanoscale. And these periodic patterns can be used as templates for thin film deposition, and as a whole, these pattern surfaces itself can show a lot of fascinating properties. And further interesting tunability can be achieved if we grow suitably chosen materials in the form of thin films and nanoparticles on these pattern substrates. So morphology dependent properties will be expected, and anisotropic properties are expected to be observed in terms of optical, magnetic, plasmonic. And very importantly, we could understand on large number of systems the pattern formation under the similar framework of contributions coming together from sputter erosion as well as atomic mass redistribution due to ion bombardment in terms of elemental semiconductor and compounds are concerned. In fact, I didn't share here. There was very nice results of Sandeep, which are unpublished, which he did during his stay in collaboration with Dr. Asakar and Dr. Kanjilal. That in even alumina also, alumina single crystals also can generate such wonderful patterns. He did a lot of studies, but those are unpublished somehow. So there also we did simulation studies for him, and it matches exactly with single crystal alumina substrate. But situation was a little different for some polycrystalline films that he grew in the collaboration with the process. Their pattern formation was not prominent. So it is very important that what kind of materials we handle and how we handle and what kind of microstructures we generate. And that finally leads to the pattern formation. And very interestingly, at the end of the day, that more industry-friendly things in the wafer scale is already established. If we can do patterning at high, greatly elevated temperature for these compound semiconductors, then we can do. They can be useful for growing solar cells, etc. 3-5 solar cells, which yield actually very high efficiency. You can do extra mirror publications and many other things. We are also in the process of growing some bimetallic nanoparticles for magnetoplasmonic studies. And then cancer research for in terms of drug delivery, etc. Horizon is really there. Scope is terrific. One has to understand that what kind of materials will be useful, because now the initial understanding has been established through the hard work of hundreds of researchers throughout the world. And at the same time, I would like to thank all my collaborators who had been really hardworking. So for my PhD students and postdocs are concerned, they did more than wonderful job in a very short span of time. And senior collaborators like Dr. Bhattacharya, Dr. Kanjilal, our good friend Rodolfo, and Professor Hofsaess and Mark, they all had contributed to a large extent from which we learned a lot. And we see that good research is coming up. And these do offer a lot of probabilities in the future. Thank you very much for your kind attention.
Thank you very much, sir, for such a wonderful, vast display of your results and from the patterning. It
You
was
are welcome.
indeed a pleasure. And now I would like to request the students to ask few questions or queries if they have from your talk, or if they want to clear some doubts. Yes, students, please ask some questions, or you can write in the chat box.
You all are free to knock me on my email address, which is available also anytime you feel like. I mean, you are most welcome.
Okay, sir, can I ask one question?
Yes, please.
Actually, once you showed some sputtering results where the film thickness is getting means it is decreasing tremendously from maybe 120 to say 60 or 40. So how you measured this? How much thickness it has remained now? And what causes so much of sputtering in low
Which
energy?
system, Indra, do you remember? I'm just forgetting.
I think after germanium you showed some results. There was a table, sir, in which you have written that after sputtering the thickness has reduced.
Let me just try to find out.
It's okay, sir. Otherwise, I will also ask you in email.
Yeah, I mean, it would be nice to hit back there.
No
but
problem, because so many slides
forgetting
are
that which
there.
one exactly.
Yeah. Actually, I did not note down the slide number, so it's okay. I will drop a query on your email.
Please feel free. Okay.
Okay, so please, thank you very much from all of us here from IBMS school for inviting our invitation to deliver such wonderful lecture in a very short period, short notice. And we look forward to encouraging more students like this in the regular series of our school, sir. Thanks a lot.
You are welcome, Indra. And thanks to all of you. And all the students, you once again are free to knock me on my mailbox. Okay. Thank you very much. Have a wonderful day. And I will catch you up by 2 o'clock during Professor Hofsaess' talk. Okay?
Yes, sir, please.
See you all. Yeah. Bye, Ambuj.
So, Ambuj, sir, you want to add something, or?
Thank you, sir.
Are Foreign sir, thank you.
Hello, sir. Hello.
Ambuj Mishra, you want to say something? You have some question?
Yes, sir.
Raise your voice,
I don't have any
volume.
question. I just want to talk to T-Som sir. T-Som sir, good morning. I just I just want to tell you, just want to draw your attention. I have also done some cross-sectional TEM of the Ripple. Some user sample is there. It's not mine sample. So I have also done some cross-sectional TEM.
Yeah.
I just it is not published yet.
So what is the question?
So we can also do the cross-sectional TEM here also.
Yeah, I know. I mean, you are doing wonderful job, Ambuj. My congratulations. I mean, I didn't talk to you for quite some time, but please help everybody in terms of. Yeah. Thank you. Thank you.
Thank you, sir.
As you know, I mean, this is very challenging to prepare good quality patterns, samples, so for TEM ready condition. But I'm sure with your increasing experience, you and Dr. Kabiraj are there, so will be very useful for users.
Yes,
thank
sir,
you.
yes. Thank you, sir.
So, sir, shall we break for lunch, or you want to add something?
No, I think this was our planned time also, so it is better we break for lunch. So it's
Yeah,
good.
thanks to
So
Somsa for finishing in time. It's
and
7:30.
so people can have lunch and come back by say 10 minutes before the time, so that 5
Yeah,
minutes,
please
10
try
minutes.
to log in by 1:50.
Yeah,
Okay,
if
No,
so
no, but
somebody
that
is logging out,
I may
otherwise
log in by 1:55 or 1:57, but I will be surely there. Okay.
yeah. Otherwise, people can just leave logged on. So you just make your mics and camera like most of them have off, and
Yeah,
then you can leave it logged on. So
that's
so
what
okay.
I.
see you at
Okay, see you then.
1:50. Okay.
Yeah.
Okay, bye.
Yeah.
Sir.
Thanks,
Bye.
Indra. Yeah, thanks, Anuj.
Okay.
Yeah.
Good morning, Dr. Hofsaess.
Good morning.
Yeah,
Oh.
I saw you had already logged in. So, how are
Yes,
you doing?
I'm fine. Yeah, welcome to everybody. It's nice.
Yeah.
It's nice to join the school once again.
Yeah, it's good we could organize. We were just wondering whether to do it or not. But then we finally decided to go ahead and do it. So it was great that we could do it and all of you could join. So
Hi, Hans.
Hi, Tabuato. Nice to
Oh,
hear you. And
yeah, absolutely. It's a sheer pleasure. How are you doing?
I'm fine, thank you. And how are you?
Oh, I'm also doing fine, fortunately. Thank you.
So you're connected from Bhubaneswar?
Yeah.
Ah, okay, fine.
In the morning, I was giving 2 sessions. Yeah.
So how do I upload my lecture?
all
It's
of
just-
us are doing from different places. So all of us are online. Even here in IUAC, we are doing from our office because we also have quite many cases on campus. So we are mostly doing these meetings and classes, whatever is online. So we also don't sit in the groups and try to avoid as many meetings and physical contact. So we are doing it all this in online mode.
Hans, suppose the situation is far better
Am I
now in
audible?
Germany?
Sorry?
Situation is far better now in terms of COVID in Germany?
It's recovering. We had a second wave, which is just ongoing, and maybe by the end of the year it will be a little bit better. In Göttingen, it's quite reasonable low, so that's okay.
That sounds good.
But still, public life is just more or less shut down.
Yeah.
Delhi, though, we keep on having every time it becomes less. They said it was first wave, then second wave. Now it is saying third wave. Even though India is still supposed to be in first wave,
Okay.
Delhi is already has two peaks. So now the third peak just went by a couple of weeks back. So Delhi still keeps on increasing.
Well, here it increased since it's getting colder and colder. And now we don't have snow, but the temperature is close to the freezing point. So it's not very comfortable outside.
Yeah, Delhi has this added problem of pollution. So they said that the dust particles carry this, maybe carrying these droplets for longer. So that seems to be making the situation more complicated. But just now it seems to be improving again. This, if it was a third wave, so cases for last 2 weeks are again decreasing gradually.
Yeah,
anyway,
Hans, for your just to brief him, I mean, Hans, for your presentation, you will be seeing a present now button, you know that, okay?
Yeah, so I will just see
on your
either...
screen, right below the there is a banner where you get to control your microphone and then video, etc. Then there is an option raise hand.
Yeah.
Then
So
turn
I will
on caption,
just...
and then present now, the rightmost.
Yes, so let me see.
Yeah. So before that, you can open your PowerPoint file on the screen so that it will be easier for you to control from here.
Yeah, it's showing now.
It's showing now. Let me see. Okay, so let me see,
This is a BCS slide. It says binary collision approximation.
Yes, yes. So I'm just see.
He's maybe trying for the full screen, sir.
So now it's full screen?
Yes, sir, it is now full screen.
Okay, I just have to see that the Google Meet page is also there. So otherwise, let me see.
So when you are in full screen mode, sir, you will be able to only see the current screen, which
Yes.
from which you want to toggle. Suppose if you want to share the slides, so PPT is on the top. If you want to go to the Google Meet, then you press the Alt tab button, and there many windows are open, so you can go to the Google Meet option.
How do I do this?
Alt tab. Alt and tab will help you to see how many windows are open on your computer. And the Google Meet one, if you click, that screen will come on your computer.
Yeah. So I've now you see the screen of my presentation, the first slide.
Still we can see your presentation screen, but for changing the slide and all, maybe you need to go to the PowerPoint screen again.
Yeah. Okay.
Or you can do it with the click of a mouse. Just try it with that.
So to see if there's any questions, so I have to just from time to time switch
from the
to...
chat box, probably we are asking the participants to write the question in the chat box. So you can see that here there is a chat box window. If you open it, you can see the messages.
Yeah, so I have to toggle between the presentation and the Google Meet screen.
Yeah, probably, yes. Whatever you feel comfortable in, it's up to you. So good afternoon, sir. I'm Indra here. Hope you remember. Indra from Material Science Group.
Yeah. Okay. So we are ready to start?
Let us wait for a couple of minutes, sir. More participants will be joining in 2-3 minutes.
Yes, okay.
Where is Som, sir?
Sorry?
Tapobrat Som, so he's supposed to introduce you. Where is he?
He has been there.
So we will wait for a couple of minutes so that other people may also join, then we will start.
Indra, Som had got logged out. He was trying to log in again. So has he come in? Or somebody has to allow him?
He has joined already.
Okay. Okay, I was unable to see. Yeah, now it is visible. Okay.
So should we start, Ambuj?
Yes, I think it is already 2 o'clock, so we can start now.
Okay.
Yeah, I think, but people are still, I see people are still logging in after lunch, so
maybe 2 minutes.
A couple of minutes.
2-3 minutes. Yeah. Yes.
2-3 minutes, and then you can start.
Yeah.
So I think you can start.
Yeah. Okay, good afternoon, all of you. It's a pleasure to have Professor Hans Hofsaess from Göttingen University. Professor Hans Hofsaess is a professor at Second Physics Institute at Göttingen since 1998, and he had taken care of many responsibilities in the university, including Dean of the Faculty of Physics, then Dean of Studies, Faculty of Physics, and then for the last 2 years he was taking care of responsibilities as a member of the Senate of the University of Göttingen. And Professor Hofsaess has been a kind of pillar in best physics of materials in terms of materials modification, characterization and all. And of late, he has been phenomenal in pursuing research on the very topic itself for him today, particularly SDTrimSP. This has given a lot of boosting for understanding and underlying mechanisms for many observed physics phenomena in the area of ion beam-induced pattern formation on material surfaces. And I am one of those lucky persons. So for my personal feeling goes to have association with him in few papers, and we learned a lot in terms of SDTrimSP from Hans. And I request you, Hans, to go ahead with your lecture. Thank you.
Yes, thank you very much, Tabobato, for the introduction, and welcome everybody. It's a big audience, I think 66 participants now. That's great, and I'm happy to give once again a lecture for the school, and I hope you are all well. Same for me, I'm healthy, and also outside it's a bit cold here in Göttingen, in the center of Germany. And okay, I will start with my lecture. It's on the simulation of ion beam irradiation of solids with software packages which are available essentially for free. That's the most popular is the SRIM program, and the derivative of this is the dynamic TRIM, transport of ranges of ions in matter, which is available at Research Center Rossendorf. And I was intensely using also a derivative of this program, which called SDTrimSP. I will explain later on what these letters SD and SP mean. So here are some web links where you can either download the software or ask for a free license and then download it and install it. So for this lecture now, you don't need to download or install any programs. I will just explain some of the features and some of the pitfalls and actually the basics, what is needed to understand what the programs do and what you can learn for ion-solid interaction. Okay, the outline of the talk is just an introduction, and so then we discuss a little bit elastic binary collisions. So we are essentially talking about binary collision between one individual projectile and one individual target atom. And one ingredient is also the electronic stopping, so the slowing down of ions due to interaction with electrons. And this is the Bethe or Bethe-Bloch formula, which we use there. And the electronic stopping, I will just briefly mention a new database which you can download for free, it's called DPass, where you have tables for electronic stopping. Then we discuss the nuclear stopping, which is essential for just calculating collision cascades and actually the details of the binary collision. And part of the SRIM package is the so-called magic formula. I will explain briefly what the magic formula is about. And then we have some scaling laws, and then I will give many examples for simulations with SRIM and SDTrim. So why do you need such simulation tools? If you do ion beam processing of materials or ion beam analysis of materials, then you require a quantitative knowledge of all aspects of ion-solid interaction, which, for example, ion implantation, you want to predict ion ranges, ion depth distributions, or defect production. In ion beam analysis, it's actually the depth scale which you're interested in also. That's the energy loss per path length of an incoming projectile. You need to know in detail the scattering kinematics, scattering cross-sections, also maybe some nuclear reaction cross-section and ionization cross-sections. And in sputtering, it's all about energy and momentum transfer from the projectile to surface near atoms. Ion track formation is essentially the issue of electron energy loss and the coupling of energetic electrons to lattice vibration, which is called electron-phonon interaction. In ion beam synthesis, it's the energy loss and also the momentum transfer between incoming ions and target atoms, which lead to sputtering or also film growth. And in surface pattern formation, that's what Tabubata mentioned, is you need to know details of sputtering. You need to know all the details of a collision cascade. So what happens to all the recoils involved in a collision between an incoming projectile and the target atoms. And so eventually you want to describe what happens similar to an incident meteorite on Earth which forms a crater, so you want to derive, let's say, the dimension, the symmetry, and the size and of a crater, also on an atomic scale on the surface. So there are many points where you actually need details of iron-solid interactions, and the way to gain these details in an easy and fast way is to use the so-called binary collision approximation. And there is a number of simulation programs. The most popular is SRIM, and there are 2 books essentially describing the programs without going too much into detail of the physics. One book is the cover is shown here. Then TRIDYN, you can look up the book, an article by Wolfhard Möller and Wolfgang Eckstein in Nuclear Instruments and Methods from 1984, which describes briefly what the dynamic version of the SRIM program does. This is purely a DOS program. SRIM can be installed under any version of Windows. And the SDTrimSP is developed at the Max Planck Institute for Plasma Physics. So that's IPP, Institute for Plasma Physics. And there's a report which can be downloaded which describes a little bit the program, and a very detailed description for this program with all physics background details is published in a book published by Springer, which is called Computation of Iron-Solid Interaction. Then you see, for example, if there is some formula used, then you say, go to this book, page 85 or so, and you find why this formula is used in this way. So it's actually really detailed manual to use this program. So if you want to learn a lot about the physics of iron-solid interactions and computer simulation of iron-solid interaction, I just recommend this book, which is also available as an electronic PDF version for download if you have the license from Springer. So what it's all about, it's about binary collisions. And a binary collisions, the binary means 2 components, and one is the incoming projectile, and the other component is one arbitrary chosen target atom. And this is seen here in this sketch, in this image. So the black dot here with mass m1, atomic number Z1, and energy E1 is the incoming projectile. And it's coming in at a certain angle of incidence, which we can define. So this is one of the few quantities which is well defined. Also the mass, the M1, Z1, and E1 is defined. And then we draw a box here, which is one atomic unit cell of your target material which you're looking at. And you just put one atom into this box. So this typically has the dimension or the size of a few angstroms in length, width, and height. And somewhere inside you put the target atom with mass M2 and atomic number C2. And then you're trying to calculate the collision between these. And the collision is essentially an elastic collision. So what you have to consider for an elastic collision is simply momentum conservation and energy conservation. So this is probably what you learn in some scattering experiments in one of the introductory lectures on physics. So it's the simplest case, elastic collision. So no inelastic losses like excitation of targets atom and so on. And what you're interested in is the path of the incoming projectile, which is this black arrow. So it will be scattered and it's leaving the scene with an exit angle theta to, let's say, the incoming direction, or if you know the incident angle alpha, you know the angle with respect to the surface normal for the outgoing ion. And the outgoing ion, of course, has the same mass m1 and the same atomic number c1, but it has a different energy. So in this elastic collision, some energy is transferred to the target atom. So the energy of the incoming projectile after the collision is different. It's lower than the incident energy. Okay. You do not know very much about the collision. For example, there are certain parameters which you do not know. One is the distance L from the actually surface of this box to the position where the atom actually is the target atom. It may be in the center of the box, but it may be at the end or more close to the beginning and so on. You do not know the impact parameter B, which can be some arbitrary value between 0, which is a central collision, and maybe some large impact parameter where the incoming projectile almost does not experience that there is a target atom and there's almost no scattering effect. And then you do not know this azimuthal angle phi, so it's the whole problem is axially symmetric with respect to this axis going to the target atom M2Z2, and you do not know which angle phi is this. So there are some unknown quantities, essentially 3 or 4, and some known quantities. Known quantities essentially the data of the incoming projectile. So how to deal with these unknown quantities, and then we come to the so-called Monte Carlo cycle, which actually Monte Carlo process was developed, I think, when the atomic bomb was developed to simulate certain processes in fission process, and it's just goes back to gambling. And so it's all about choosing random numbers. So what we want to do is to restrict this binary collision consisting of one target atom and one projectile, and describe this collision with the help of random numbers. And we choose random numbers which can take values linearly between 0 and 1. And there are many software tools and small programs and algorithms how to derive random numbers, which are actually random, accidentally chosen, and do not show any internal structure how you choose the number R between 0 and 1. So the first random number we have to choose is to decide which target atom we actually have. For example, if our target is silicon dioxide, we have 33% silicon and 67% oxygen. So with the probability 1/3, we should put in here a silicon atom, and with probability 2/3, we should put in an oxygen atom. So if we have random numbers between 0 and 1, so if the random number is between 0 and 0.33, then we say, okay, we put an a silicon atom, and if it's larger than 0.33, then we put a silicon atom. So in this way, we arbitrarily select the target atom according to the stoichiometry of our sample. What you see here from the random number 1, which we choose, and the fact that we are just discussing a binary collision, we have no other idea about the structure of our target. So it can be any composition consisting of many different target atoms, but there's no crystal structure, nothing. So we're just considering an amorphous structure of our target, and the only parameter which we have to define for our target is the size of this unit cell, and this essentially depends on the atomic density of our target. So this is the only parameter which we have to define. Otherwise, our target is amorphous. So with these binary collision approximations in the first place, and especially with these software packages, we can only describe ion-solid interaction for disordered or amorphous targets, or maybe liquids or gases. Nothing which has to do with crystal structure. Now, the second parameter which we have to choose is the impact parameter. And the impact parameter, we could think, okay, just we use a linear random number to describe the impact parameter, but an impact parameter with large B is more likely than one with small b, because the impact parameter occurs for all values of b in a ring, maybe like the ring shown here with a certain width. So the circumference of this ring is just increasing with r. So it's more likely to have a large impact parameter than a small one. And to take this into account, we have to define a maximum impact parameter and then multiply with a random number 2 and the square root of this. So this gives you the weighted random number to get an impact parameter b. It's weighted with the area of a ring with for all azimuthal angles phi and a certain impact parameter b. So in the book of Eckstein, I think around page 80 or 85, so there is a detailed description how to derive these random numbers for the different parameters. So this is the second random number. The third random number is only needed for actually the first collision. So if this surface, the right surface of the box, is the actual surface of our target, and then initially we do not know where this target atom which we have chosen is positioned. Is it actually in the center or close to the surface, or at the end somewhere on the other side of the box? And so the path length is given, the average path length is given by the atomic density multiplied by some cross-sectional area given by the maximum impact parameter. I will just describe what the Bmax actually should be. So this is the inverse value of this is some average path length. And typically it's a path length if we have one scattering event and then you're going to the next box, which you just put in on the left side of this box. So then the mean path length L is more or less the same for all following collisions. But for the first collisions, you use this length and multiply it with a random number. So it can be small, but the target atom is maybe close to the real surface, or it approaches the value L. So then you put your target atom here somewhere at the end. So this is a random number to describe actually the first collision. And for all following collisions, it's just a fixed value of a mean free flight path of the ion. And then, of course, we do not know the azimuthal angle phi, so we have to take any value between 0 and 2 pi, and therefore we choose a fourth random number describing the azimuthal angle. So we need to calculate 4 random numbers, and we have some known parameters for the incident projectile and for the target atom, and then we are able to calculate the collision. And so then all we need to know is what is the interaction potential, and if we can solve this trajectory, so then we know the first collision. And everything else what we do in the SRIM program or in the derived program TRIDYN and SDTrim is just bookkeeping. So you write down as after the first collision, the exit angle, the exit direction, the exit energy, maybe the transferred energy to the recoil, the direction where the recoil atom flies to, which energy it has, and then you proceed to the next binary collision and calculate it again with the help of random numbers, and then you get an output again with a new exit angle, new exit energy, new exit direction, and you just write down every data you get from each collision. So this is just bookkeeping. And at the end, if you do the whole process for many, many incident ions, you have enough statistics determined by these random parameters, and then you can plot some histograms for ion range, for energy losses, and whatever you have. So it's just one binary collision, essentially, and everything else is bookkeeping. Actually, if you have the target atom recoiled maybe in the direction to the upper right corner, so then you may consider this target atom as a new projectile entering a new unit cell box, and then you do a new type of scattering with this target atom, maybe silicon, and other target atoms, maybe oxygen, and then proceed. And then it's again just bookkeeping to follow up all the recoils. And in this way, you get all the details of the collision cascade, including the recoils. So this is actually the core part of the binary collision programs in SRIM and SDTrim and TRIDYN. So in all three programs, it's essentially the same algorithm which you use with the 4 random numbers and the binary collision. As a result, if you look for a screen which is obtained from SRIM simulation, this is the case, you define your projectile, phosphorus, you define the energy, 100 keV in this case. So it's some typical case for an N-type implantation into silicon. You choose silicon as a target. And you see here on the upper left corner that you have chosen phosphorus, the energy. And here what you see is the result after 254 incident projectiles. We have chosen a window with a depth of 300 nanometers, which is seen here. And here you see some details for your target. The density of silicon is 2.32 grams per cubic centimeter. The mass is 28, and it's chosen as a solid, not as a gas. So it's the density of a solid material. And there are some parameters which we will discuss later on, which are in the SRIM program set as default, but you should be careful choosing these parameters if you want to look for special features of the simulation. And then you get a display like this, and all the red curves show the path in an XY plane of the incidence phosphorus atoms. And the green, the many green dots are just recoil events where silicon atoms are recoiled. So you see all the green clusters are the silicon recoils, the collision cascade, and the red dots are, the red curves are the path of the phosphorus ion. So now you can do statistics. You have stored every data. You have done the bookkeeping in a perfect way. And then you can just look, make a statistics, a histogram of the end position of the phosphorus atoms. And then you see here in the upper right corner that the longitudinal range is 137 nanometers with a certain variation, 50 nanometers. There's a lateral distribution of 35 nanometers with a straggling of the lateral projected range is 35 with a straggling of 43, and you can also look for radial range. So radial is the distance from this one. So this is just statistics of the ion range which you get. And then you see in the center right some statistical data about the energy loss. So most of it is lost by ionization due to the incoming phosphorus ions, 32%, and 26% by the recoil. So more than 50% of the energy is lost by ionization, and this word ionization means electronic energy loss. So that's slowing down of the ions by collisions with electrons. And then a significant fraction, 40% roughly, is lost by energy transfer to the recoil atoms, which are the silicon atoms shown here as green dots. And these recoil atoms eventually lose their energy, and eventually this goes to vibration of silicon atom and heat. And this is described here as phonons. So you know in which way the energy is lost in the target. And then you also get a number, which is the sputtering yield. And you may get an impression that the incoming ion here from the right has a collision cascade that it may extend to the surface over here and over here. So there's a chance that some atoms will be pushed out of the surface, and this is called sputtering. So it's like atomic scale sandblasting, and you get a number 1.24 atoms, silicon atoms, are removed from the surface per incident phosphorus ion. And you also see that the average energy of these atoms which are removed from the surface is 214 electron volts, which is a quite high energy. So suppose you would evaporate something from the surface, thermal energies are, let's say, if you have a hot surface, up to 100 millielectrons volts. So here you get atoms removed from the surface, which are called often hyperthermal. So they have very high energy per atom or very high temperatures. So if you would get these energies from evaporation, you would have to go up to several 100,000 kelvins, which is not possible by just heating up your target. So to describe the binary collision approximation, what do we need to do is we need a software program which does the bookkeeping, and this is essentially what all these binary collision software programs do. The main job is bookkeeping, and the minor job is just to calculate this binary collision in a decent way. So to describe this binary collision, we need to know the interaction potentials. If we know the interaction potentials, we want to find the path of the projectile and also the recoil. And physically, this or mathematically, this means we have to describe a scattering integral, and we have to solve this integral, and then we get the scattering angle, the projectile energies, the direction of the outgoing particles, and so on. So this is actually what the programs do. They solve the scattering integral to get the outgoing angle, the outgoing energy, and so on. Then we have to include some electronic stopping. So while passing through this atomic unit cell, there are some electrons, like core electrons of the atom, but maybe also conduction electrons, and there's an interaction of the ions with the electrons, which do not actually change their direction, because electrons are so light ions, but they slow down the ions. So we have to include electronic stopping as, let's say, a fractional energy loss from entering the atomic unit cell to leaving the atomic unit cell. And this is just done by looking up electronic stopping tables in all these programs. And in most cases, these tables are based on experimental data where you have applied some analytical fitting function, and you use the fitting function to describe electronic stopping as function of energy. So that's not calculated in the program, so it just looks up a table and it's taken from experimental data. So then we may think of binding energies of the target atoms. So they may be bound by neighboring atoms, and it requires some threshold energy to recoil them. And then usually there is some exotic energy, which is called displacement energy. And if I go back to this one here, you see in the center, displacement energy for silicon 15 electron volt, lattice binding energy 2 electron volt. So this displacement energy is a little bit tricky to handle. I will discuss it during this lecture. And then there is a surface binding energy, which is needed to describe sputtering. It just describes how strongly bonded are atoms in this solid material, and how is there a threshold energy to let's say sublimate an atom from the surface and bring it as atom to somewhere infinity into the vacuum. And then, as I said, bookkeeping is very important to extract this distribution and average values and so on. If we compare the different programs, so the idea of the binary collision means we throw away any information about crystal structure. So all these programs treat amorphous structures, either solid amorphous or liquid or gaseous type. SRIM describes everything as static, which means you have an incident projectile, you follow up all the bookkeeping of the collisions and recoils, and when every recoil has lost its energy and the incident ion has lost its energy, then you start with a new ion, but you reset your target to the initial state. You do not take into account some changes in stoichiometry and losses due to sputtering of atoms from the surface. So that is meant by static. And the other versions of the TRIM program, TRIDYN and SDTrim, so they can take into account compositional changes, dynamic compositional changes by implantation or incorporation of projectile atoms, and either by growth of films. If you deposit more atoms than you actually remove, or you describe sputtering, so you remove atoms. So these dynamic changes can be taken into account, also stoichiometry changes. And TRIDYN and SDTrim can be, you can switch between the static mode and the dynamic mode. And the dynamic mode, of course, is much more useful in many simulations. The static mode is much faster. Okay, interaction potentials. We discuss in a moment which type of interaction potentials you use. For SRIM and TRIDYN, it's essentially fixed to some sort of standard potential. And in SDTrim, you can choose different interaction potentials. And essentially, since you get the source code, you could also include your own interaction potential if you feel comfortable enough to do this. Integration, so to solve this scattering integral, to get the path of the projectile and the recoil atom, is a little bit time consuming, and in the time when these software programs were developed in the 1980s, computation time was very expensive because the computers were relatively slow. Therefore, one has developed some speed up integration methods, which is the magic formula, which is not that accurate, but at least an order of magnitude faster than conventional integration methods which can be used in this SDTrim program. Okay, then there are some details about what you can do. In many programs, you can define some ion angular and energy distributions. For example, in SDTrim, you can actually define a Maxwell distribution of the incoming projectiles if you have, let's say, low energy thermal distributions of the incoming ions. With the dynamic programs, you can simulate film growth. You can handle multiple projectiles with these programs. So let's say you irradiate your film, let's say, not only with phosphorus, but also some other projectile, like some noble gas or something, or different energies. You can use a complex target composition in many of these programs, in particular SDTrim. And so then if you have finished the collision cascade and you have dissipated all the energy and all the atoms have come to rest, then you may start some diffusion model, which shows you what happens after this very fast collision process, that atoms may diffuse in the solid, and there are some models implemented in the SDTrim program. So there are several options which you can choose, and you get as output all the collision details, ion recoil depth profiles. So that is what you actually get from the bookkeeping. You get all the sputter details. You can ask how many atoms with which property, energy, emission angle, and so on is transmitted through a thin target. You get concentration profiles, and you get some detailed information about angular dependence of backscattered, forward scattered, transmitted, sputtered particles. So whatever information you want to extract from your data can be obtained if you extract the correct data from the wealth of data which you obtained from bookkeeping. Okay, the electronic stopping is typically described by the Bethe or Bethe-Bloch formula. The Bethe Bloch formula is relativistic, the Bethe is non-relativistic, and actually in most cases for ion-solid interaction, except maybe for thermal spike regions or so on, we are in a regime where we can actually use classical mechanics for the scattering. We do not need to take into account relativistic effects, and this is shown for some MeV helium in silicon energy loss. So there are tiny difference between the relativistic and the non-relativistic formula. What you see here is the classical 1 over energy dependent decrease of the electronic stopping electron volts per angstrom in this unit. And you see there is a slight difference between the electronic energy loss data used in the SRIM software. This is for 2008 version, but it's not very much different to 2013. And the difference here is the Bethe or Bethe-Bloch formula is a pure theoretical model of electronic stopping based on elastic collision with electrons and some partially elastic. So there is some let's say ionization thresholds for bound electrons involved, and the SRIM uses actually a fit to experimental data, and in the low energy regime there's some deviation between the theory and the experimental data. So the SRIM is not wrong, but it uses just a different data set. Or you may say the theoretical description of electronic energy loss does not really fit well the experimental data obtained here in this low energy region. Okay, so the Bethe-Bloch formula actually has a problem. It's not useful for the low energy part, therefore we have a cutoff, and this is due to the definition of this maximum impact parameter Bmax, which I also used in this definition of the random parameters. And this is simply when is the impact parameter large enough so that a certain atom appears as a neutral atom, or the transferred energy to electrons bound in an atom is so low that it cannot be ionized. And this is defines a typical impact parameter, B max, maximum impact parameter, which is typically of the order of an atomic radius, for example. And so the Bethe formula only describes the high energy regime, not the low energy regime. There are models which work for the low energy regime, which is a different physics approach or mathematics approach. And SRIM uses experimental data, so there is no actually theory involved. It's just fit to experimental data, and it covers the whole energy regime. But you see there is a significant difference at low energies. Just to give you an impression how many experimental data exist. So this is from the SRIM book, and you see some plots of energy loss data for different elements, aluminium and hydrogen and helium projectiles. And you see there are many, many experimental data measured during the last decades. And so there are some deviations for the individual measurements, sometimes strong deviations, but based on these data, you can derive these black curves as an analytical function to use to describe the electronic energy loss. So the database for the SRIM electronic energy loss is actually quite large, and it's mainly based on hydrogen and helium projectiles and energy losses in various materials. And all the other energy losses for heavier projectiles are calculated from these data using some scaling laws, where you know that the electronic energy loss has a certain dependence on atomic number of the projectile and so on. There's a recent theoretical database for electronic stopping actually calculated, provided by Peter Sigmund and Andreas Schinner. That's the 4 letters PASS. And dataset from Peter and Andreas Sigmund and Schinner is called DPASS. You can download this and you get a small program where you can just select your projectile, your target, some output units, and you get the electronic energy loss given in for energy in MeV, mega electron volts per unit mass of the projectile, and the electronic energy loss can be given in different unit, for example, electron volts per square, 10 to the 15 electron volts per square centimeter. Just some results if you compare with SRIM and with DPASS. So for the higher energy, 440 MeV helium and silicon, that's quite good agreement. And for the lower energies, you see, as we know from the theoretical Bethe formula, the energy loss obtained from DPASS theoretically is almost twice as large as what you obtain from SRIM. So there's a significant deviation, but this has to do with the fact that DPASS is just a theoretical, maybe more accurate calculation compared to this what you find in the Bethe formula. But SRIM is actually using experimental data, and at low energy there might be a difference. So the output of DPASS is just columns of numbers of the energy per unit mass and the stopping power in certain units. Now let's look for the nuclear stopping. And the nuclear stopping, or the collisions which we calculate in the binary collision approximation, is essentially calculating the interaction of projectile and target atom for a screened Coulomb potential. And the screening should take into account all the electrons actually bound to the projectile and all the electrons bound at the target atom. Typically, the projectile is singly charged as an incident ion. So maybe if it's helium, it has one helium plus, it has one electron left, and the target atoms, maybe silicon, has 14 electrons, is neutral. The situation changes if the helium ion enters the silicon material. So maybe the second electron will be stripped off and then it's doubly charged and it passes through a sea of electrons, and probably you have to calculate some average charge of the projectile, but nevertheless the ion will interact not only with the silicon nucleus with 14 positive charges, but it will be screened by the 14 electrons. Okay, so we have to describe screen potentials, and the easiest way to describe is the Thomas Fermi screening function. So that's the simplest case of density functional theory. So you describe the electrons of an atom as a free electron gas with a density of states d, and the highest energy level is described as some Fermi energy. And so if you know the density of states, you can calculate something like a charge density, and you use this charge density to solve the Poisson equation to get the interaction potential V of R. And so in this way you can, let's say, either in an iterative way or if it can be solved analytically, calculate the V of R as a screen potential, providing the correct charge density of electrons around an atom. So this has been done. I can just go through this very briefly. You actually find the screen potential, and it's the Coulomb potential, which we have here with a 1/r dependence and the atomic number of the target atom with a screening function. And the screening function is actually in the Thomas Fermi model some sum of polynomials which you have here, and x is a parameter which is the distance from the atom divided by some screening characteristic, screening length. And actually this Thomas Fermi screening length is used with many other screening potentials, which is of the order of, let's say, some Bohr radius, a little bit smaller than this. So roughly the screening length is of the order of an Bohr radius of an atom. And the screening leads to a stronger decrease of the potential, stronger than 1/r. So that's the idea of the screen potential, and the simplest approach is using the Thomas Fermi model and calculate the screen potential. There are other screening functions, and actually the Bohr has introduced the simplest one. It's just an exponential screening. So if you don't know what to do, actually you say, okay, well, electron cloud screens the nucleus by exponential screening. And then there are some more sophisticated screening functions, for example, some sum of exponential functions used in the Molière, some other numerical expression in the Linthart function or the Sommerfeld function. So there are different ways. It's often not quite clear how they are derived. It's just maybe some best guess or fitting to some maybe experimental data. And so to describe the scattering, we have to use a screen potential. And in the Thomas Fermi screening model and for maybe the other screening function, we have up to now only considered the electron cloud surrounded of the target atomic nucleus. But we may also have an electron cloud in the incoming projectile. So now we have to find something as an approximation which takes into account both electron clouds. So that's actually our binary collision looks like in reality. We once again use this Thomas Fermi screening length, typically 1 Bohr radius, and we have to define some effective charge. So rather than having here one atomic number C in the potential, we have to define something which contains the atomic number of the projectile and the target atom, and the screening function must take into account the effect of both electron clouds with some sort of effective charge. And there are several approximations also, or approaches, which look similar but which are slightly different. So this actually approximation for screened interatomic potentials, which take into account both electron clouds, and you see Bohr, Firsov, and Lintard have slightly different definitions of their screening lengths, describing an effective screening for 2 electron clouds. So this is an approach. Probably one can do some detailed molecular dynamics calculation and calculate the scattering, and from a limited number of data you probably can derive this mathematic expressions for the effective charges and the corresponding screening lengths, or it's just a best guess how to average these 2 electron clouds. And then there is the very popular CBL universal potential. This is goes back to Jim Ziegler, Biersack, and Littmark. Ziegler and Biersack developed the original TRIM program, and Ziegler distributed it through IBM, through the SRIM webpage, and developed this user's interface, this graphical user interface. And they used as a screening function a sum of 4 exponential functions and a screening length, which is actually defined by this Thomas Fermi screening length and some effective charge given by this expression. And the parameters used in the CBL potential screening function are shown here. So these are actually the parameters for this screening function, the parameters A and B. And of course, for x equals 0, then you just have the Coulomb potential, then the screening function should have the value 1. So the sum of the 4 parameters A should add up to 1. So this is one boundary condition. In the SDTrim program, there's another program which is actually a sum of 3 exponentials with different parameters, a different definition of the screening function, and this is called krypton-carbon potential. And the origin, okay, is the name. Maybe you have a carbon target and krypton ions coming in, and it turns out that this potential is very useful and accurate if you're considering low energy collisions, for example, if sputtering is involved. So there, the CBL potential in SRIM is not the best choice. The krypton-carbon is quite good. So what is the difference between these potentials? For high energy ions and small impact parameters and small values or close approaches to the nuclei, they are more or less the same. So that's the screening function, and all these screening functions are more or less the same here, but they differ for large impact parameters if the approach of the ion is not too close. So then you get strong deviations from Bohr to Thomas Fermi, and then it matters which potential you have to use, and in particular for low energies, it's essential which potential you choose. And here you just see a comparison of many of these potentials, krypton-carbon, and the U is the universal potential. So there are not too many differences, but it may become important for certain target ion combinations.
Excuse me, Hans.
Yes.
Maybe in 5 minutes time, we can go for a small break for 10-15 minutes.
Yes, of course. So we've started at,
So you can continue for 5 more minutes before we take.
Okay, that's great.
No?
So then I think if we've finished now, is it just one comparison of the nuclear
sure.
stopping
You stop at an
power?
appropriate time, no problem.
And maybe I just explain if we have this interaction integrals, you have to solve the scattering integral to get the path of the ions, and this can run with typical numerical integrations. And the magic formula is the following approximation. So typically the path of the projectile and the recoil here shown in the center of mass system are some parabolic or hyperbolic path, which is a little bit numerically difficult to handle. And a simple approximation is that you approximate it as a circular path, shown here as the dashed line. And if you do this, the simulation gets much faster. You can gain a factor of almost 1 order of magnitude in integration time. But of course, you have an approximation that it's not the correct path which you get. And anyway, you can calculate the scattering angle and the energy transfer between these. So that is what is called the magic formula. So you have this approximation that the path of the ion, at least at the central part, which where you do the integration, is approximated by a circular path rather than a hyperbolic path. So this is behind the magic formula, and this is used in the SRIM program, and the other programs typically use a more precise, typical numerical integration method. Okay, then maybe we are just through with the basics behind the software programs, and then the next part of the lecture will be some applications, what can be done with this simulation. So then I suggest we will have a break.
Okay, thank you, Hans. So now it's 3 minutes past 3 o'clock. So maybe we start again at 3:15. I think it should be okay for all the participants. Please try to come back before that. Thank you.
Oh, okay.
Yeah.
So as we have been seeing in every break, so either people can just leave it logged in. So we prefer that because otherwise it takes time.
That's better.
Keep it logged on and wait for 10 minutes and join after 10 minutes.
Yeah. Whoever wants to reduce the effort.
Yeah.
Dr. Kabiraj, how are you?
I think he's taking break, Dr. Sir.
Looks like solid break. Or maybe Ambuj, if you agree, then it's hard break.
Yeah.
Actually, there is no tea, so sometimes it looks like that.
I can give this.
I think this is empty.
So you are really making it formal physical conference like.
Sorry?
You are making it giving a feel of real physical conference, like, you know, the organizers would put on some slides on display and like that, you know. Not a bad idea.
Yeah, as far as possible, we want to keep it as we would have done it here. So
yeah. No, but actually one good part, Hans, I think you will also agree, you made a mention also about the number. You know, it always gives a good feel when you speak in any format, anywhere. When you get to see that many people are spending their time to listen to the discussions, you know. So this one good part is all online meetings, seeing that there is no gap of participants, you know, that really makes you feel happy. In physical conferences, often it gets very thinner sometimes, you know.
Yeah, okay. Here it's a big audience, and I know from the lectures which I give for my students here in Göttingen, also using some video conferences by Zoom or BBB. So they log in, and often through their phone or their smartphone, and you know they are logged in, but you don't know if they are actually listening. So you can be logged in, the microphone is switched off, and then when the lecture is off and you ask for questions, you get no response. And if you say, okay, thanks for listening, and you log off, so they do some of them just do something else. So they log in and maybe do something else. So that's a bit.
That's a reality, true.
So now, if someone asks questions, so then it's clear. So sometimes maybe one has to stop and ask questions to get a feedback. At least to ask, can you hear me? Or to say something.
Hi, Jeroen, how are you?
Yes, I'm fine. I actually wanted to say something about Hans's remark. I just had a similar. I also had lectures and. Do the students react? So what I did in my lectures is very small component, organize a very small quiz at the end of the lecture, asking very simple questions about the lecture, just to see whether they paid any attention. And since I give them marks for it, then they pay more attention. Seems to work.
Last week, some 10 days back, we had another school that was a small one. This 2-day on this ECR source. In that we did this exercise. Here actually number is too much, so I didn't want to do it because of bandwidth issue may come. There the number was smaller, so we asked in between people to everybody to switch on their video so that we know that people are there or not. So
well, I just used an online quiz type of platform, so they can just with their phone log into this quiz and then just ask some very simple questions. There's multiple choice questions. It's quite exciting, actually, I think. Normally I did it always during my lectures, but I don't give marks for it. But now because of the lockdown, and I want to see what happens, and because how do you do exams in this case? So I even give a little bit of marks for it at the moment.
Yeah, probably this will also evolve naturally if it continues for so long. Many tricks at many places in their own ways probably will be devised, such that say after all, putting effort for the students and all the participants, younger participants, if they are not sitting, it becomes as good as sometimes the physical meetings. But in the classroom, there is no way. I mean, when the teacher is there, the students have to be there. I mean, whoever enters, they are there. So.
But already in the classroom, I instigated this quiz just to see how they feel about it. Just at that point, I made it free, but just to see how they pick up the lecture.
Here the physical fear of the professor is not there.
Of course, I mean, but on the phone, it's anonymous, so people that's the nice thing. Answering this type of questions.
Right.
Anyhow.
About this quiz thing you mentioned, I have seen another school in which this teacher is doing. This is one of the schools where the teacher is doing these quizzes, and I saw one of this students. They have this WhatsApp group, and whatever question is saying, that is being flashed on that. And everybody is answering, and then everybody has this answer. So,
yeah, but then everybody might, because I don't give them. Depends how much time you can give. You can limit the time, of course.
Yeah.
See how they. Anyhow, I didn't have the impression they were talking to each other,
But now a lot of this, since you mentioned about this exams, now a lot of these softwares are there. And recently there are some of this major entrance exams in India. It is very difficult to get admission in many of these professional courses, and there is very tough competition. So some of them are doing this written test online, and where you have all this AI softwares. So you are supposed to do it on this computer screen, and if you are looking or trying to talk or trying to open any other window, so it detects it. So this proper entrance exams are now happening on this using AI.
Yeah, but if you have your phone next to your PC, you can. I mean, nobody can see you watch your phone.
No, but
you don't see I watch my phone now.
No.
How can you know?
This is what AI does. If your eye movement. If your eye is moving with more than a certain angle, it detects it and it warns you.
But if you want to write down things, I mean, to calculate something, how can you say it's not allowed?
There was now this software, this MNIT University, one of this private university in Delhi, this NCR region. They had, I saw in their thing, so they have this proper exams happening, and they say it is quite accurate. I don't know how successful this is, and one of these major entrance exams also happened using that, and they say ki it is foolproof. I don't know if there are any.
But if I'm a bad student, Amboj, if I'm a bad student, my only job will be to look here and there, you know.
Because I saw this functioning, and it somewhat they say it is foolproof. I don't know. I was also expecting.
I don't see it, because if I put my phone on my screen, I divide my window in my PC in a section for my phone and a section to do the thing. I mean,
no.
Sure people can go around it.
On this software disables any other window at the time. When the exam starts, it freezes every other window, so you cannot run anything on that computer.
Yeah, but on phone. On phone.
No.
There are so many gadgets to fix your phone just by the side of your computer screen, you know.
Yeah, sorry.
Okay.
Well, Jeroen, good to see you after nearly a decade or so.
I mean, I'm very skeptical. That's why the quiz I put very little marks on it. But anyhow, that's.
Good. Okay, so I think
we shouldn't.
Now we can probably restart the presentation of Hans. Yeah, Hans, please.
Yes.
Yeah. And again, good to see that 71 people, including all of us, are there. So good.
That's great.
Yeah.
Okay, I hope all the 71 can see the presentation.
Yes,
And
sure.
there was one question by Inda, how to choose which screening functions to choose. Well, in most cases, you have no choice.
Just 1 minute, yeah. Ambuj, your presentation and
Sorry?
your presentation was coming, so now Hans's thing has to come. Yeah, now he's seen, but it's seen. So far I am concerned, I see only a small things.
Yeah.
Can you see the presentation?
So you can pin on Hofsaess sir's presentation, then it will be always there on your screen. You have
So
to
I
pin
can
it.
ask presentation.
No, okay, that's fine.
No, not you,
Okay.
sir. Not you.
Yeah,
Not
thank you, thank you.
The
Inda.
other people I am saying.
Yeah.
Hofsaess sir, you are fine. Yours is fine.
No,
Okay.
first, someone has to remove this break slide, no? Only then it can.
No, you go to the presentation by Hofsaess sir and pin it on your screen.
Yeah,
Pin option.
Correct. That's the correct thing to do.
Okay, so there was a question how to choose which screening functions to choose.
Yes, so when you were saying 4-5 screening functions are there,
Yes.
so which one is appropriate, where to choose?
So in most cases, you have no choice. And that is if you're using the SRIM program, it only uses this CBL universal potential and the screening function behind it. And this is some good choice if the ion energies are not too low, let's say typical for ion implantations or ion beam modification, but it may become difficult if it comes to sputtering. And so anyway, but SRIM is, as I will explain in a few moments, is not the choice to calculate sputtering. So there you are just fixed to this CBL universal potential. The same is for TRIDYN, which I think originally it was also the CBL, but I think now it should be the krypton carbon. And only with the SDTrim program you can select different potentials, or you can, even if you just modify the source code a bit, define your own potential if you feel capable to do this. And it turns out that in particular, if you are working at lower energies where sputtering, pattern formation, the krypton carbon potential is really a good choice, because you can keep track of low energy collisions with larger impact parameters.
So which software out of these uses that krypton carbon potential?
I think the TRIDYN uses it, and you can choose it in the SDTrim. With SRIM, you always stick to the CBL potential.
Okay, sir. So if we are using SRIM to calculate sputtering, how much deviation it will be having in terms of percentage?
There are sometimes significant deviation, but this has not really to do with the interaction potential, but which has to do with some other programming errors in the SRIM. So SRIM is, if you ask Jim Ziegler, so then he says SRIM was not designed to calculate sputtering, but it has the feature that it shows some sputtered atom, but sometimes it's not very reliable. So there are significant deviations with SRIM if you calculate sputtering. So you better switch to the TRIDYN or the SDTrimSP. Okay, so BCA simulation. So there are some other programs. There is one rudimentary version of the TRIDYN which can calculate binary collisions for crystals, but only for a few cubic crystals, which is also available from Rossendorf. And then there's also a TRIM version which was developed in Jena, where you can calculate interactions of ions going through some nanowires. So you have, let's say, a circular cross-section of a nanowire, and you can just pass ions through it and see what happens to this nanowires regarding sputtering on the whole surface of the wire and so on. And So these programs are comfortable, convenient, and really fast to calculate ion ranges. So that's not a problem with any of these program ion distributions. Sputtering, probably best with the SDTrimSP. Then you can do energy loss calculations. But okay, energy loss is electronic energy loss. And what you do, you just look up an analytical fit to the database of experimental data. So you can do energy loss calculations, but you take data from experimental data. You can estimate damage production and look for ion beam mixing if you go to these dynamic versions of TRIM, and you calculate energy and angular straggling. For example, if you're interested by passing ions through a thin foil and you want to know the energy distribution and the angular distribution of the ions leaving the foil from the back surface. But marked in red, there's a warning. Have in mind the approximation and in limitation of the codes, in particular that you always calculate with, except for the crystal TRIM, with amorphous or disordered solids, and beware of programming errors. So these programs, like every program, contain some programming errors, and some of them have been fixed and some not. Now, the point is, for example, for the SRIM program, Bierzak, who has written the core of the program, he's not anymore alive, and Jim Ziegler is retired, and there's actually nobody who can actually fix programming errors in the SRIM. So what they do is Jim Ziegler's son, he just maybe a little bit improves the graphical users interface, but with time, so there is since 2013 no new version of SRIM, and the existing programming errors are still there. The advantage is this SDTrim program is maintained by a group at the Max Planck Institute for Plasma Physics in Garching in northern Germany. That's Andreas Mutzke, for example. And if you write an email to him, so you get a license for free to use this program, and you get the source code, so you can look into a source code if you think there's a programming error and see if it's actually there. Then you can contact him, and he will, if it's necessary, fix some bugs in the program. But that's the way it is. So the warning, don't trust these programs, in particular SRIM, and just make some more calculations to verify that you actually calculate the things you want to know. Just make some lot of tests and so on. Okay, the advantage of SRIM that it's self-explaining regarding the user interface, and it uses some default parameters. You have a nice setup screen. You can select projectile and targets from a periodic table. You have a compound direct dictionary where you can have some complex compound like dry air or some polymers and so on. So that's very convenient to use. And you just click in some projectile, some energy, some target you want to have, define the thickness of the targets which you want to use, and then you just press the green button, save input, and run TRIM. And then it starts running TRIM, so you don't care about which potential you use, and many parameters are just set by default, which may become problematic in some cases. With a SRIM, you can distinguish or decide how accurate you want to have the calculation. So it's just, if you're only interested in ion ranges, you can select this. You can follow the bookkeeping of all recoils, then you have the full damage cascade. You can calculate with monolayer collision steps, which is essential if you want to calculate sputtering. And then there are special options if you want to calculate neutron cascades and so on. Or you have just ions with certain specific energy, angle, depths, and so on. So these are some options which you can choose. That's shown over here. And the typical, if you choose ion distribution and quick calculation of damage and define your projectile. Here we have just chosen hydrogen, and we have not yet just selected one target atom. And then the bookkeeping is you have to want to have access to your data which you obtain by bookkeeping, so you can save some output disk files, for example, all collision details. If you click this option, or you can get all the details of transmitted, of sputtered ions, and of the ion ranges. So whatever you want to do, just store this file. You get a huge text file, difficult to read, but it contains all the information about all collision details. Okay, now we have just chosen hydrogen as a projectile. We've chosen a target 50 micrometers, and the target is water. You see hydrogen, oxygen with stoichiometry 1 and 2, and the density is 1 grams per cubic centimeter with some correction factor, which is suggested by SRIM. So then you can do the simulation of protons in water. And then you get the trajectories, and you see there is a certain range of ions, roughly 37 micrometers. And you see most of the protons entering water have a fixed range, like alpha particles in air, if you watch in a bubble chamber. And this is very interesting. Water is a dummy sample for the human body, which is essentially water. So you can use SRIM also to estimate, let's say, ion irradiation procedures for example, treating cancer. So you can choose the ion energy, proton energies, and let's say the lateral and longitudinal distributions to get the most irradiation where the tumor is. So this is one interesting feature. So you use protons or light ions in a light matrix like water. So now you can do statistics. So we plot all the endpoints of these trajectories, and then we make a histogram, and then we see the ion ranges. And we see the ion range is 27 micrometers. The straggling is roughly 600 nanometers. So the range variation is smaller than 1 micrometer. And this is not exactly a Gaussian profile. Okay, the statistics is not very high, but there's also a deviation given by the higher moments of such a distribution in terms of skewness and kurtosis, which describes, let's say here, the flatness on top and maybe tails to the left and right. Typically for implantation, you have tails to the surface. So you get a histogram about the details of ion ranges and ion range distributions. And then you can look for the energy loss, which is again important if you use protons for tumor therapy. So the proton is coming in here from the right at the surface of the target, and the end of range is roughly 30 nanometers. And you see the highest electronic energy loss is here at the end of range. So there we create most of the damage in terms of ion electron collisions, and that's where you're damaging most the tumor. And the region at the surface is also damaged, but with a much smaller amount. So this maximum of the electronic damage is called Bragg peak. It has nothing to do with Bragg diffraction, but it's called Bragg peak. And so this is an important parameter if you want to use such simulations to in water dummies to calculate the energies required to irradiate a certain tumor which has a certain size somewhere in the depths underneath the surface. Okay, so then you get some average values regarding range. And you see that most of the energy is lost by ionization, which means electronic energy loss, 99%. That's a major fraction. So it's just a slowing down of the ions without significantly changing the direction. There are only few ions few ions out of 839, which have been calculated in the simulation, which have deflection angles a little bit larger. Most of it is just going straight and slowing down due to electronic interaction. So this is what you can see here. And then there is some value showing here with 27 vacancies per ion. And so you may ask, what does it mean in water, vacancies per ion? So this is just some artificial number which comes out of SRIM. And this has to do with this exotic displacement energy, which we see here, which is 10 eV for hydrogen and 28 eV for oxygen. So these are some arbitrary numbers suggested by the SRIM program, which are, to my opinion, not useful for the case of liquid water, because you do not know what is the vacancy defect in water. And the numbers are actually arbitrarily chosen and do not really apply for water. I will tell you in a moment why. Just to be careful with the SRIM program. So here you see we did a simple quick calculation of the ion ranges, and we neglect informations about sputtering. Therefore here we see no recoiled hydrogen oxygen going backwards. There are some simple programming bugs in the SRIM program. So they provide some nice features of 3D plots of distributions. For example, you can try to calculate 10 kV aluminum implanted into silicon, and you look for the recoil distribution. And so the recoils are distributed at a certain depth over here, which you see here. And this is the number of recoils. And if you look for the lateral distribution, it's relatively sharp. It looks like a shark fin, more or less, okay? And
there's some problem. People are not able to see. Is it possible to exit again and present?
Yes, let me see.
The screen is not visible for some people. So can you just exit out and again present?
No, it is visible here. So
YouTube also they are not able to see, it seems. The screening also.
So I now just select once again.
Yes. Present now. In chat box, many people have written they could not see. We are able to see, they are not able to see.
Yeah. So let me see.
Actually, just tell the people about this pinning thing. Are they doing it? Because
even in the YouTube, it seems the screening it is not coming properly.
Okay, so then I have to.
Yeah, you can present now again. It should work, I think.
Can you see it now?
No. Yes.
Yeah.
It's visible.
Okay, now you can see it?
Yeah.
Yes.
Okay, then I try to go to the full screen mode. Can you see this also?
Yes.
Yes. No problem.
Okay. So this is a SRIM simulation for 10 kV aluminum implantation into silicon. And you want to look for the ion and recoil distributions. And so what you see in the 2D plot, which you get, is so the yellow dots are or the orange dots are the silicon recoils. And it's a very large lateral distribution and also longitudinal. And then you have the 3D plots, which you can click on in SRIM somewhere on the lower left edge of the screen. And then you get this one. And essentially the recoil distribution here shown with the red line more or less represents what you see if you go here from the 2D screen from left to right. But it does not actually shows you this lateral distribution. It's extremely narrow and it looks like a shark fin. And the reason is simply a programming error. To plot this 3D distribution, SRIM uses the x coordinates of where the recoils have stopped. So this is here the x scale. But for the y and z coordinates, they use the start coordinates where the recoils have started. And this is much closer to the surface and much narrower. So therefore, the distribution is absolutely wrong. And it's just one of the programming errors which you see. You can create plots which have nothing to do with reality. So just be careful if you use these 3D plots. There are programming errors. And actually, I discussed this. I told Jim Ziegler years ago, and he didn't really understand what the error is. So it has not been corrected. So it's visible there. You do not get this shark fin profile for the aluminum recoils, for the recoils in silicon after aluminum implantation. It's just simply a wrong plot. So stick to the 2D plot and then it's fine. Before I come back to the SRIM, just look, if you decide to use the dynamic trim, it's a DOS program, and you have to write a small script file with some cryptic numbers in it to start the simulation. And this is an input file to calculate the irradiation of titanium nitride with 1 keV nitrogen ions incident at 20 degrees from the surface normal, and the total fluence is 5 × 10 to the 17. So there are some input parameters, and you see the red marked data show the titanium data, the green, the nitrogen, for example, atomic number 7, mass 14, for titanium, atomic number 22, mass 48, and this is the total fluence in units of 10 to the 15, and so then you have the substrate iron, which is here, and the backing, and then blue is something for the ions which you the ion which you choose. So it's a little bit cryptic. You have to use the manual to set up this script file and use it several times until you get familiar what parameters are entered in here, and then you can start the simulation, and it will take into account dynamic changes of the stoichiometry, so you can actually with nitrogen implantation into titanium nitride look for ion beam assisted deposition processes. So it's a little bit uncomfortable to use it and to set up these script files, but it works. The same is true for if you use the SDTrim program. And now I should explain what SD and SP means. Trim is transport and ranges of ions in matter. And S and D means static and dynamic. So you can choose whether you want to follow up compositional changes or not. So if you choose the dynamic way, so then it takes into account positional changes. And static is similar to SRIM. And this SP means that you can run it in the sequential mode, like typically on the PC on your laptop, or you can run it in a parallel mode. If you have the proper Fortran compiler, you can run it parallel on your 4 or 8 cores of your computer, or run it even in the environment of a computer cluster, which speeds up things quite a bit. And then you also, it's let's say a program which runs under Linux, and you have to compile it, and then you need a script file to run it. And this script file is a little bit easier because it has some more or less easy to understand description which parameter you have to put in. And so this is some part of the script file. For example, here you can choose iPot is an integer number 3, and then you choose the CBL potential. If you use another number, you have to look up the manual, and you can choose another interaction potential. And then here you use 20,000 projectiles, and there's some default number of 10 projectiles, and every 10 projectiles the program updates the composition of the of your target and takes into account stoichiometric changes. So every 10 projectiles is an approximation for, let's say, a small fluent step in maybe 5 × 10⁻¹² ions or so. So in total, you have, let's say, 2,000 fluent steps up to 5 × 10⁻16. And so then in this way, the program calculates stoichiometry changes. So we have chosen the Gauss-Legendre integration method. We define which type of surface binding energy we choose. This is one point which I will discuss in a moment. We have 6-degree incidence angle. The incidence energy is 500. So we can use several incident ion. We have defined silicon and oxygen and argon as an ion. We can extend this list to more ions and so on. So if we have set up our file, target thickness, some cutoff energies when the simulation is stopped, when energies have dissipated their whole energy and so on. So this is one setup file which you have to use, and then you can start the simulation. And you have some output options. Now this is a sketch of the computational flow chart of the program. So in the dynamic version, you collect target-specific data, make a target update, change composition, include sputtering, and then you go back and continue in a loop. And once you've finished with all your ions you've defined at the beginning, then you write down all the output files. So this is where you get your bookkeeping. So essentially, the core simulation is here, projectile and recoil loop. Here is the basic Monte Carlo loop. It's the integration of the scattering integral, binary collision, and you calculate the random numbers. Everything else is bookkeeping, and eventually you have an output of your bookkeeping data. Okay, now there are two important energies which enter in this simulation. One is the surface binding energy, and it's simply what it says. It's the energy how a surface atom is bonded to the surface, and it describes the energy which is necessary to sublimate it and bring it into vacuum, into infinity. So it's the surface binding energy is nothing else like the sublimation enthalpy of an element. So this is the thermodynamic quantity which can be calculated, and it's tabulated. And here we use the sublimation enthalpy for transition of the most stable compound in into a diluted atomic gas. That's atomization enthalpy. For example, for oxygen, it's just the dissociation of oxygen molecule into 2 oxygen atoms, or the dissociation of graphite into a carbon gas as an ideal gas distributed somewhere into infinity in vacuum. And for silicon, it's just if you vaporize silicon into a silicon gas, and this atomization enthalpy is usually something like 450 kilojoule per mole for silicon. And from that, you can calculate it into electron volts per mole, and then you divide it by the Avogadro number, and then you get 4.7 electron volts per atom. So to remove a silicon atom from a solid surface, you need to transfer at least 4.7 electron volts to a recoil. We will just briefly look in detail what this actually means, how you transfer it. There are other enthalpies like the melting enthalpy, evaporation, and sublimation. So there are some different values which you can use. And so essentially we need something from the strongly bonded state to dissipation or sublimation into atomic species and separate them as an ideal gas into infinity. So let's assume we have some recoil collision, and one atom has received an energy and a momentum and is moving in the direction of this black arrow shown. So it will just leave the surface, which is here on x equals 0. Positive x is going into the solid. And so it will leave the surface. And now we ask for the velocity of the normal component, and then we calculate the kinetic energy of this atom going in this way, just using the normal velocity. So that's the energy fraction related to the normal velocity component. And then the programs assume if this energy component is larger than the surface binding energy, for silicon 4.7 eV, then it's removed from the atom. If not, then it remains at the atom and it will be reflected, and it maybe bounces back and forth the surface and eventually comes to rest. So this is the procedure how sputtering is taken into account. And so you need to calculate the sputtering in a correct way, have the correct velocities and momenta of the atoms leaving the surface. You have to calculate the correct vertical energy component of the kinetic energy, and then just make a decision if it's larger or smaller than the surface binding energy. And in this part of the calculations, SRIM has some severe programming errors, which is essentially the reason why SRIM is in many cases not accurate calculating sputtering. It gives you partially wrong sputter yields and definitely wrong angular distribution of the sputtered atoms. Okay, the TRIDYN suggests some average components or contributions to the surface binding energy if you have a component A, N, B, M with stoichiometry N and M. And this is questionable if you should use it or not. My opinion is just use the surface binding energies as I have defined it from the sublimation enthalpy of the individual component. Here it is assumed that an atom at the surface is bound in a component, but when the atom actually reaches the surface, it has been part of a collision and already has some significantly large kinetic energy. So it's not bound in some component A, N, B, M. It's just moving freely, and then you do not need these suggestions which is recommended for TRIDYN. It could lead, if you use these options, which you can also choose in the SDTrim, that your sputter yield is extremely low. For example, if you use titanium nitride, so the surface binding energy for titanium is quite high, or maybe for tantalum is quite high. And then if you have a high surface binding energy, it will reduce your sputtering yield because not many atoms can be released from the surface. So this is suggested, but I would suggest to use the surface enthalpy. And so this typically the programs SRIM and SDTrim, they have tables for all elements, and there are data like atomic number, mass, and so on. Also, you see here in the yellow bar 4.7 electron volt surface binding energy for silicon, which is just derived from the atomization enthalpy or sublimation enthalpy. Okay, so this is the first energy. The second energy is difficult. It's the displacement energy. So here I have shown schematically a crystal lattice of green atoms, and a projectile is coming in here from this arrow, and recoils is scattered, so the projectile goes into this direction and is then eventually this red atom. And the original green atom is recoiled into some direction and just moves through the lattice and collides with other atoms, and eventually loses the energy and comes to rest at this position in between the position of the regular lattice atoms. So this is an interstitial, and this is a vacancy defect. So vacancy defect is only defined in a crystalline material. It's the question, what is a vacancy in an amorphous material? It would be maybe some density fluctuation, but not really a vacancy, except you have some sort of dangling bonds. But typically an amorphous solid will rearrange so the vacancy the term vacancies does not really apply to amorphous materials. Now, if we remove an atom over here, so the lattice will be distorted and we have some stress or strain in this region over here. And we also remove some positive charges from the core charges over here and maybe also some electron charges. So there will be some residual Coulomb potential over here. And we will also have strain or stress over here. The lattice will probably expand and there will be an additional charge distribution over here. So these two spots, the vacancy and the interstitial defect, they may interact through their strain fields and also through their Coulomb field. So there may be a tendency of this whole system, the vacancy defect and the interstitial, to recombine. And if the distance between both is not too far away, so then they will recombine. So it actually depends on the recoil energy, that the recoil has a chance to get far away of the initial position so that it's a stable defect of a vacancy and an interstitial. And typically in the literature, so vacancy and interstitial pair, it's called a Frenkel defect. So the question is, for which energy transfer we will create stable Frenkel defects, vacancy interstitial pairs. And the only way to measure is if you use a single crystal, because then you only have the term vacancy defined and the term interstitial atom defined, and you use a well-defined projectile. And typically it's high energetic electrons, which you have from transmission electron microscopes. So you do an experiment in an electron transmission microscope, you irradiate your target, let's say a metal, at a certain temperature with energetic electrons, and to some extent these electrons induce some low energy recoil, which may be sufficient for creation of stable vacancy defect pairs. If the energy is too low, so they will recombine. So how to decide whether you have created stable Frenkel pairs? For metals, it's very simple. So you cool the metal down to low temperature and you measure the residual resistivity, the electrical resistivity. And when you start creating defects by electron irradiation, the residual resistivity increases. And there's a certain threshold. And if you calculate this or determine this threshold experimentally, you know, aha, there's a threshold for formation of stable vacancy interstitial pairs, and then the residual resistivity increases. So it's simply an experimental energy which you can only determine in an experimental way, maybe with the exception of very fancy molecular dynamics simulations. Okay. Why does one use such a displacement energy in the SRIM simulation, which deals with an amorphous material? So it's only defined in crystalline materials, so it will not apply for a SRIM simulation. You can derive this energy, the threshold energy, maybe from MD simulations, and you find some tabulated experimental data. All are obtained from electron microscopy. The energies depend on the temperature of the target, and it also depends on diffusion processes going on. So if you're not, in the general cases, if you're not in a single crystal, you can actually forget about this displacement energy and set it to a small value or even zero. The only reason to use this energy is if you want to stimulate ion implantation into semiconductors with SRIM, and you want to get an idea what is possibly the number of defects, vacancies created in an implantation process. And to do this, you have to assume a certain displacement energy, and then you get a number of vacancies per ion, and this is just a best guess of the damage you create if you implant into a single crystalline many other you see for copper, different orientations in copper crystal. You get a large variation of this displacement energy going up to 60 electron volt at very low temperatures, and maybe only 16 or 13 or 10 electron volts at high temperature. So it's a difficult energy. It's only defined and measured by experimental values, and better for many applications you can forget about it. So you don't need it if you want to implantation ranges, or if you want to calculate ion erosion. Okay, some examples, straggling and ranges. So SRIM uses just the experimental data and fitting function to experimental data for electronic energy loss, and then you follow up the collision cascade for, let's say, nitrogen ions into iron, and depending on the ion energy here in MeV, you get data over here and over here, or curve over here, the nitrogen ion range in iron. So you can get this roughly dependence from a data table from SRIM, which is called projected ranges it's called PRAL ranges, and straggling in ions. And you can also extract for electronic energy loss the tables from the DPAS database. But in most cases, you have to consider the nuclear energy loss. So you can run a SRIM simulation, and you get a range distribution for nitrogen in ions with 2 MeV and 8 MeV. So you get here 2.89 and 1.1 micrometer, and these are the two plots shown over here. So from the continuous curve, which you get from electronic and nuclear energy loss, you can get here two distinct values by doing a simulation at these two distinct ion energies, for example. Now, another example, if you want to study implantation into materials like silicon, it's the standard target, and you decide to do implantation in xenon. And then you do the simulation with SRIM, for example, and with a low fluence, and then you get, let's say, a distribution here, the depth scale, and here the intensity, the concentration in the log scale, given in 10 to the 21 per cubic centimeter. You see such a depth profile, which you would get from SRIM. But this is actually the case where you do not have modified the sample, but due to the implantation. With this energy, heavy ions and high energy, you have significant sputtering rate. So what you do with continuous implantation going to higher fluences, you just remove material from the surface. So your initial profile will eventually shift closer to the new surface. And if you take this into account with a dynamic simulation, so this is shown for the red, green, and blue dots, you get a completely different concentration profile. And this 0 always represents the new surface. So you continue to remove silicon's atom from the surface, and your dynamically implantation profile looks like this. With SRIM, you would actually calculate just the black curve, and your implantation profile would only show the situation for very low fluences, but not for a high fluence of, let's say, almost 10 to the 17 ions per square centimeter. So there you clearly see the advantage of a dynamic simulation, which includes stoichiometry changes by removal of atoms from the surface, and you get a more accurate and realistic implantation profile. So, for example, you implant rare earth isotope erbium into silicon. Maybe you want to have some luminescent material. The erbium, the rare earth atoms are mainly luminescent in an oxide surrounding. And if you implant the erbium into silicon, so the implantation looks like this. with a SRIM profile, you would get the black dots where you have no dynamic changes of your implantation profile. With a SDTrim profile, you take into account that you actually continuously remove silicon oxygen atom from the surface, and then eventually your implantation profile looks like this. It's completely different. So you see, higher dose implantation, it's necessary to include compositional changes of your material, including sputtering and incorporation of the impurity atom. And with the SDTrim, if you look after an implantation fluence of 10 to the 17, then you see in the larger depths you have just silicon oxide with the red concentration of oxygen, 33%, and 67% silicon and 67% oxygen. And in the surface region where you have implanted the erbium, so you have a significant concentration of erbium, which extends up to the surface, and then the oxygen, the silicon concentration is a little bit decreased, and also oxygen is a little bit decreased due to sputtering. So this is your real situation after implantation, and this is your real implantation profile. So this is something which you cannot calculate with the static version of SRIM. So you have to be aware of this limitation if you run the SRIM program. So your implantation profile may be completely different from what we have in reality. Another example, okay, 3-layer silicon and silicon dioxide, and you implant it with another rare earth isotopes, and after you've done the implantation, you just see the concentration of silicon, the green curve, the concentration of oxygen, the red curve, and the concentration distribution of the praseodymium in the depth scale up to 300 nanometers. So this is actually what you expect following the implantation, including incorporation of praseodymium and sputtering of silicon and silicon dioxide. Okay, so your silicon on silicon of an insulator layer is just smeared out, so the concentration of silicon is not actually just a rectangular function from 100% to 33% back to 100%. So it's some continuous function, the concentration distribution of silicon in your sample. Can only be done with a dynamic simulation and not with SRIM. Now let's go to sputtering, and that is question: how accurate is SRIM with sputtering? And so there are some experimental data where you can look at, for example, for SIMS measurement, 2 kV cesium coming in on silicon surface, incident angle of 60 degrees, and there one has measured the distribution of sputtered atoms for different incidence angle, and you see the sputtered atoms or the reflected cesium, the sputtered atoms are just emitted with a distribution around 30 degree in forward direction. So for 60 degree incident direction, the sputtered silicon atoms appear somewhere around 30 degree in forward direction. Okay, and the same is for germanium, and there essentially you get a distribution with close to the normal surface. And now you do it with SRIM and SDTrim. In both cases, accidentally, you get more or less the same sputter yield of 5.5. But you see, if you look for this distribution for where the sputtered atoms come from, so you're looking on top of the surface in the hemisphere, then you see the angular distribution you obtain for SRIM is much narrower, and it's centered to the normal direction, 0 degree. SRIM tells you all the ions are sputtered in a narrow region or along the surface normal. SDTrim actually shows you this forward sputtering at around 30 degrees. So this is the correct distribution. This is the completely wrong distribution. This is simply a programming error in SRIM. So the sputter yield is okay, but the angular distribution is completely wrong. Or significantly wrong. So this can be tested for some other situations where you have experimental data, let's say argon or nickel, There have been experimental data on sputter yield distribution, and it can be very well calculated with SRIM. I will flip through this and show you that there are some extreme deviation with the SRIM. 1 keV argon on silicon, and you're looking for the angular distribution of sputtered silicon atoms, and we have here normal incidence to the surface in 40 degrees. And SRIM tells you that all ions with the SRIM 2008, all ions will be emitted normal to the surface in both cases, with almost no angular distribution. So that's clearly programming error. That has nothing to do with reality. Then there has been a modification of SRIM after I told Jim Ziegler that there's a problem with target elements having atomic numbers smaller than 18. 18 is argon, I think, and silicon is 14, aluminum 13. So then Jim Ziegler modified the program. So he has adjusted the program. He has not corrected the error. He did not find the error. He only knows there's a problem with light elements in the target. So he has adjusted the problem so that for silicon you get now a distribution like this, which is actually narrower than the real distribution, and it still does not represent the forward sputtering if you have some grazing incidence of the ions. For silicon, it looks like this, so it's adjusted, so it looks normal, but the sputtering yield is maybe a factor of almost 2 off from the real value, which you actually get from SRIM. So it's not just a correction, it's what people call fudge factors, which are included in SRIM. And if you do the same simulation with a new version of SRIM for not for silicon as a target, but for aluminum, you would get once again the same situation for which you get for 2008. So SRIM tells you all ions are sputtered in normal direction, which is wrong. And this error also follows up if you have a compound target like silicon oxide, where you have lighter atoms than silicon. So this error has not yet been solved, and it still exists in SRIM. So all the sputter yield calculation with SRIM, which contain elements lighter than silicon, even if you have a compound which contains oxygen and carbon, are problematic and give you the wrong situation. So the upper row shows you the results from SRIM, completely wrong, and the lower row shows you calculations with SDTrim, which shows you angular distributions and also sputter yields, which you can compare with experiments which are really accurate. Also, if you calculate sputter yield and you measure it, we have done this for certain cases, xenon and silicon, you see the energy is typically what you need for sputter erosion and pattern formation experiments. You see the SDTrim fits very well to the measured sputter yield. For SRIM, depending on the versions you choose, you have significant deviation. And also here for 1 keV xenon and germanium, SRIM is not very accurate on the value of the sputter yield as function of incident angle. So you can use SRIM simulations to estimate sputter yield value, but it's a best guess. There are significant deviations, either much stronger, much larger, or much lower, and the angular dependence is not represented correctly. So therefore, just forget sputter calculation with SRIM. Okay, now you can follow up the sputter data by storing an output file, and then you can make a histogram. So you follow up every sputtered atom. You see the energy, you see the lateral position where it's removed from the surface, and you see 3 cosine values which describe the angle under which the atom is removed. So by storing these text files, you get all the bookkeeping data on the sputtered atom. And of course, sputtering is then a statistical process. So for the number of ions, you see sometimes no atoms are removed, sometimes up to 20 atoms are removed. For the case of 2 keV xenon and copper, And as an average value, which is the black line, you get some average sputtering yield, which is then maybe plotted with SRIM or output with SDTrim. So you see there's a strong variation for individual ions, and you have to do a large number of incident ions calculated to get a decent value of an average sputter yield. But you have to have in mind it's an average sputter yield. In one single collisions, you may remove maybe here 18 atoms, so you small a form crater, and in one single collisions you may actually sputter off atoms with the total energy up to 450 or an ion with up to 450 electron volts, so very high energetic ion. So you have strong variations, and sputter yield and the energy you get per atom is just an average value, which a large distribution, and to get a decent value of this average value, you have to calculate a large number of incident ions. And you see here typically 1,000 up to 1 million ions are typically calculated in dynamic simulation with SRIM. For the calculation which we do for pattern formation, we typically are between 10 and 100,000 ions per input condition, energy, ion, incident angle, and so on. Okay, if you do these dynamic calculations, as we saw for implantation, you can get concentration profiles. You see particle reflection coefficients, which just reduce if you change the target composition, let's see here from tantalum carbide, and add some iron. And you see here the particle sputtering yield, which change with fluence until you have reached a steady state condition with a more or less time-independent composition of iron, carbon, and tantalum, which defines eventually the sputter yield. So also the sputter yield in the dynamic way depend on the fluence, and they will change with time or with fluence, and so the sputter yield will change if you start changing the composition of your compound target and if you implant target atoms in the in your material. So to get a real picture, you have to do the SDTrim simulation dynamically. You cannot get this information from SRIM. And now maybe let me see how much time do I have. Now it's 15 minutes for 12. Maybe I have some minutes left. So that goes back to the questions, can you see difference in the interaction potential? And the answer is yes, but you have to do a very tricky experiment. So we have done an analysis of an X-ray multilayer mirror, which is a tungsten silicon multilayer disc that's deposited on a wire. And so you see here the different layers of tungsten and silicon. The black is the tungsten and the white is the silicon. And this is deposited by laser deposition, by pulsed laser deposition. And there you deposited some energetic ions. So you will have, during the growth process, some erosion of silicon and tantalum while you do this. And eventually you have this disc, it's like a Fresnel disc, and you use it for X-ray diffraction to get a pattern. And now what they know from the laser deposition, that the growth rate depends on the laser fluence for silicon and for tungsten, and there are certain thresholds, and then it's saturated. And the layer thickness which you get, so the layer grows here, just increases and reaches some steady state growth rate as a function of number of laser pulses. So you have initially a low growth rate and you start here. And for tungsten on silicon, you see just a linear growth rate. And for silicon, it's different. And the reason is, if you implant silicon in tungsten, you have some sort of reflection or backscattering of silicon, and you have to reach a steady state until you get a constant growth rate. And we tried to simulate this with a dynamic trim simulation. So to get this experimental observation realistic? Is it just a ballistic effect due to the implantation collision cascade, or it's a chemical effect? So we have to do some simulation, and we calculated the sputter yield of silicon and tungsten as a function of fluence, and we followed up the growth of the film and the concentration of target atoms. So black is the silicon. We start depositing silicon and tungsten. You see a growth of silicon, and there's some intermixing with tungsten. It decreases, so we get really details of the ballistic effects going on. And then we look for the total yield, the backscatter yield, the sputter yield, and there we see difference between the CBL potential and Gauss-Legendre integration and the krypton-carbon potential. And these give completely different values of the amount of material you lose in this process. And only with the krypton-carbon we can actually describe what we actually see here on the evolution of the silicon film, which grown on a tantalum film, but it's not able to follow it up with the CBL potential. So there you see one case where you see that the CBL potential, which is used in SRIM, provides you completely different loss fractions of ions, which you see here in these two diagrams as a function of fluence. And this is one of the few examples where you see that you see significant differences in these screen potentials, in particular if you have just some combinations of heavy elements and light elements like tungsten and silicon. So this is a problem which we could solve and explain just by ballistic effect in the collision cascade, but we saw we have to choose the right potential. Okay, then I will just flip through the bookkeeping. You can just get the end positions of all the recoils, or the position of where atoms are removed from the atom. So from these positions where you remove atoms, you can calculate something like a crater function. And if you look where are the start and end positions of your recoils, then you can calculate something like a redistribution crater function. And so this is some examples which you can get from SDTrim. So the erosion crater, it's like an impact of a meteorite on Earth, and then you see a depression which has a certain center and a certain size depending on the incident angle and the ion energy. So you can, as an average value, calculate something like an erosion crater using, on atomic scale, using just the bookkeeping data you analyze, which you obtain from SRIM or SDTrim. And for SDTrim, you can look for, if you neglect the erosion and just consider the recoils, so you move the recoils from the initial position to a new position, and this gives you a recoil crater which has a rim, which is the red one, and a depression in the center, which is the green and blue one. So in average, for the just recoil collision cascade, you do not lose any atoms. So you need some rim and a depression, so the total loss of material is 0. And this is how a recoil crater looks like. And this is the erosion crater, which we obtain from SDTrim. So this can be calculated, and this is an important ingredient in calculating the parameters which you need for this differential equation for pattern formation. So you need, let's say, the size and the magnitude and the extension of these crater function. Okay, just a view into a silicon target which you irradiate with carbon ions incident at 60, with xenon ions incident at 60 degrees, and you can just plot where are the recoil end positions, and you see actually what happens. So you displace recoils and they come to new positions somewhere in the target, and that's where the deposition also energy which is transferred in these elastic recoil collisions. So this maybe it's just a recoil end position distribution, but it could be in some way roughly converted to some energy deposition in the volume of the silicon. And as you see, if you go to grazing incidence, so then the system uses the memory of the incident. So it's just forward. So the atoms are forward, but it more or less looks symmetric. So if you're going in and you have some reflected xenon ion, the momentum transfer is downwards, which you see here. But in total, you shift the recoils a little bit in forward direction by a few nanometers. Okay, so there's two examples of crater functions. If you look inside, where do the atoms go to from initial start to a stop position? Can be extracted just from bookkeeping. Now, one funny thing is there is this term thermal spike, which is typically known from very high energy collision, so that you have huge electronic energy loss, which eventually goes to vibrations of atom and high temperatures. But there's something at a thermal spike at low energies, at keV energies. So what you can do, you can go through your bookkeeping data. And so these are individual recoils. Species 2 is silicon, species 1 would be argon. And you see the start energy, the start position, somewhere the stop energy, and you see all the energy transfer data. Also the time in femtoseconds when the collision takes place. And you can just make a bookkeeping of all the energy transferred in a certain volume element of an atomic size. So determine what is the energy which is deposited in a certain atomic volume element, which is, let's say, the difference between the incoming energy and the outgoing energy. So there's electronic energy loss, and then maybe some collisions which do not lead to recoils, but just thermal vibrations. And you just plot this energy, and you can convert this energy per atom into a temperature using this relation. 1 eV is 11,600 Kelvin. And then you get a plot of a temperature distribution, 3D. So this is the ion is coming in from the bottom, and this is 100 eV carbon on some carbon target. And plotted here in this explosive view is the atomic unit cells, and the color describes actually the energy per atom deposited in these unit cells, and the color and this converted to a temperature. And you see here we get a maximum temperature of 6,000, almost 6,000 Kelvin. So that's beyond any melting and vaporization temperature for graphite. But this is a temperature which exists only for a very small time window of between femto and picoseconds. And then the energy dissipates through thermal conduction, and then it cools down. But you see, the ion impact is as a process extremely far from thermal equilibrium. And you can create a tiny thermal spike in a small volume using these low energy ions. Okay, this can be calculated also for, let's say, for 5 kV nitrogen's molecules going into silicon. So 5 kV is distributed over 2 nitrogen's atoms. And you see also here we end up 4,000 Kelvin heating initial temperature of the silicon. And you see it's a relatively huge hot volume which you have, which immediately cools down in picoseconds. But it may be the question, what happens within these picoseconds when this volume is extremely hot? So you may have a lot of rearrangement processes going on and diffusion processes going on, which you cannot really describe by the binary collision program, but you can calculate the start condition and the start temperature condition, and then maybe develop some thermal diffusion model describing what happens in the a few picoseconds when you have these extremely high temperatures. Once again, argon on silicon, 1500, 1.5 keV. You are beyond the melting temperature of silicon, 3500 Kelvin. But of course, you do not evaporate silicon, because the question is, within 1 picosecond, how much silicon atoms can you evaporate? So that also has to do with some diffusion steps and so on. But actually 60% of the energy goes into heating up of the system, and it creates a tiny hotspot thermal spike in this region. So this is one funny aspect which you can get out from the bookkeeping using the binary collision approximation. And that's nice to have also this feature to calculate this far from thermal stability effects with binary collision programs. Okay, and the last transparency. When you get the the SDTrim program, you get the source code, which is a Fortran code. Maybe some of you are familiar with Fortran or know someone in my age who is familiar in Fortran programming. So you can include some other options of bookkeeping. And one of these options is just to calculate moments of erosion or redistribution, which you use for this crater function for pattern formation. So you can modify the program to get all these, let's say, first, second, third, fourth, sixth moment of recoil distributions, and then you get the complete crater function moments. And these are the input parameters for the analytical differential equations calculating pattern formation. So I have rewritten one program which, just to avoid confusion, is now called not SDTrim, but SDPat for pattern SP, which gives me as a bookkeeping the output of this data. So I haven't rewritten the initial core Monte Carlo procedure, but have just modified the output that I have get more bookkeeping data which are useful for other purposes out of the program. Okay, the conclusion. I hope I've convinced you that these Monte Carlo programs using the binary collision approximation are very useful to start with calculations for any type of iron-solid interactions. They're extremely fast compared to what you can do with MD simulation. And although there are sometimes very rough approximation, many parameters you get out of it from the bookkeeping is very accurate. Like ion ranges is very accurate down to very low energies and so on. It's applicable to almost all compounds, very complex compounds, polymers and so on, and high energies. It's a good accuracy even for very low ion energy. And it includes dynamic compositional changes if you use these dynamic versions of the TRIM code. The SRIM is good for first rough estimates. It's easy to use with the user interface, but it has many undocumented approximations and error. It's okay for ion implantation. It's okay for estimated of ranges of what should this say, of sputter yield, etc. And for ion ranges, SRIM uses the approximation of this magic formula, so the scattering integral is not calculated with the possible accuracy, and it only uses the CBL potential, which is not very well suited for low energy collisions. I have shown you one example where accidentally we find a case where there are significant deviations to the experiment. And green, the dynamic versions are very versatile to use, in particular if it goes to high fluence implantations and high fluence irradiation. You can take track of stoichiometry changes, and the most flexible program is the SDTrim. You have to ask to get the source code, and you get the license for free, and then you have to compile it using the Fortran program, Fortran compiler on a Linux system, And the advantage of the SDTrim program that you can use the book by Eckstein on computer simulation of ion-solid interaction as a detailed manual for the software. To get familiar to it, also to get it started, it's somewhat cryptic, and you have this script file, but there's a good documentation to get used to it. Okay, so with this, I have reached the end of my transparency. I hope I was more or less in time, and I would like to thank you for your attention, and it was a pleasure to give this lecture at this year's school. Thanks for your attention.
Thank you very much, Hans, for very nice and enlightening presentation. And if there are some questions.
So one is there in the chat box.
Indra, can you please help me by
yes,
reading it out?
What is this correction factor about next to the density in SRIM? Slide number 30.
Okay, so SRIM is using experimental data of stopping powers. And most of these stopping powers are measured for elemental systems. And some of them are calculated or measured also for, let's say, compound systems like polymers and so on, or covalently bonded systems. And then it turns out that the problem here is that your electron distribution is not uniform. In particular, you have covalent bonds, or have your molecules like water. And to adjust this database of experimental stopping powers to a specific system where maybe someone has calculated stopping powers and found some deviation. So to correct for this, SRIM suggests some correction factors. So that is the reason you find some correction factors which you can actually arbitrarily modify, but maybe you rely on this experimental database from SRIM that you may use this correction factor. So typically it's the situation is some people do stopping experiments and see, aha, it deviates from SRIM. And then you say SRIM is wrong. But okay, SRIM cannot be wrong because it only uses a fit to experimental stopping data. So you have to extend your database, in particular for compounds and like polymers and covalently bonded system. And one option made in SRIM is for certain compounds to suggest some correction factor, which actually somehow a little bit modifies the density, which also modifies the stopping values. So that is just one of the fudge factors, many fudge factors, which is included in SRIM to better get to reproduce experimental values. So that's behind it.
Okay, so one student, this Taranga Dehuri, wants to know how to know the temperature of the material during irradiation process experimentally.
That's a good question. Actually, if you have several thousand atoms and you can calculate it using SDTrim, some energy per atom. So energy per atom is a quantity which is okay, but temperature is a thermodynamic quantity. And the question is, how can you define a temperature for a limited number of atoms, in particular for a short period of time? So there has been an idea to measure the temperature. This has been done many years ago at Hahn-Meitner Institute for ion tracks, high energy ion tracks. So you measure you measure the emission of Auger electrons and you analyze their energy distribution. And from there, you get an idea of the initial local temperature of the impact site for a high energy ion track. This can be done. Otherwise, I don't think there is a way to measure it. So the time scale is so low. You cannot see it, let's say, optically. A temperature of 6,000 Kelvin would be optically the temperature of the sun. Okay, it should be bright as the sun. But on the time scale of picoseconds, you have almost no photon emitted. And so there's no way. So the only thing is left. There are temperature measurements through Auger electrons for the high energy ion tracks. Otherwise, you only can get maybe indirect information about this temperature through possibly some diffusion effects going on, or let's say redistribution of atoms. You get the idea. There must be a high temperature from the energy you deposit. And okay, you have to use energy conservation. You cannot just throw away this energy which is deposited to the target atoms without going into recoils. So there must be this energy for a short period of time. You can apply a thermal diffusion model to see the dissipation of the energy. That's similar what is in the ion tracks software, which was written by Marcel Toulemont. There's also some thermal dissipation included. So that's the way you can go. And then you have to look for experiment which accidentally show you the effect of this thermal spike at low energies in some experimental quantity. But maybe just pattern formation, the smoothing of pattern may be one case where you may have a chance to see it. But I have not found a case where it's very obvious to see it. So that is my answer to this question.
Okay, so any other question? Ambusa, you raised hand. Do you want to ask something?
I just wanted to, because a lot of people are using this for 2D materials. So where this is stopping power, people take, this is what the most commonly SRIM a lot of people use for stopping power. So can you say for the students' benefit, if they are trying to use for the stopping power, which program will be the best suited for calculations?
2D materials.
Okay.
In 2D materials, where just a single layer or two layers are there and charge equilibrium is not reached.
Okay, with 2D layers, okay, depends on the energy you use of the primary ion. So probably I'm the only group worldwide which does ultra low energy doping of 2D materials, where the incoming ions have energies of around 20 electron volts. Many experiments are done with higher energetic ions where you just create defects in the material or have electronic energy loss. So then you can use, for example, the SRIM stopping powers. It's okay, you can use the D-pass, but as I said, the D-pass is calculated, and at low energies, the D-pass stopping, electronic stopping, gives you higher values compared to SRIM. So then it's the question up to you. Do you rely on a pure theoretically calculated model or some fit to experimental data? So that's the difference between D-pass and SRIM. And at very low energies, then of course the electronic stopping is not anymore important. So then you have to deal with the nuclear collisions. But then you run into another limitation with the Monte Carlo programs. You assume an amorphous matrix, but your 2D materials are crystalline materials, 2 or 3 or 4 layers of crystalline materials. So then you should have to rewrite, either you say, okay, I do some hand-waving estimates for the amorphous 2D layer with the same number of atoms per square centimeter, or you have to rewrite your program to include a crystal structure. So you have to reinvent something like the crystal trim. Crystal trim cannot be used for the 2D layers. Or you have to go to molecular dynamics simulation, which has been done, for example, by several groups, also a group in Rossendorf. But then you have the choice. You do MD simulation, very accurate for a system which you understand for MD, and then you do a simulation which takes several months, and you have several thousand atoms simulated, and from there you want to do some statistical analysis. Or you assume an amorphous matrix, and you do the simulation in 20 minutes with 100,000 ion, and get much better statistics, but under the assumption of an amorphous matrix. So that's the balance you have to choose.
Okay.
that's my suggestion if you want to deal with 2D materials.
So is it okay, Ambut sir?
Yeah,
Is there any
fine.
simulation program to study electron beam damage on samples? Electron beam. For electron beam, is there any code available?
For electron beam, there is a program similar to SRIM. I forgot the name, but it calculates. It's essentially designed for, maybe Marcel Tullemont knows how it's called. Casino, is it called something Casino or something? It's you can calculate them. You can get a Monte Carlo program which calculates electron cascades and all these electron effects. So that's available, which is mainly used for calculating effects in electron microscopes or these electron cascades, maybe in high energy ion tracks.
Yeah, John sir has written Casino V2, V3.
Yes.
These are the programs.
Yeah. So this is also an option. If you stick to electrons, I think Casino is a good choice to use.
Okay, Som sir, over to you. Som sir?
Jérôme asked no relativistic effect. Okay, typically for the energies which we use, let's say kV or for ion implantation, you do not really need relativistic effects. However, there's this funny situation. The question, the energies of the ions are definitely, or the velocities are small enough so that you can treat it with classical mechanics. Relativistic is only if you go to several hundred MeV light ions or several GeV uranium, then you have to take relativistic effects into account, or you have to consider relativistic effects for the electron collision cascade. Another point is for the collision, you can use just simply classical scattering kinematics with one exception. This is higher energetic scattering of protons or light ions. There you might come into the situation that you have described the scattering quantum mechanically. And the other system is if you have scattering of identical particles, so-called mod scattering. There you also run into some quantum mechanical effects which change the scattering cross-section. So these are the two changes where two situations where you have to consider quantum mechanics. Of course, typically these cutoff parameters include some quantum mechanical simulations using Born approximation, for example, to derive the Bethe formula. So there quantum mechanics comes into play. For electrons, of course, you much more easier enter the situation where you have to calculate relativistic effect. This starts from above 10 or 20 or 30 keV electrons, which are significantly relativistic.
Okay, sir. So
okay, Jérôme just said Casino relativistic effects.
Yeah, he was explaining actually
included.
that it is not including the relativistic effects. So it's already you have answered. So I think please join me in thanking Hofsaess sir to deliver such wonderful lectures, which are very useful for the students. So very nice, sir. Thank you.
Maybe I add one brief comment. So I've sent you the PDF of my presentation, which I've shown here, and there's also a second part which deals with these energy loss issues from a fundamental state. So you can distribute this PDF so it's can be made available for the students if you want to look up things later on.
We will be sharing the files with the participants registered for the school. Thank you so much.
Yes.
Thanks once again.
Yeah, it was a pleasure to give this lecture and see you again after some time. And maybe the next
conference
time
also.
Maybe the next time I can come to Delhi.
No,
when all this nightmare, when all this nightmare with Corona is over.
Correct.
Okay.
You have another talk in the conference also.
So
next week, yes.
Yes. Okay, so
okay, I hand it over to you and Nabuj. Please take care of the.
Okay. Thank you so much, sir, for chairing this session.
Okay.
We will. So wait, we will be having some participation interaction. Interaction with the participants. You can listen to a few of them. What are they working on? So let us begin with alphabetically from the list of participants which are seen on the screen. So Abid, are you there?
I can just was saying we should stick to research scholars and just tell them for 1 minute, because if the list is
only just take 1 minute since there are many to introduce. So
your
define
PhD
your name,
problem. So where are you
affiliation,
from?
and what
PhD
you're
problem.
Yeah, please. So let us begin with Abid. Abid, are you there? Okay, Aditi wished. Aditi?
Yes, ma'am.
Please, can you turn on your video so that we can see? All of you, please turn on your video, because this is the only time you will be allowed to turn on your videos. We will be taking a screenshot. Okay, just a moment. Maybe Abid is trying to say something. Abid, wait, let Aditi finish.
Hello, everyone. Myself, Aditi, and I'm from Indraprasth University. And I am under the supervision of Dr. Satyabrata Mohapatra. And I'm currently working on metal oxide nanohybrids and nanocomposites and its application for gas sensing and photocatalysis.
Okay, very nice. So next, Abid, now you can say something. Your audio is very bad. It's not coming properly. So I think you mute yourself. We will go to the next one. You try to sort out your audio. Okay. So Amandeep Sharma.
Hello everyone, I am Amandeep Sharma. So actually I am the beginner in this field of ion beams. So till before I did some work with gamma radiations by applying gamma radiations. Now I was looking for the possibilities to do some work with this field as well. So in that sense, this school is very helpful, and I thanks to organizers for providing me such a platform, especially in this period of pandemic. So thanks a lot to all.
Okay, you are most welcome. So next is Anand Pandey. Anand Pandey wrote, same here, so you don't want to introduce yourself. Next is Anand. You want to say something, or shall we go to the next one? Balwinder Singh. Balwinder Singh, are you there? Okay, Bhanupriya. Next one is Bhanupriya. Bhanupriya. So it is actually helping us to know that people are actually attending the school, or they are just signed in and not actually attending the school. Bhanupriya, are you there? No. Bhargava Rajya Guru.
No, Bhanupriya is there. You have to unmute yourself, Bhanu.
Okay. Bhanu, there is a mic button here. You can see down ribbon mein, there is a mic button. You just click on that. Achha, it's not working. Okay, so you write in the chat box. I will introduce. So by the time we can go to Bhargava Rajya Guru. Bhargava, are you there?
Yes, ma'am.
Yeah, please introduce yourself.
I am Bhargav Rajiguru from Saurashtra University, Rajkot, and I am working under the guidance of Professor Nikesh Shah and Dr. Piyush Solanki. I am working in the field of bilayered manganite-based thin film devices, in which we are studying the irradiation effect to improve the electroresistance.
Okay, very good. So, Bhanupriya, what you have written? Still she may be writing. So, Balwinder. So when I called the name, were you not there? Balwinder Singh, please go ahead.
Yes, ma'am. Good evening to all of you. My name is Balwinder Singh. I am doing PhD under the supervision of Dr. Sanjeev Puri at Punjab University, Patiala. My PhD problem is the investigation of charge particle interaction with some heavy elements. and I'm currently working on M-shell X-ray production cross-sections. And I have also applied for BTR1 for Pelletron and LEIVF in IUAC and New Delhi. Thank you.
Okay, very good. So Anna, we missed your name, Anna Masharat. Are you there online? Anna? Please keep your videos on for short time.
Hello,
so that
good
we
evening,
can...
everyone.
Yeah.
Good evening, ma'am.
Good
Can
evening,
you hear me?
Anna. Yeah, please go ahead.
Good evening, ma'am. Myself, Anha. I'm doing PhD from Jamia Millia Islamia, and I have also worked under in a project with Ashokan sir. My thesis problem is studying of thermoelectric properties of CSV3 scutterite, and I have utilized ion implantation method to dope various elements and then studied its thermoelectric properties. Thank you.
Okay, very good. Thank you, Anna. Okay, so next is Bhanupriya. She has written that I am pursuing
you, ma'am.
PhD from Central University of Jammu under the supervision of Dr. Tanush Deshwal. Okay, he is our student actually. IUAC's former student. I am currently working on vanadium oxide thin films and their various applications. Okay, nice. I hope the school will help you. So next is Colin Retar. I don't know. I'm not able to pronounce his name.
Colin B. Nettar, ma'am.
Okay, sorry. So please introduce yourself.
Hello, ma'am. Hello, all of you. I am Colin B. Nettar. I am from Pondicherry University. My research supervisor is Dr. R.N. Baumi. Now I am working on aluminum oxide, and also
Okay.
the next year we are working on the gallium doped Al2O3. Thank you, ma'am.
Okay, thank you. So DP Datta. Are you there, DP Datta? I think you are Devi Prasad Datta, Dr. Devi Prasad Datta.
Yeah, he has a oral presentation. So
Where is he?
Leave him. I mean, he's quite senior, so.
Yeah, I said that.
At the short form.
Scholars, I think that's better.
Okay,
Yeah, we stick to research scholars, so
fine.
faculty we can.
So Dhan Balan Dhandapani. Dhana Balan Dhandapani. I don't know whether I'm able to pronounce it properly. Dhanabalan, are you there? My mic is not working. So please write it in the chat box. Next one is Dilruba Hasina. Dilruba Hasina, are you there?
Yes, ma'am. Good evening, all of you. Hello.
Yeah, please go ahead.
Myself Dilruba Hasina. I am from Institute of Physics, Bhubaneswar. I am working under the supervision of Professor Topic-Nano-patterning and my thesis title is Nanoscale Functionalization of Tier 2 Thin Films for Artificial Synapse Application using Low Energy Ion Beam Facility.
Okay, very good. So next is Dirga Mankad. Dirga Mankad.
Yes, ma'am.
Yeah,
Yes,
please
ma'am.
introduce.
Namaste to all the delegates and all the research scholars. I am Dirka and I am presently located in Rajkot and I am the student, research student under the guidance of Chetwa sir from Saurashtra University, Department of Physics, and presently I am working on the crystals which are made up of transition metals and I am interested to explore its applications. Thank you.
Okay, nice. So Dhyaneshwar Dake. Please excuse me if I'm not pronouncing the names properly. Yeah, please.
Okay, ma'am. I'm good evening, all of you.
Yeah, good evening.
I'm Dr. Dhyaneshwar Vittal. I'm doing PhD from Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, and my research topic is synthesis and diverse property studies on chromium substituted ZNS nanowires for photocatalytic application.
Okay, very good.
Thank you.
Welcome. So Vinayak Hegde, Dr. Vinayak Hegde, are you a Vinayak Hegde, are you there? Hemant Chaurasia.
Hello, good evening to everyone. Myself Hemant Kumar Chaurasia, and I am working on the metal semiconductor Schottky barrier structure, effect of the ion radiation, beam ion radiation, and I have just completed my pre-PhD submission, and just I am submitting the thesis, and I have done the work at IUAC for the beam time application. So we have published 2 or 3 papers like palladium and silicon Schottky barrier structure and titanium and silicon Schottky barrier structure. And now I'm working between the metal and semiconductor at an interfacial layer like zinc oxide or graphene or MOS2 type structures. So we will see the effect of the ion radiation on the interfacial layer of nanostructured materials. Thank you.
Okay, so from chat box, I am taking Dhanabalan Dandapani. I am pursuing PhD at Crystal Growth Center, Anna University, Chennai. Currently, I am working in gallium oxide technology. Since gallium oxide can be utilized as an extreme environment material, and I am concentrating on irradiation studies of OFZ grown gallium oxide single crystals. Okay, thank you. So next one is Himani. Sorry, where was I? Hemant Chaurasia. Hemant Yadav. Jatav. Hemant Jatav, he is our student. Please unmute yourself, Hemant.
He is already unmuted.
Okay,
so.
go ahead.
Yeah. Okay. Good evening to everyone. My name is Hemant Jatav, and I am doing my PhD at IUAC itself under the supervision of Dr. Dedulal Kaviraj. And currently, I'm working on ion beam interaction with the metallic nanocomposites, where the metallic nanoparticles are embedded in some dielectric matrix. So I also would like to thank every speaker for very informative lectures and all the participants as well. Thank you. Thank you very much.
Okay, good. So Himani Saraswat. Himani, are you there? Next is Himani? No. So Jaya P. Jaya P. So unmute yourself. Please introduce.
Hello, ma'am.
Hello.
I'm Jaya. I'm doing research from Mother Teresa University. My research guide is Dr. Guma Devi. And my research problem is to analyze the effect of fifth heavy ion metal chalcogenides for thermoelectric application.
Okay. I hope this school will be beneficial to you. So let us go to Jishna Rahman. Jishna, are you there?
Yes, ma'am.
Yeah, please unmute yourself. Okay, please please go ahead.
Okay, ma'am. I'm Jisna Rahman from Calcutta University, and my research guide is Dr. N.E. Rajivan sir. And my topic is fifth heavy ion induced enhancement of magnetoelectric coupling in rare earth doped multiferroic films, and I'm concentrated on multiferroic films.
Okay, Jishna, thank you. So Anand Pandey is writing, hello everyone. I'm Anand Pandey. I'm working on organometal halide perovskites for energy applications under Professor Lokendra Kumar at University of Allahabad. So I hope this school will be beneficial to you, Anand. So next we will be going to Kalyan Ghosh. Kalyan. Are you there, Kalyan?
Yes, ma'am.
Yeah,
I am Kalyan Ghosh from Niger. I am working with Dr. Pratap Kumar Sahu. I am using ion beam to thin film. Basically, I am trying to grow zinc telluride thin film with silicon ions and gold ions. It will help to make some defects on the film. That is our aim.
Okay.
And this is a very useful talk. I am recently working on ion beams, started recently.
Okay, that's good. So next is Mahendra Rathore. Mahendra Rathore, are you there?
This is good evening. Myself, Dr.
Your voice. Sir, are you a faculty or?
Yes, ma'am, I am faculty right now. Previously, I completed my PhD from MNIT in the ion irradiation with the heavy ion on the germanium oxide principle. Presently, now I am currently working with the low ion lithium ion in the germanium oxide and as well as the peroxide material.
Okay. So thank you, sir. Next is Manoj Kumar Rajbhar. Manoj Kumar, are you there, Manoj? Okay, yes, ma'am. So you cannot. Your mic has some issues, and you write in the chat box. I'll read from there. Okay. Next is Mansi Tyagi. Yeah, please go ahead.
Hello,
Mansi.
everyone. I am from IP University, currently doing PhD under the supervision of Dr. Mohapatra, and I'm working on two-dimensional materials for sensing applications. Thank you.
Okay, thank you. Next is Mayur Khan. He is our student, IUAC
Yes, ma'am.
student. Yeah, please.
Good evening to all of you. I am Mayur Khan, IUAC student. Under the supervision of Dr. Ambus Tripathi, I am doing my PhD title of my thesis title is 2D band gap engineering of the 2D materials by using the ion beam. And I would like to thank to all the speakers for giving us such a nice talk and effective talk.
Okay, thank you, Mayur. Next is Monica Sahayam. Sahayam. Monica. Monica, are you there? Monica. Next is Navjyoti Bhagat.
Can we mute Mr. Srinivasan? The noise coming from that.
Okay, whoever's mic is not working, please write your introduction in the chat box. So I will read it all of them together. Okay, please write it in the chat box. Yeah, Navjyoti, please go ahead.
Yeah, good evening, ma'am. Good evening, everyone. Actually, I am Navjyoti from Department of Physics, Guru Nanak Dev University, Amritsar. I am pursuing my PhD under the supervision of Dr. Aman Mahajan, and my research topic is basically third generation solar cells. So I want to explore ion beam implantations work in solar cells. Thank you, ma'am.
Okay, thank you. So what material you are using to make such cells?
Hello. Yeah. Actually, ma'am, basically we are using. I'm working on different solar cells like DSSCs, perovskite, and also quantum dot. So these are particularly different.
Okay, thank you. So Nisha, next is Nisha Tanka Chen. Nisha, are you there? So next one is Paramita Patra. So Paramita, you unmute yourself and introduce. Pankaj Mohanty. Pankaj.
Good evening, ma'am.
Yeah.
Am I audible?
Good evening. Yeah.
Thank you.
Go ahead.
I'm Pankaj. I'm lecturing at University of Johannesburg, South Africa, and my research interests are rare earth and transition metal oxides and their magnetism changes with the application of ion beams. Thank you for organizing and this nice school, and thank you all the delegates.
Okay. Welcome. So Pooja Tiwari. Next is Pooja Tiwari. Pooja, are you there? Prachalit NC. Prachalit. Unmute yourself. Unmute yourself. Your mic is muted.
Hello. Hello. Myself, Prachalit NC, ma'am.
Go ahead. Yeah.
And I am new to the research field, and I am interested in ion beam technology. And I am from the Karnataka Krishnadevara University, Karnataka, Ballari. And I am wishing to do my PhD under the Uday Kumar Kadke, sir. My
Okay,
work is
so
on
you have
regarding hello
okay, so you are
irradiation
new
effects
to
on
ion
the
beam field.
yes ma'am, yes ma'am. Uh, and my intention is to study about the this one spectroscopic effects factors, how it is going to affect on the how the irradiation is affecting on the chlorine based fluorescent salts that is used in the dye based solar cells. So that is what, and these sessions has helped me to create my new ideas and new problem even.
Okay,
Thank you.
that's nice. So 3 more days to go. Sincerely attend the school. Next
Okay, thank
is
you.
Punita. So Punita has some issues with the. Punita, are you able to mute yourself and speak? Punita has written that I am working as a JRF at IUAC and I am planning to do some ion matter interaction using low energy ion beam, and I am actively participating in school. Thank you, Hans sir, for such an elaborative talk about simulation technique. Okay, so I hope he has heard you, Punita. Thank you. Next is RK Singh. RK Singh, Rajeshri Urkude. Rajeshri, are you there? Please unmute yourself. Rajeshri, has she written here? So next is Rathika. Rathika. Rathika, she has written in the chat box. So she is a research scholar from TBML College, Poraya, Tamil Nadu, and she is doing research in transition metal oxide thin films and improving their properties for optoelectronic devices by irradiating with swift heavy silver ion beam at different ion fluences. And I did my irradiation experiments at IUAC. So you have some experience already with the ion beams. So I hope this school will help you further. So next is Renuka Chauhan. Renuka, can you unmute yourself? Ma'am, I'm on the way to home from college, currently working in Puma University. Okay, no problem. So Richa Sharma. Richa Sharma, are you there?
Hello.
Yeah, please. So you introduce yourself, Richa.
Good evening, ma'am. I am
Good
Richa
evening.
Sharma, research scholar at the Department of Physics, SRT campus, Garhwal University, and I have been working on in thin film field, and in their interaction with ion energy, and I have also participated in the ion beam experiments. Now I'm just finishing my thesis work, so I'll be submitting within next 2 months or so. And thank
Okay.
you for this school. Thank you, ma'am.
Okay, thank you, Richa. Next is Sangeeta Basa. Sangeeta, are you there? Sangeeta, let me see if she has written here in the chat box. Otherwise, we can go to the next one. Sanjay Kumar. Sanjay Kumar, please unmute yourself. Yeah, go ahead. Please speak up. Sanjay, your voice is not coming. Are you saying something? Okay, please write in the chat box. Are you speaking something? We are not able to hear you. No, the voice is not coming. So please write in the chat box. Okay, kindly write it in the chat box. I'll read it. Santosh. Santosh.
Hello.
Yeah.
Good evening, madam.
Good evening.
I'm Santosh from Karnataka, VSK University.
Okay.
So I'm joined for a PhD program under the supervision of Dr. Uday Kumar Kadke, and I'm working on the field ion beam modification for ferroelectric polymer nanocomposites.
Okay. Thank you. Next is Shikha Kaushik. Shikha.
Hello, good evening, ma'am. Hello.
Good evening. Yeah, Shikha, please go ahead.
Ma'am, I am pursuing PhD from MNIT University, Noida,
Okay.
under the supervision of Professor D.K. Avasti.
Okay,
Currently, I
that's
am
good.
working on metal-rich metal oxides for RAM applications.
Okay.
And I will be using this ion irradiation for making my RAM metal-rich by that ZNO layer. And thanks for such an effective talk on simulation techniques that I have heard today.
Okay, you're welcome.
Thank
So, thanks to the speakers. Shipra Chaudhary. Shipra? Shipra, are you there? Yeah, please.
Good evening, everyone. I am Shipra Chaudhary, research scholar from Indraprasth University, New Delhi, and I'm working under the supervision of Dr. Satyabrata Mohapatra and working on the development of visible light active multifunctional hybrid nanostructures for environmental applications. Thank you.
Okay, nice. Thank you. Shivani Chaudhary. Shivani, are you there?
Hello, ma'am. Hello, ma'am.
Where are you? Yeah.
Hello, ma'am. Good evening, ma'am.
Yes. Good
I'm doing
evening.
PhD from DDU Gorakhpur University from under the supervision of Dr. Uday Bhan Singh. I'm new enrolled in PhD. My research topic is not selected yet. I'm very thankful to all speakers and organizers of this school. This is very beneficial for me. Thank you, ma'am.
So, Uday is also our former student. You know that? He did
Yes,
PhD
ma'am.
from here. So,
Yes, ma'am.
attentively attend the school. Otherwise, we will give the feedback to him. Okay?
Yes. Yes, ma'am.
So, next one
Okay, ma'am.
is Shivar.
Thank you.
Yeah, thank you. Shivaram NJ. Shivaram? Yeah,
Hello,
please.
ma'am.
Yeah, hello.
I am Sivaram. Currently, I am working as a postdoctoral research fellow at University of Free State, Bloemfontein, South Africa. My
Okay.
top here, working as a luminescent material for solar cell application. I have done PhD from Bangalore University with collaboration of IUAC New Delhi.
Okay, that's nice. Thank you. Sidhu, Sidhu Mate Panavar. Sidhu, are you there? Sidhu. Okay, Srinivas N. Srinivasan S.
Good evening, everybody.
evening,
I
sir.
am Dr. S. Srinivasan,
Oh.
working as an assistant professor of physics, Presidency College, Chennai. Currently, I am working on some metal oxide semiconducting nanomaterial like zinc oxide, tin oxide, and titanium oxide for their applications in photocatalytic as well as energy storage applications. I
Okay,
think.
thank you, sir. I hope this school is benefiting you.
Yeah, I have already applied AUC proposal for getting such a proposal. This school will be very much helpful for understanding some concept how the ion beam modifying the structure and the electronic properties of the material. Thereby, we can tune and increase the efficiency of energy storage applications as well as photocatalytic applications. So,
Certainly, sir.
I thank IUAC and other organizers for giving me this opportunity to attend this school. Thank you.
Thank you, sir. Welcome. Surekha Chaudhary.
Hello, ma'am.
So, yeah.
Hello, my name is Surekha Chaudhary from Manavrachna University. I finished my MSc and worked in material science field. Thank you.
Okay. Taranga Dehuri. Taranga Dehuri. Taranga, are you there?
Yes, ma'am.
Yeah, please go ahead.
Good evening. My name is Tarang Dehuri. I am from IIT BHU. I am working in material science department on the functional properties of transition metal oxides. Thank you.
Okay, so you have some interaction already with ion beam or new to the field?
I am basically new to the field, lekin I have submitted one proposal for ion beam.
Okay, okay. Fresh AUC. Okay.
Yeah.
Okay, all the best. So Vinayak, Vinayak, are you there, Vinayak?
Yes.
Yeah.
Good evening, everyone. My name is Vinayak. I had completed my PhD in 2016 from JNU, and right now I'm teaching in the First College for Women, University of Delhi. Thank you.
Okay, thank you. Vishnu Kotwade. Vishnu, are you there?
Hello, ma'am.
Yeah,
I'm here.
please. Yes, yes, we can hear you. Please go ahead.
Myself, Vishnu Kutwade. I'm working under the Dr. Rampal Sharma at Dr. Baba Saheb Ambedkar University. I'm working on one project from IUAC, effect of SHI radiation modification, structural and optical properties of heterojunction thin films for solar cell application from last
Okay.
1 year.
So I hope this school will be beneficial to you. So
Yes, ma'am.
attentively
Yes, it is
attend all the
very
lectures.
benefiting to us. Okay. Thank you.
So thank you. So I will be reading now from here. I think I have Bhanupriya. I have introduced already. Balvinder. Sir Balvinder, Ambu sir, Balvinder Singh has asked whether IUAC will be allowing workers to do their respective experiments on Pelletron and other facilities. So this question is over to you. So next is Dhanbalan Dhanapandi. So I am pursuing PhD at Crystal Growth Anna University Center. I think I already read it. Gallium oxide can be utilized in extreme environment material. I am concentrating on irradiation studies of OFZ grown gallium oxide crystals. Punita, I have read already. Anand Pandey. So Anand Pandey is working on organometal halide perovskites. I think this also I have read. Ratika, I got confused now. So she is working TBML College Porayar, Tamil Nadu.
Yeah, I think you have completed.
Okay, sir. So Shikha Kaushik already introduced herself. She is working with Dr. Avasti. And next is Taranga. He or she, I don't know. So pursuing. Good evening, ma'am. Everyone, myself Taranga Devuri from School of Material Science and Technology, IIT BHU Varanasi. I am working on multifunctional properties of transition metal oxide. Okay. So Prachalit, you have already introduced yourself, I guess. And Bhim Khan. Good evening, ma'am. I am Bhim Khan, research scholar, Punjab University, Patiala. I am doing research on metal chalcogenides, thin films, and improving their properties for device applications. Okay. So Manoj Kumar Rajbar is presently working in IIT Bhubaneswar under supervision of Dr. Shamal Chatterjee. So his topic is the modification of ID functional nanomaterial and their various sensing applications. So Pooja Tiwari is pursuing PhD from University of Mumbai, Kalina under the guidance of Dr. S.K. Dubey. Currently working on dilute magnetic semiconductor synthesis by negative ion implantation and its exploration in sprintomics. Thank you. So Anju Ajo. Hello everyone and good evening, ma'am. Myself Josli Jose. I am pursuing PhD from Marwadi University under supervision of Dr. Mukesh Keshwani. And I am working on magnetite-based thin films to study role of swift heavy ions in transport properties. So Pooja Tiwari has some network issues, so she has mailed. Monica Sahayam. Hello, ma'am. Myself, Monica Susai Mari, working under the guidance of Professor Narayan Kalkura, Crystal Growth Anna University. I am working on the effect of low energy ion on polymer ceramic composite for biomedical application. This session is really useful for me. Okay, thank you. We are glad. Paramita Patra, good afternoon, everybody. Thank you very much for organizing this interesting and useful school. Every time we learn so many things, basics and application of ion beam. I have completed my PhD under the guidance of Professor S.K. Srivastava in physics at IIT Kanpur. Now I am doing postdoctoral research at ITER India, Institute of Plasma Research. That's good.
IIT Kharagpur.
IIT Kharagpur, what did I say?
Kharagpur.
Okay, sorry. So Rajeshri Urkunde, she is writing that it is nice to connect once again with IUAC. Okay, so welcome. So Renuka. Dirga Mankar. Namaste ma'am, I am Dirga. I am presently located in Rajkot and presently doing PhD from Saurashtra University under the guidance of Dr. Harshkant Jetwa. I am working on studying crystals involving transition metal and finding its application. Okay, so my interest is to explore its optical applications. I'm glad to have some interesting takeaways from the school and hoping to involve it in my research. Okay, all the best. R.K. Singh. Hello, ma'am. This is R.K. Singh. I am postdoctoral at JNCR, Bangalore. I did my PhD from IISER, Kolkata, under Professor Chiranjeev Mitra. My work mainly focuses on the quantum interference and spintronic related work on topological quantum materials. Sangeeta Basak is saying that she is from Tripura University under the guidance of Dr. Ratan Das, and she is working on swift heavy ion irradiated group 2,6 semiconductor nanoparticles. So Surekha Chaudhary has introduced herself. So Sanjay Kumar is pursuing PhD from MNIT Jaipur, Department of Physics, under the supervision of Dr. Kamalendra Avasthi. And my work is based on zinc oxide nanostructure based gas sensing application. I will study surface modification in ZNO nanostructures using ion irradiation and also effect of implantation on gas sensing. Thank you so much, organizers and speakers, for very informative talks. Thank you. So Renuka Chauhan is finally, she is writing that my PhD research was on swift heavy ion irradiation induced modification on multiferroids and ferroelectric composites. Currently, I am interested in multiferroid thin films. Okay. So, ma'am, are users now allowed to take their beam time? Taranga Deuri is asking. So I think these kind of questions you can email. Ambusa, you want to say something?
Okay, since there are two people have inquired, so we can just mention that as far as the beam time is concerned, we have been writing to the users that there are two options by which we are going. If some of the users are sending their samples, so if you have a collaborator here and is ready to, the samples can be transported without getting damaged, or means you are confident that it can be done. So some people have sent it, so those irradiations have been done. We have also allowed users to come, but then you have to follow all the whatever COVID we have now is standard operating procedures which are in place. So you have to write it, get approval, and then once you come here, you have to be ready to go into this whatever is statutory quarantine is there. So like in nuclear physics, some users came, they stayed for whatever quarantine period was required, and then only they're allowed to enter the complex. So we are gradually starting, and of course we are following whatever government guidelines come. So as you must be knowing, in last what they are calling unlock 4 or unlock 5, this as the lockdown is gradually getting removed, they have allowed institutes to open for science research scholars as and when possible under this protocol. So we are following that. So if you can write a detailed mail through your supervisor that what you want to do, how you plan to do it, and what procedures and things you have in place, so then we can reply in detail. But we are operational and we started doing user experiments. Indra, you are muted.
Sorry. So we have been following it for past 2 months. So for details, you just write email to the corresponding person. So they will tell you how you can do the irradiation and other things. So Pradeep Kumar Bankar is writing that I am Pradeep Bankar. I have completed MTech Instrumentation School of Instruments, DAVB Indore. My work based on 5-axis diffractometer and their some instrument interfacing in SPEC software at RRCAT Indore under the supervision of Dr. Parasmani. Okay, that's nice to know, Pradeep. So hope this school will be beneficial to you. So I thank all the participants who have introduced themselves, and I'm wishing you all the best. And I hope I have not left anybody's name. So if somebody is left in introducing, please, you can go ahead and mute yourself and introduce. Okay, so if all is finished, then over to Ashokan sir. Sir, you want to add something?
No, that's nothing. So tomorrow we will close this session. Tomorrow again we'll log in around 9:20.
May I ask, if you don't mind,
yeah,
sir, if you don't mind,
yeah.
I just asked one question in the chat box, but it was not actually answered there. Is it possible to run SRIM on Mac operating system?
Mac operating means?
Marshall is there. He can answer that
Means
question.
Apple Macintosh. Okay, Saif sir, is it okay to run SRIM on Macintosh?
Marshall will answer, I suppose.
Oh, Marcel sir.
No.
Where is he?
He's there.
Sir, your mic is mute. Marcel sir, your mic is mute. You are speaking, but
Well, Saif has written through Wine program.
So
Marshall was talking something, but mic is muted.
Marshall sir, your mic is muted. Please unmute it. You are saying something? Every window application can run on Macintosh through Wine applications. So I hope Vinayak, now you got your answer. Okay, so with using Wine application, you can run any program. You just try it. Okay?
Yeah, thank you.
Okay, so we will be closing this session, and I hope you people are getting benefited from the school and keep looking forward from some questions from you. Actually, you should ask some questions to the speaker so that this will be an interactive session. Okay, for any small question and query, you should try to ask. So because it may be, it may be a silly question, but you can actually go ahead from that, solving that to another step.
Yeah, okay. Marshall, I think want to answer something.
Yeah, Marshall.
Yes, please go ahead.
I just get my micro. Sorry, I just say that I never use Macintosh, whatever it is, since the beginning of the computer, so I cannot answer.
Okay.
I'm very sorry, but
no problem, sir. It's already answered through Wine application. I think people can use it.
Okay.
Thank you. So, okay, good evening to means all goodbye to everybody, and now we will be seeing you tomorrow.
Thank you very much. Bye bye.
Okay. Bye bye.